Our first speaker is Martin López Corredera from Instituto de Astrofísica de Canarias. And his topic is alternative cosmologies. So the floor is yours. Thank you.
Thank you very much for the invitation. Nice to be here. I'm going to talk about cosmology, as you know, the representation of the cosmos as a whole, but not from the standard point of view, but mainly from other ideas that are in the literature. The standard point of view, usually called Big Bang, the popular name Big Bang, nowadays they call it more technically lambda CDM, is characterized by some points that I point out here. We describe the universe dominated by gravity, and the gravity is described by general relativity with the metric of Friedman, Lemaitre, Robertson, Walker, which supposes homogeneity and isotropic universe. Yes, I can see it here. There are some elements that have been introduced ad hoc in order to fit the data. For instance, the CP violation in order to understand the asymmetry between matter and antimatter. Inflation or non-baryonic dark matter, dark energy are some of the ad hoc elements. The redshifts of the galaxies are understood as a sign of the expansion, the cosmological expansion, also the motions of the galaxies. The CMB, the cosmic microwave background radiation that we receive in the microwave isotropically, is interpreted in the terms of the decoupling matter radiation at redshift 1100. Then the abundance of light elements, hydrogen, helium, lithium, etc., is interpreted in terms of primordial nucleosynthesis at the early universe, and the formation of galaxies and large-scale structure is interpreted also by dominance of gravity and with these conditions, with dark matter, dark energy, etc. These are basically the points of the standard lambda CDM. However, even if most of the cosmologies nowadays, I would say more than 98 or 99% of the cosmologies follow this mainstream idea, there are other ideas in the literature. And it deserves to be dedicated some time to explore other ideas too. Since cosmology is a quite speculative area, almost philosophical area, and it's not so clear what is the reality or not. First, there are some very minor variations of the standard model that I would not call even alternative models. There are proposals of new scenarios of the CP violation or different models. There are almost 1,000 models of inflation. Some of them are more standard, others not so much. There are variations in the primordial nucleosynthesis, different number of neutrinos, for instance. Instead of 3, they assume there are 2 types of neutrinos or 4. There are different equations of state for the dark energy, different types of dark matter, etc., different process of formation of galaxies. But all of these are very minor variations. I would not consider all these small changes in the standard model, I would not consider properly alternative models. There are other proposals that are more challenging to the standard model. They affect to the fundamentals ideas of the standard model. For instance, I cannot mention everything. This is a short review because there are hundreds of ideas. I will mention some of the most representative, perhaps. One proposal is the idea that the universe is not homogeneous at large scale, at scales larger than hundreds of megaparsec. There is a proposal of a fractal cosmology. The universe is a fractal. This means that the dimension the fractal dimension is different from 3. If you take a sphere with radius r, the mass embedded in the sphere is not proportional to the r up to 3. This is what will be followed in a homogeneous universe. In a fractal universe, the d is lower than 3. And these ideas are in some way supported by the data also, according to some of the proposers of these ideas. Of course, if we have a non-homogeneous universe, Friedman metric does not work here. We have to modify cosmology in many aspects. Big Bang, the lambda CDM, assumes that the early universe is a hot state. The temperatures are very high because of the conditions of density and pressure. We have almost a singularity and then a high pressure and high density. So it is assumed to have a hot Big Bang in the standard model. That is what produced the primordial nucleosynthesis. However, there are proposals of cold Big Bang. And this is an old model that is still with some supporters. Cold Big Bang is exactly the same idea. We have the origin of the universe, we have singularity, we have expansion, but at the beginning of the universe, the temperature was 0. This modifies many aspects of cosmology nowadays. In order to explain the cosmic microwave background, you need other different ideas. In order to explain the origin of the elements, of the light elements, you don't have enough with the primordial nucleosynthesis. You need also stellar nucleosynthesis and other aspects. So the cosmology is quite different. Just to mention another example of variation. Indeed, the idea is very similar to the standard model, but is with some important major variation with respect to the Big Bang. There are, I would say, tens or hundreds of ideas related with the change of the fundamental constants of physics. Instead of assuming that the speed of light or the gravitational constant or the Planck constant or the fine structure constant are really the same everywhere in the universe and in any time, they assume that there is a variation with time or with space also. So, well, they produce, of course, different consequences for the cosmology. If the speed of light is not constant, if the gravitational constant is not really a constant, they change the laws of physics. We have different laws in the early universe, and consequently, we have a different cosmology. Even we can modify the gravitational law itself. And there are indeed a very, very wide literature proposing modified gravity laws. Here I give some representative list. All these, let me see, all these names are some alternative models of gravitation different from general relativity and Newtonian gravity. Perhaps the most popular one is this one, the MOND, which means modified in Newtonian dynamics, although there are many other considerations. MOND, the idea is very simple. They just take the Newtonian acceleration between two bodies, and they modify by a factor mu, divided by a factor of mu, that depends only on the acceleration. And this factor mu is significantly different from 1, only for very, very low acceleration. This is represented here with real data indeed. Here we can see that below 10 to minus 10 meters per square second, we have some departure from this horizontal line, which will be the expected with the Newtonian gravity. We have an excess of acceleration, which is reflected also in the rotation curve of the galaxies here. And this excess of acceleration is common for all the galaxies. There is only here one free parameter, A0, and with these free parameters, MOND can reproduce the rotation curve and other characteristics of other galaxies without dark matter. This is the point of MOND. The idea of modifying the gravity is say, okay, we need more mass, but if we preserve the standard cosmology and the standard gravity. But if we modify the gravity, we don't need the dark matter to explain rotation curves, clusters of galaxies, and other things. Well, the idea is not so simple as this. This is only for two bodies. When you represent the galaxy as a whole, you need something, a more complete theory that also to preserve the momentum, linear momentum, the angular momentum, the energy. There are more sophisticated theories. This is, for instance, called the Lagrangian theory, a quadratic Lagrangian theory, or the quasi-linear approximation. But the basic notion is this one. You take the Newtonian approach or general relativity and you modify slightly. Even there is a relativistic version of Mond called Thebes, which is an expansion of general relativity, but modifying it for small accelerations. This, of course, has also some consequences for cosmology, although they are not totally developed. There is not a Mond cosmology yet. They don't explain still not many facts. And the same thing can be said for modified gravity, F of R, Einstein ether theory. There are plenty of different gravitational theories that will have important consequences for cosmology. Even if we keep the general relativity and the standard idea in gravitation, and we keep the metric, the Friedmann-Lemaitre Robertson-Walker metric, the homogeneous and isotropic universe, there are some other possible solutions different from the lambda CDM. The lambda CDM, as I said, contains dark matter, dark energy. Lambda is the term claiming there is a dark energy. But there are other solutions depending on the assumptions. One of the most successful alternative solutions nowadays is what is called the model RH equals CT, which basically means that the ratio of the expansion of the universe is constant, is always constant. It's a straight, this black line, you can see, is a straight line, and there is a constant ratio of expansion. This is different from the standard model in which, as you may know, there is an accelerated expansion due to the dark energy. Locally, I'm going to put here, in the present time, there is more or less an agreement between the standard model, the accelerating expansion universe, which is the green line, and the black line. So there is a coincidence in the results between the RH equals CT and the other one. However, it is quite different in the early universe. Here we can see also that the predictions of the age of the universe with this model is 14.6 gigayears instead of 13.8. So there is, in some way, there is more time for the formation of galaxies at very high redshift. How can this produces this constant ratio expansion? They only need one assumption. They need general relativity, the normal metric of Friedmann-Lemaitre, and adding this condition. If you add this condition, density plus 3 pressure, what we divided by the c squared, just to have the same units, equals 0. If you add this condition, which is called also zero active mass, for the whole time of the universe, you get this model, which is quite simple. It has no free parameters, no omega lambda, no omega m, only just this condition. Just to say that Milne cosmology is a special case of this kind of RH equals CT, just assuming density equals 0. Let's put here from here. A Big Bang, lambda CDM assumes that there is a beginning of the universe, there is an expansion, and does not tell anything else. Possibly there is an end of the universe. However, there are proposals of cyclical universes, that the universe has been some way eternal. There was some universe before the Big Bang, and there will be more Big Bangs later. Some decades ago was popular the idea of the big crunch, that if we have enough matter in the universe will expand, but if you have enough matter, it will contract again, it will produce a collapse and produce a big crunch. It's the opposite. After you have the big crunch, you start, you have a restarting again, and you produce a new Big Bang, infinite cycles. Another proposal by Penrose, for instance, is the conformal cyclic cosmology that also adopts basically is a Big Bang cosmology, but assumes that once the universe evaporates in some way, even the black holes evaporate and everything is diluted, there is a rescaling factor in which the very large scales become small, and you start again a new cycle. This is represented here. This is more or less idea. It's more a mathematical idea. This has not any support, of course, but it's an alternative cosmology, I would say. Something similar is proposed by here, Tuomo Suntola, and I would like to say something about his model, although next talk will be the presentation of his model, so he will give more details. Also, Tuomo Suntola has presented a model, also a cyclical universe, also with a state of a singularity or something with high density at the beginning and expansion, although the conditions are very different from the standard model. Here, it is assumed that the space that we observe is a 3D surface of a 4D hypersphere. It's a different representation of the standard gravitational model with general relativity. And also connects the expansion, the velocity of the expansion of the universe with the speed of light. In some way, they are connected. So this changes in many aspects the rules of the game. But fundamentally, it's the same idea than before. You have an infinite series of expansion and contraction cycle. And this expansion and contraction is governed by a simple law, which is the zero energy principle, by which simply we have the kinetic energy and potential energy. Kinetic energy related with the velocity of the matter in the expansion, and the potential, the interaction between the matter itself. If we require that this to be conserved equal to zero, we have the dynamics of the universe. The idea is simple. Although, as I say, this is it has some similarities with the Big Bang, but it's quite different in the assumptions of the gravity. Even as it was remarked yesterday in some talks here, there are some reformulation of some understanding of the mass as a wave-like substance. There's a reformulation of the Planck's equation. So there are a lot of new elements that are not in the standard physics and standard cosmology, even if it has some similarities. One remarkable prediction of this model is that it assumes that there is expansion also in the local universe, also in our solar system. There is the expansion of the universe does not affect only to the galaxies, but also to the Milky Way itself and the solar system. The planets are being separated from the sun, and so on. And Tuomo will explain which are the proofs that support this. This is, I would say, a bit controversial. It's not everybody agrees these statements, no? But it's some of the proposals of this model. There are other predictions and other observations that agree more or less with the model. For instance, the rotation of stars around the Sagittarius A, which is the black hole in the center of Milky Way, is, according to the author, correctly predicted by the model. The binary star period in some cases, when the eccentricity is large. Also, the supernova magnitude redshift relation without dark energy is reproduced, the angular size test, and others. Nonetheless, as I say, it will be explained better by the author. than me. There are many pending tasks here to be developed. Still, we need to explain the nucleosynthesis, the CMB, the large-scale structure. All these are things that are developed in the standard cosmology, and here we have not so clear explanation. And also, the proposal that the speed of light can change with time, which is due to the variation of the speed of expansion, is, maybe clashes with some supporters of the special relativity and other aspects. These are some examples, because there are more, this is just a few examples, of alternative models which are some variations, major variations with respect of the idea of the Big Bang, the idea that we have a beginning, we have expansion, and so on. However, there are even alternative scenarios which are much more different. They don't resemble at all of the Big Bang. In the most extreme cases, we have the proposals of a static universe, Euclidean, with infinite space, eternal time. But I will not dedicate time to these models. They are quite exotic. As you can imagine, they have many problems. They explain the redshift of the galaxies with a direct light mechanism, so there is no expansion, as I say, and they have different predictions. There are other models very similar to the dynamic universe that use this idea of the hypersphere, that we have an extra dimension of the space, and what we are observing is only the hypersurface of this hypersphere. And if from a historical point of view, perhaps the most relevant alternative models are these two, which are quite different from the Big Bang, the steady-state cosmology and the plasma cosmology. Steady-state cosmology was proposed in 1948 by Fred Hoyle, and independently by Bondi and Gould, also in the same year, in independent publication. According to them, there is not, the universe is eternal, but there is not even a state of singularity at the beginning of the universe. The universe has always the same size. They think there is a continuous creation of matter. Rather than a creation of matter at the beginning of the universe, the galaxies separate, and in the space in between the galaxies, new matter is being created. So there is a continuous creation of matter. This was the proposal in the 40s, remember, not the present day one. So the effect is that you get what they call the perfect cosmological principle. The universe is always the same. It's homogeneous, isotropic, but it does not change with time. At any time, the universe will have the same aspect, because when the galaxies separate, new galaxies are created in the middle, so in the end, the density of the universe will be the same. Of course, this creation of the spontaneous creation of matter is just a speculation. It's a metaphysical speculation. Nobody has demonstrated this. In the 50s of the last century, steady-state cosmology was considered a cosmological model as competitive as the Big Bang. They were at the same level, and the professional physicists paid the same attention to both models. Both of them were able to explain the light elements, the existence of the helium, deuterium, lithium, with different hypotheses. Big Bang uses the primordial nucleosynthesis in the early universe. Steady state uses the stellar nucleosynthesis, assuming there was a all population of stars previous to the present generation. But the numbers were more or less in agreement with the data at those times. And as I mentioned, also the steady state assumes the expansion of the universe. So the two main facts that we knew in the 40s and the 50s was the redshift of the galaxies and the light elements were explained by both models. However, in the 60s, the situation changes. In the 60s, appeared some observations that were not in agreement with the steady state model. Particularly, it was found that at high redshift, at high distance from us, the galaxies are younger than the local universe. This was not in agreement with the steady state because they assumed that the universe has not evolution. And also, the distribution of radio sources was not in agreement with the steady state. The most important fact was the discovery, or the discovery and the interpretation in cosmological terms of the CMB, of the cosmic microwave background radiation. That was, as predicted by the Big Bang, was isotropic and has a black body radiation. There were some failures in the prediction also. The temperature was in agreement with the predictions of Gamow and collaborators. But however, they posited the existence of this cosmic microwave radiation, while the steady state cosmology has not predicted it. This motivated, especially this fact, motivated that most of the cosmologists at those times moved to the Big Bang idea, to what we call now lambda CDM, formerly the Big Bang, and they abandoned mostly the steady state. Much later, in the 90s, 93, 94, Fred Hoyle again, and with Geoff Barbish, an old collaborator, and a new one, Diane Narlikar, who was a student of Fred Hoyle, created a modification of the steady state cosmology, which was called a quasi-steady state model. The idea was very simple, just an ad hoc correction. They have added an ad hoc correction in order to justify why their model did not work in the 60s. They added some cyclical sinusoidal expansion. Instead of having here only an exponential term in the expansion, the scale factor of the universe, they added some new term with a cosine here. And due to this term, the universe has infinite cycles of expansion and contraction. Pay attention that the minimum size of the universe is never 0 here. Here we have 1. So it's different from this, these models of cyclical universe. There is no singularity. So the universe has a minimum size and a maximum size, but never reaches 0, the universe. So this is quite different from the standard CDM. Anyway, only with this modification and assuming that the creation of matter and therefore the creation of galaxies is produced in the minima of the oscillation, and only assuming this, they can explain many of the failures that they had in the 60s. For instance, that they can explain that we observe young galaxies at high redshift because they are created in the last minimum. They can also explain the distribution of radio sources, and moreover, they have introduced ad hoc, again, a way to explain the CMB. They have posited that there are some material in the intergalactic medium, they call whiskers, which is able to thermalize the stellar radiation and produce a black body shape. Not here I mentioned the thing of the radio sources and the young galaxies. Not only the black body radiation is obtained. I have some doubts about this, but this is what they tell. This is the idea. These are not my ideas. These are the ideas of Hoyle and collaborators. No? They claim they can thermalize the radiation, and also they can explain the power spectrum of the anisotropies of the CMB. And this has nothing to do with the explanation of the standard model. They use this radiation in interaction with galaxies and clusters of galaxies, and they produce this power spectrum. Totally different theory for the explanation of the CMB, but they are able to explain many things. So I think this quasi-steady state cosmology is one of the most advanced alternative theories, even nowadays. However, already in the 90s, most of the cosmologists have focused totally in the Big Bang, and they did not pay attention to this theory. So they simply ignore. They say, okay, you have a new theory, you explain everything, possibly not in the same level of perfection as the standard Lambda CDM, but you explain roughly most of the aspects. But, well, we are working in this, so we don't care. This is the reaction, no? Hoyle and collaborators later published a book, a serious book, a monography, published in Cambridge University Press, and they complain if they say, okay, why the community is not paying attention to our model now? And this is what they have published in some of the pages. No, this is our view of the conformist approach to the standard hot Big Bang cosmology. We have resisted the temptation to name some of the leading geese. This is some caricature of the some sociological facts of the cosmology. I will refer to this later. No, but I think in some aspects they are a little bit right. I recognize that, well, maybe Hoyle and collaborators, they were a little bit frustrated because they have not got the impression they wanted. But they are a little bit right. It's true that now cosmology goes in the direction of the leaders. There are a few leaders that saying, hey, let's go here, dark matter, and everybody, dark matter, dark energy, dark energy. Well, this is how it works, cosmology nowadays. Unfortunately, we are human beings. And human beings are like any other animals going in herds. Another example, just to continue with the list of alternative models, is the plasma cosmology. It was also quite relevant some years ago, and even nowadays. It was proposed by the Nobel Prize of Physics, Hannes Alfvén, and other people. Even nowadays, there are supporters like Eric Lerner and other authors. The main idea is that the main force controlling the dynamics of the universe is not gravity, but the electromagnetic forces. Of course, gravity is there. The galaxies have mass, and the gravity should be there. But they claim that the electromagnetic forces are stronger than gravitational forces, because they assume that the universe is a plasma with strong magnetic fields and everything. These people, many of them have been working in plasma physics in the laboratory on the Earth. They are used to work with plasma in some labs, and they are able to create structures in the plasma that resemble some structures in the large-scale structure of the universe. In the large scale, in the distribution of galaxies in the universe, we observe some filaments, some walls, some voids, and they say, oh, of course, this is very similar to what we see here on the Earth with in our laboratories with the plasma. So they have created some simulations and embodied simulations to reproduce this, and they say, well, we can't do it. And forget about general relativity, forget about Big Bang. We can do it just assuming that the universe is a plasma and controlled mainly by magnetic fields, electrical and magnetic fields. Even they can reproduce the formation of galaxies dominated by electromagnetic forces. In order to explain the CMB, they assume something very similar to the steady-state cosmology, which is that in the intergalactic medium there is interaction between the radiation produced by the star, the stellar radiation, and some particles. In this case, the particles are the electrons. Since we are in a plasma, there are electrons everywhere, free electrons, which have some interaction with the photons produced by the stars. This is thermalized, according to these authors. I have my doubts, but this is what they say. And they produce the CMB, they claim. And other aspects of the cosmology are also touched in this model. We have to bear in mind that this model has been produced almost 50 or 60 years ago and is still in some way alive. Very few people support it, but still there are supporters. So it has a long time to be developed. There are in this different versions of the very different cosmologies. In the old version of the plasma cosmology proposed by Alfvén, they assumed the universe was in expansion. They assumed it, although was an eternal universe. There was not a beginning, and the expansion was not due to the existence of a Big Bang and eternal expansion. There was a repulsion between matter and antimatter. This was the explanation for the expansion. Later, this idea was rejected, especially after the 90s or so, because we have evidence enough that there is no antimatter, at least in the local universe. So this idea is not working. But originally, in the 70s, they thought they could explain the expansion in a very different way. Nowadays, in the new versions, there are different models of plasma cosmology, but one of them even assumes that there is no expansion. The universe is static, simply. And everything, we see the redshift of the galaxies, is due to a different mechanism. Redshift has nothing to do with expansion. No? Anyway, I have presented here, how is the time? Yes, I have time. I have presented here a long list of models. I have to say that, of course, many of these models have problems. They are not perfect. Even Lambda CDM has problems. There are many tensions. There are many observations that are not explained. But these alternative models have even more problems. And there are many questions that should be refined. Here I mentioned some aspects. For instance, if you assume there is an infinite universe, well, you have to explain the Olbers paradox, that you don't observe infinite flux in some direction. You can assume that there is no conservation of energy or fractal universe, but you have to do something. And you have to explain the expansion or the redshift, the CMB, which is a quite important thing. In my opinion, all these alternative cosmologies do not give a good explanation of the CMB, because especially of the black body shape. Because you can produce a black body at some redshift, but when you integrate many black bodies at different redshift, the integration of many black bodies is not a black body. So they have a serious problem there, but it's not my problem. The light elements can be explained in some way, and the formation of galaxies and the large scale structure, but yeah, they are not as perfect as the standard model. So summing up, these models have problems, but possibly they can solve these problems with time. They need manpower, they need people just to work in these ideas. And also, we have to bear in mind that the Big Bang has serious problems too. The question here, and this is my point now, just to finish the talk with some slides, is that it's not only the physics that is counting here. There are some sociological factors also. It doesn't matter whether your model is good or not, whether it fits your data or not. In order to move the community and to convince the community, you need something else. And it's not only a question of physics and mathematics or philosophy. No? Narlikar, one of the creators of the steady-state cosmology, complained about this sociological effect and claimed that there is some snowball effect. The snowball effect arising from the social dynamics of research funding drove more researchers into the standard cosmology fold and contributed to the drying out of alternative ideas. This simply means that there is no money for developing alternative ideas. There is no money, you cannot get students, you cannot get telescope time, you are isolated, and even sometimes you cannot go to conference, main conference in cosmology, etc. The idea is something like this. The higher the success of a standard model, the more scientists and more money dedicated to work with it. The more money and more scientists, the more problems you can solve ad hoc. You can introduce more epicycles because you have hundreds or thousands of theoreticians, an army of theoreticians just introducing new elements to the theory in order to solve the problems. And the more problems you solve, the higher the success of the standard model. This is the cycle. This is something similar to what the sociologists call the Matthew effect. This is the sociologist Robert Merton called it Matthew effect. The Matthew comes from the name in the Bible, Gospel of St. Matthew, that you can read here. And to everyone that hath shall be given, and he shall have abundance. But from him that hath not shall be taken away even that which he hath. But this is the idea of capitalism. If you are richer, you become richer, and if you are poorer, you are even poorer. And since science has become so capitalist, the important groups in science that have a lot of money, they get even more money. This is the idea. No? And if you have nothing, you are rejected for everything. Also, metaphorically, we can compare this sociological situation with some nuclear reaction. In a nuclear chain reaction, you need a critical mass to trigger the reaction. No? What's here in cosmology the same. You need a critical mass of people and money, and when you have enough people and money for creating a cosmology, it works. If you are alone, or you are 2 or 3 people just creating a new cosmological model, forget it. You have no chance of success, even if your model is perfect. There are, of course, many heterodox cosmologies, many amateurs or some professionals that still dream of with creating a new cosmological model or just a new gravitational model or demonstrating that the general relativity was wrong, Einstein was wrong. This is the favorite idea of the amateurs is claiming, oh, I have demonstrated that Einstein was wrong. No? Well, I think they don't live in the present day times. Still, they are thinking that you can create science in your house, and most of them are like in my country. We have the character of Quixote, the famous novel of the Cervantes. And Quixote was a very good guy with high ideals, but he was not living in the present times. Times nowadays are moving in a different way. Science is not produced like in times of Einstein, that you can work in your patent office and just produce your excellent papers. You will not get any attention. This is the thing. Even if your ideas can be very good. On the other hand, we have the orthodox cosmologies, which are the majority. And the orthodox cosmologies, most of them are very good professionals, very specialized, but they are very conformist. They accept everything because this is what everybody claims. They are not interested in finding new truths. What they are interested in is in getting a new permanent position in some university or getting some big grant to have a lot of students. This is their interest. They don't care. They don't care about how the universe is. 0 minutes. Okay, yes, I finished now. Just to the last 2 slides. With this panorama, I have to be pessimistic again, like in my previous talk some days ago, about the cosmology. I think, we are dominated by, there are 2 factors, of course, the nature is there, but we have many important sociological factors to explain why some theories dominate over others. I would prefer a cosmology more plural, like what is claimed here in this paragraph by Ribeiro and Videira. In as much as no cosmological model can ever be capable of holding ultimate knowledge about the universe, then it follows that no cosmology can hold eternal truths. Then, the larger the number of cosmologies available to cosmologists, the higher the chances of we obtaining better representations of the universe. This is the last slide, this is not new among philosophers. Pluralism is common among philosophers. For instance, here we see Feyerabend saying that use alternatives only when refutations have already discredited the orthodox theory, puts the cart before the horse, and also Popper that claims that when there are no alternative theories, this is a problem for science. And that's all I have to say. Just to remind that there are many other ideas, philosophical and scientific ideas in this book, if you are interested. Thank you very much.
Thank you very much. No niin. Okay, thank you very much. We are running so short of time, so we could take one question, perhaps. So, yeah, there's the first one. Yeah.
Thank you. I was wondering why you thought the CP violation of the dark energy in Lambda CDM were ad hoc. I mean, the immediate thought is something like CP violation is empirically confirmed in the lab, and dark energy from a cosmological point of view is just a parameter in the Einstein field equations. There was never a good theoretical reason to think it had to be zero.
Well, I don't know many things about the last experiment in the lab. CP violation was introduced already the 70s or 80s, and when it was introduced, it was just an ad hoc condition, just to save the model, because there was a clear prediction in the standard model. If you have a symmetry between matter and antimatter, we should see how collision between matter and antimatter and gamma rays are what, and we have not seen. At present, possibly they have confirmed it in some way. As you correctly say, dark energy is not confirmed so far. It was also an ad hoc introduced in order to explain the supernova, also the CMB.
What's ad hoc about it? It's just a parameter in the field equations.
Yes, I totally agree. It's just a parameter, but also dark matter. Inflation is the same. It's a parameter. In my opinion, these are pure epicycles. Epicycles in the sense that, like in the geocentric theory, when your theory does not work and you say, okay, we have some data and my theory is not predicting correctly the data. Let's introduce some new parameter in order to save the theory. And the cosmologists are always trying to save the theory. They never admit that their theory may be wrong. They say, if something does not work, let's introduce something new. This is it's a constant during the last 50 years in cosmology, no?
No, absolutely not, but it will be a longer conversation.
Good, all right. Let's give an applause. All right, so next up we have Tuomo Suntola. From Physics Foundation Society, and Tuomo is an accomplished engineer and inventor in Finland and abroad, and also physicist by training and philosopher in spirit. And Tuomo is speaking about the dynamic universe.
Okay, good morning everybody, and thank Martin for the nice general presentation of alternate cosmologies and the nice presentation of dynamic universe model. So we start from the very beginning. The dynamic universe theory is a holistic depth description of universe, just like the Copernican model was the holistic description of the planetary system. In DU, our three-dimensional space is described as a three-sphere, which means the three-dimensional surface of a four-dimensional ball that enables, and that structure enables solution of the energy buildup and the dynamics of space as a zero-energy process of motion and gravitation. The basic elements of the DU theory, the three-sphere space, and the zero-energy principle are in fact well known in prior art. In his lectures on gravitation in the 60s, Richard Feynman pondered the three-sphere geometry and the energy balance of the universe in his, which is published in a book on his lectures. On page 10, he states, if we now compare the total gravitational energy to the total rest energy of the universe, lo and behold, we get the amazing result that the two energies are equal, so that the total energy of the universe is zero. Why this should be so is one of the great mysteries. And therefore, one of the important questions is physics. And still he states here that after all, what would be the use of studying physics if the mysteries were not the most important things to investigate? And further on page 164, one intriguing suggestion is that the universe has a structure analogous to that of a spherical surface. If we move in any direction on such a surface, we never meet a boundary or end, yet the surface is bounded and finite. It might be that our three-dimensional space is such a thing, a three-dimensional surface of a force sphere. The arrangement and distribution of galaxies in the world that we see would then be something analogous to that, to a distribution of spot on the spherical ball. And let's see what it means. Dynamic universe is just a dynamical solution to Feynman's great mystery. For that, we need some reinterpretations and or definitions behind the theory of relativity. In the theory of relativity, the fourth dimension is used as the time dimension. However, the line element in the fourth dimension is ds4 is equal to c times dt, which means that it's not measured in seconds, the units of time, but it's measured in meters, the unit which is the unit of length. Interpreting the fourth dimension as a metric dimension, we are not 13.8 billion years from the starting point, but any point in space is at 13.8 billion light years distance from the starting point, which is increasing at the distance which is increasing at the velocity of light. Geometrically, it means that the three-dimensional surface of a four-dimensional ball expanding at the velocity of light. In the expanding three-sphere, the rest energy of any mass m in space appears as the energy of motion due to the motion of space in the fourth dimension, the expansion. And the rest energy of the total mass is Em when we take all the mass in space is m total times c to the second. The gravitational energy of the three-sphere space can be expressed with mass equivalence at the barycenter of the system, the center which is not inside in space, but in the fourth dimension, in the center at the center of the sphere. From the zero energy balance, we can now solve the speed of expansion, the velocity of c, which we can find to be equal to plus minus square root of g gravitational constant times mass equivalence divided by R4. And that's very interesting, but it means that it can be either, it can mean that space can either be contracting or expanding. So let's start, look what happens if we let space do that, what nature allows. So the first, if we start from an infinite, almost infinite sphere, the motion is against the center, so the mass gets its velocity from its own gravitation in the system, and we get a huge energy excitation until we come to a singularity, or at least close to a singularity. And then now we release back the energy we have obtained from the gravitation, and in a way pay back the loan from gravitation which we have in our rest energy or matter. So it means that the cycle of a physical existence can be seen as started from emptiness in the past and which ends up to emptiness in the future. Whether it makes another cycle is another question. Maybe either mathematicians or philosophers may give the answer. But anyway, right now we are in the expansion phase, which means that we gradually pay back the energy debt. Compared with a standard model of cosmology, which states that everything started at once, also time was started at the same time. When the Big Bang happened, everything and the laws of nature came into force. When we switch to dynamic universe approach, then we first extend the time scale so that the time already existed before the Big Bang, and we get the contraction phase, which built up the energy of the universe, and now we are releasing it gradually back. But what is extremely important here is that we have precise expressions now as the solution of the zero energy balance. We can solve the development. Sorry, up. I was too fast now. We can solve the velocity of the expansion and also the radius in the fourth dimension, the radius of the free sphere. In fact, the comparison with the standard models is not that dramatic as we can see in this picture. So when we apply the standard model equation for the development based on the light travel distance, we can see almost a similar type of expansion. However, it strongly depends on the choice of the dark energy here. Now with dark energy equal to 0.735, the current radius matches with the H 13.8, which gives the average expansion rate equal to the present velocity of light. Let's look at the energy buildup in these two cases. In the standard model, the rest energy of matter has stayed essentially stable throughout the expansion. However, once the volume of the space has been smaller in the past, it means that the gravitational potential, the minus potential, has been far larger. So that's something that doesn't differ very much from the development in the dynamic universe calculation. But what is essential is that even today, both of the models state that today there is a zero energy balance, as stated in Richard Feynman's comment, that the amazing thing that these two energies are equal. However, in the standard model, it must be then a special case, because in the past this has not been possible if we don't accept the changing velocity of light, which is bound to the expansion in the fourth dimension. What is interesting, recent observations with James Webb Telescope tells that it looks like the development or early development of galaxies is much too fast to be explained with the energy which is available here. However, when we make the same comparison here, we can see that there's a lot of energy available in the early expansion, so that it's strongly supported by the Webb telescope observations. Let's summarize what we have found until now. So the rest energy of matter is built up in a contraction process as the energy of motion against the release of gravitational energy, not in an instant Big Bang, so that now we don't need such an assumption, but development of the energy has come from well-known interaction of potential energy and motion and potential energy. There is no matter-antimatter asymmetry. The rest energy of matter is balanced by the global gravitational energy. That's very interesting, that any mass, the rest energy of any small mass particle is balanced with the gravitational energy arising from all the other mass in space. There's no need for hypothetical inflation period. I didn't mention that in the standard model presentation, but they need some very fast early expansion in order to explain the homogeneity and the general development, the early universe. However, the inflation was assumed to be extremely small, only a very, very small fraction of a second. The zero energy balance produced a precise algebraic solution to the development of the expansion. And that's very important, because now we are able to derive the cosmological predictions without additional parameters. the turn from contraction to expansion was associated with a huge excitation of energy, which we already stated. And as a part of the zero energy balance, the velocity of light in space is linked to the velocity of space in the fourth dimension, which slows down with the expansion and is reduced close to mass centers, which we are going to look after a short while. The rate of, which is very important, is that the rate of physical processes is proportional to the speed of light. The build-up of local structures in space was extremely fast in the early expansion, as indicated by the James Webb Telescope observations. And then yesterday we have some talk about the nature of mass as the substance for the expression of energy. And as another important notion about that is that the basic form of mass is non-structured, and we can consider that the dark matter, which we know that will be needed in the overall energy balance in space, means that there must be some hidden material. And in this case, we can see that it's quite possible that we have such non-structured matter. I will shortly come to this a little bit later on. Possible, and also that's a possible explanation for the huge mass densities close to the singularity, which is certainly where the volume is too small to accept any structured particles. A possible mechanism for galaxy formation also then will be via black holes, which is also suggested by some observations in James Webb Telescope observations. Okay, let's see how relativity appears as a manifestation of the conservation of total energy. And this is what, in fact, was one of the key issues in the dynamic universe approach. So we can first notice that any mass in space has velocity c in the fourth dimension. And the rest energy or mass is the energy of motion due to the velocity in the fourth dimension, balanced by the gravitational energy rising from the mass equivalence m, or which means from the total mass of space around the free sphere. Also, it means that any velocity v in space is associated with a hidden velocity in the fourth dimension. And that's very, very important. And for getting further, it's very useful, or something that we have to do, is to reformulate perhaps the most famous equation in physics, which is the equation for rest energy E mc to the second, which should be written as C0, which is the expansion rate, and then m and c as local values of mass and local velocity of light, which also can be written as, which can be written as c times momentum p. So now we can see directly from this drawing here that the total momentum can be expressed as the orthogonal sum of the rest momentum mc and the local momentum p. And also you can notice that the total energy we then obtain has the same form as has been obtained in special relativity, but not now without any assumption tied to special relativity or the postulates behind special relativity. Further on, in a more detailed analysis, we can also find out that total momentum, the momentum in space is associated with increasing relativistic mass as also expressed in general relativity. But what the relativity theory is not disclosing, that the overall energy balance requires that at the same time, when the relativistic mass is increasing the momentum in space, the rest momentum is reduced. And this is exceedingly important now because, for example, the frequency of atomic clocks is proportional to the rest momentum of the oscillating electrons in the system. It means that instead of blaming time for the slower frequency of clocks in motion, we can see that there's a precise physical reason for that reduction. Let's see how we can conserve the energy balance when creating structures in space. So these are the length of the arrows shows the balance between the energy of gravitation and energy of motion, which is the rest energy. So what is the trick of creating motion in the space direction and at the same time maintaining the balance and conserving the energy, so that we don't have any extra energy for that. So the simple trick is to bend the local space. So now the local fourth dimension here is bended with by the tilting of the space, and we can create the velocity in space, the velocity of free fall towards the mass center as an orthogonal component of the original fourth dimension velocity, which means that the velocity in the local fourth dimension is reduced. And this also is extremely important because then the rest energy is reduced. And the same process occurs then in several steps, which also is very important in order to understand the energy structure of space. So as I mentioned already, so that here we see that now we can see that the rest energy of a mass object close to a mass center is reduced due to the reduced local velocity of light. However, such a mechanism for creating velocity in space is not available when we accelerate objects at constant gravitational potential, such as in our accelerators or anywhere else, which means that we need to add some additional substance for the energy, which can be expressed with delta M, which is the mass increase when expressing the total energy of motion. Again, the equations look exactly the same as the energy in special relativity, but now the reason is very simple, that we have brought the extra energy for creating the delta M here. And in a more detailed analysis, which I'm not going into details, which can be read in my papers and the book, DU book, we can see that the change in the velocity of light can be expressed in terms of the local gravitational factor, which now also relates the local gravitational ratio M divided by R to the global gravitation as the ratio of M double quad divided by R4. And that's also very important, that everything in the local system is related to the whole. So there are no isolated systems. And what is extremely important here is that when we come to the physical reason behind the reduction of the rest energy, rest momentum here, is that we can notice that any motion in space is central motion relative to the barycenter in the fourth dimension, which means that the central force created by motion reduces part of the gravitational energy, and that's the mechanism of reducing the rest energy, but it's exactly the work which we call the inertial work. So in fact, when we accelerated our object or our car, it means that we are working against the gravitation of the rest of the rest of space, which is exactly the Mach's principle. But now we can give a precise mathematical expression on that, and that's exactly the effect that reduces the ticking frequencies of atomic clocks in motion. Let's go further. Okay, now we can solve the rest energy containing both the factor of gravitation, which comes from the bending mechanism here, and from the motion, which comes from the mechanism here, where we are adding the extra substance for the energy buildup. And also, as we can see a little bit later on, is that from this equation we can find out that the frequency of atomic oscillators, like atomic clocks, we have exactly the same factors, the gravitational factor and the velocity factor. And this can be related to the general relativity solution, which looks mathematically a little bit different because the delta and beta factors are under the same square root. But we can find out that in Earth conditions, near space conditions, the difference between these two equations appears only in the 18th or 20th decimal, so that they are very, very close to each other in low gravitation conditions. However, this is not the case in close to black holes or very heavy gravitation. Anyway, the general picture of space looks very much the same as presented the general picture of space-time geometry of general relativity, so that every mass center creates a dent in the space in the fourth dimension, and the general picture looks very much this. But what is very much different is that instead of not being a local theory as a theory of relativity, we have now started from the whole and extended the analysis toward details. We can build a system of nested energy frames. So as a reference, we can consider homogeneous space where all mass is in principle at rest and uniformly distributed. And when we then form, let's say, first local galaxy group, the motion of the group first then reduces the rest energy. So the rest energy in homogeneous space is reduced by the gravitational factor and motion factor of the group. In the group, we have galaxies like our Milky Way. Now again, the motion of the Milky Way within the local group creates another factor to the rest energy, and we have less energy available in our Milky Way systems. And same is true when we go back to the solar system. So now the solar system is moving within the Milky Way, and we in any actions in solar system, we have again a little bit less energy available. And this is true in the next steps there. We can go down to our laboratory experiments where we have ions accelerated in an accelerator. And it means that we are any object on the Earth here, we have motion, we have shared part of our energy to the motions with the local group, with the Milky Way, with the solar system, with the rotation of the Earth, and then the local motions which we are creating in our laboratory experiments. So finally, we can now express the rest energy available locally with this equation, which states the effect of all the parent systems we are participating. So in fact, this equation contains both the gravitational effects and effects of motion on physical processes such as the ticking frequency of atomic clock. If we look at what it means in experiments made on relativity, we can find that now the system of nested energy frame explains the local state of rest. The local state of rest in local system in fact replaces the postulated relativity principle, which is one of the key postulates in our present theories. We don't need that, and we can't do that because we can see that the state of rest is not bound to the observer, but it's bound to the state where motion is obtained. And now we can find that it explains the local tests where it's the special relativity works very well in the laboratory experiments because the observer automatically is at the state of rest of the accelerator in the laboratory frame or the accelerator frame. And then when we go outside the surface of the Earth, the first time atomic clocks were taken first in airplanes and then in satellites, it was found that we can't use the reference of rest here in our laboratory reference clock, but we need a clock which is at rest relative to the Earth-centered frame, ECI frame, which is Earth-centered inertial frame, so that a ray frame not moving following the rotation of the Earth. And going further to GPS, global positioning, and then to Mars, we still need other reference clocks. But with a system of nested energy frames, we can bind all these experiments together and see how they are connected. And in fact, the way in space traveling and space experiments, the clock frequencies are. The clock rates are calculated. They exactly follow the same scheme, although the explanation behind the scheme is different in relativity theory. Let's go further. As a very important comparison is the theory of relativity is observer-oriented theory, and it's based originally on kinematics and metrics. So it means that the only parameters available for explaining the change in the clock rates is the flow of time. There is no physical reason for that, and that was the way the theory was derived. In the dynamic systems, we have a dynamic approach, which means that we are looking the effect of energy conservation, which we came to the conclusion that local gravitation and motion reduce the rest energy when we follow the zero energy principle and take care of the conservation of energy in local interactions. So it means that instead of blaming time for the different ticking frequency here, we can see that we can base our frequency on the quantum mechanical solution, which is delta E divided by Planck constant H. And as we spoke yesterday, it's so important to find out that in Planck constant we have a hidden c, which means that the clean form of this equation is mc divided by h0, which is h divided by c. And in fact, this is a very important confirmation to the effect of the need of cleaning the Planck constant. Now, also the message here is that once the frequency is directly proportional to the local velocity of light, it guarantees that whenever we measure the velocity of light with atomic clocks, we get the same result. So that's something that Professor Raimo Lehti used to call the conspiracy of the laws of nature. So that's how the nature hides the reasons of things. As a summary of the relativistic effect, universal time and distance. We have universal time or distance, which are the properties defining an understandable physical reality. People like to understand the place and the time of event. The velocity of light and the rest mass are now function of a local state of gravitation and motion, respectively. In theory of relativity, the choice was vice versa. The constant velocity of light was defined as constant and the rest mass as constant, which means that we needed time and distance as function of the state of gravitation and motion. And then this gave especially relative to the observer, which then brought some extra problems. The famous equation mc to the second must be rewritten in the form c0 times mc, which honors the effects of local motion and gravitation on m and c respectively. And now the effect of motion on the rest mass explains the Lorentz covariance of special relativity, so that we have now a physical reason why this is the case, and we don't need to blame time for that. The same is true for the change of the velocity of light. It comes from the local bending of space and explains the gravitational blue shift of general relativity. The system of nested energy frame indeed means a full replacement of the relativity principle. It explains the local state of rest and relates local to the whole. There are many consequences on that. So let's make some remarks on celestial mechanics in DU. DU explains all the basic tests of general relativity, the perihelion advanced, bending of light close to messenger, gravitational lensing, Shapiro delay, Sagnac effect, emission of gravitation related to the period degrees of binary star. By the way, Martin Lopez stated that general relativity's prediction that also circular orbits have the effect is observed. I tried to check the thing last week, also using artificial intelligence, and the answer was that for orbital circuits there is no change in the period, so that now we have to check what is the actual observational situation, but according to the artificial observations, the DU prediction was supported, and we have to check the origin of Martin Lopez observations, how they were interpreted, shall be interpreted. Also, what is very extremely important, due to the local nature of the relativity theory, local gravitational systems such as galaxies and planetary systems do not expand with the expansion of space because they need to maintain their gravitational energy. However, in the dynamic universe, we have seen that local systems are bound to the total, which means that local systems such as galaxies, the distance to the moon, and so on, expand in the same ratio as the expansion of space in general. So in fact, we have very strong observational support. Once we clean the observations from interpretations made for standing with general relativity framework. And sometimes that cleaning is not that easy, but it certainly can be done. So there are very many observations, and one very less known but important is the coral fossil and sediment layers, which let us calculate the number of days in a year for the last 1 billion years. which is very, very unique because it's not tied to any cosmology model, and we can simply calculate. But in order to get the prediction correct, we need the expansion of the space, which changes the length of the year in order to make the observation match with theory. So it's very strong support to dynamic universe. Or same is true for ancient solar eclipses and also the geological development of Earth and Mars, which means that it's now easy to understand why there has been liquid water on Mars for 3 or 4 billion years ago. In DU, celestial mechanics show stable orbits down to the critical radius of black holes, which is very, very important. And it also shows that there are slow orbits near the critical radius that maintain the mass of the black hole and doesn't know a specific singularity within the black hole. And how it's seen, I simply have plotted here the Foster and Nightingale's books, predictions for GR predictions for escape velocity here and orbital velocity. And when we approach the critical radius here, we can see that the orbital velocity here exceeds the escape velocity when we are at 3 times the Schwarzschild critical radius, which means that absolutely there are no possible orbits beyond that limit. In DU, which is based on the conservation of energy, we don't have that effect. Instead, we have very stable, nice orbits down to the critical radius, and here we can see the slow orbits, which can be estimated to be responsible for maintaining the mass of the black hole. So it's very, very difficult. My conclusion has been that the reference comes from the equivalence principle. Here, the equivalence principle means that there is similar buildup of relativistic mass in free fall and in velocity obtained at constant gravitational potential, which infringes the conservation of energy. But let's look at the predictions close to black holes. So there are some interesting observations near the Sagittarius A, the big black hole in our Milky Way center, measured orbits with period of something like 17 minutes has been observed. And when we compare that with the Schwarzschild prediction, which ends at something like 29 minutes, it doesn't match. When we have the DU prediction here, which is looks a little bit more complex, but it has a very nice match to the observation here. And also we can see here the possibilities for the slow orbits then beyond the 2 times DU critical radius. So in fact, the 2 times critical radius is exactly the Schwarzschild radius, where the number 2 clearly comes from the boundary condition of Newtonian mechanics. So an extension of Schwarzschild metric is Kerr black hole. I don't go into details, but it possibly then explains the rotation here. The comment here is that in DU perspective, the equivalence principle behind general relativity infringes the conservation of energy in free fall, and as a consequence, Schwarzschild solutions on unstable orbits near black holes, and when the orbital velocity exceeds the escape velocity, and the Newtonian boundary condition brings the number 2 in Schwarzschild. Let's see some of the cosmological consequences here. Cosmological distances get simple mathematical expressions and free of additional parameters. DU prediction for luminosity matches observed bolometric luminosities. Bolometric means the directly observed luminosities without dark energy and without converting observations to any emitter's rest frame, which is the term used for manipulating the observation before comparing them to the general relativity predictions. The DU predictions for the angular size of galaxies show Euclidean appearance in agreement with observations, which is very important, and the cosmological time dilation of GR certainly turns out to be illusory. Distance effects are faster because the energy excitation in space was much faster in the past, but they are observed dilated when they combine all the effect on the velocity of light and the expansion and so on. Okay, just as a comparison, the so-called co-moving distance, we have the prediction of general relativities here. There are parameters, the mass parameter and dark energy parameter. In dynamic universe, we have nothing like that, and we have very simple mathematical expression, sum for the light travel distance, which is the integrated tangential path of the yellow line here. So, which it's basically very much the same in general relativity and standard cosmology and dynamic universe, but you can see that the mathematical expression is far more simple here. What is derived here is the observed luminosity and volumetric magnitude, which are the observables which we can measure from distant object. Very importantly is that the standard prediction comes from Tolman's article in 1930, when as a real scientist he is very careful because he has to interpret the effects of general relativity, the Planck equation, Doppler effect, and anything else, everything was new at that time. And that's why he clearly says that evidently the prediction is like that. But the final conclusion is that one should use the co-moving distance for the aerial dilution, and also he adds both the Doppler and Planck equation. And let's say, principal problem here is that now the dilution of the power density decreases relative to the fourth power of the expansion. At the same time, the volume increases relative to the third power, so it means that we are losing some energy. In dynamic universe, the area dilution is related to the actual path of the light, and we have only one dilution due to the redshift, because the Planck equation shouldn't be considered as the intrinsic property of radiation, but the conversion. It tells the conversion of the that has occurred once, and it's no more then available for expansion. And the final result is that the predictions for magnitudes are quite different. And as stated here, there is far too much dilution, and it's solved to match with the prediction, the observed luminous and transferred to emitters redshift by a factor of 1 plus z to the second which is hidden in the co-correction. In DU, observed luminous is matched directly to the prediction. And let's see how it looks. These are the supernova predictions about 20 years ago. The standard model without dark energy, and this was the way the dark energy was introduced. And with the dark energy, the curve works fairly well. The DU prediction, when converted to the prediction to the observation, which are converted to emitters rest frame, matches exactly the same, and we can remove the first so that we can see very, very, very nice prediction. Angular diameter. So in standard cosmology, there's a very, very strange interpretation, which is based on reciprocity theorem by Effrington in 1933, which states that the apparent distance of an object shall be the same as it was when the light was emitted. And it's very strange because it means that in a very distant observations, the object should look as it were as close as it was here. In DU, we don't have anything like that. And if we compare that with observations, these are the angular size is the vertical line here, and the distance, which is measured, expressed in terms of the redshift, they are here. And we can see that the standard prediction, the dots should be between these two lines. They clearly are not there. In DU, we get Euclidean appearance, because part of that also is that the local galaxies expand in direct proportion to the expansion, and that's all those factors together. If we try to add the James Webb Telescope observations, there is something there. But now we switch to the unification and the last comments here. So one important point, which we didn't go into the detail here, but we discussed yesterday a little bit, is that solving the Planck equation from Maxwell equation for dipole antenna discloses the hidden C in Planck constant. And one important consequence is that now we can see that mass and wavelength are very closely related, and mass can be understood as a wave-like substance for the expression of energy, and it expresses energy for particles, electromagnetic radiation, and Coulomb energy equally. And you can, when you compare now the expressions written in this way, we have the wavelength, the intrinsic Planck constant and wavelength expression here, and it has a mass equivalence. It has the dimensional mass, so that we can apply the basic equation for all these expressions of energy. So it's one part of the unification. Also, the cleaning of Planck constant from the velocity of light discloses the substance, nature, or mass, allowing a unified expression of energies, and the essence of the fine structure constant, which now appears as a pure geometrical or mathematical constant without any connections to other physical constants as we are looking them today. So that it simply has a numerical value, as we all know the numerical value. Particles are described as mass wave resonators, so Compton resonators. And what is extremely interesting is that when we put a resonator into the motion, the de Broglie wave is formed as the sum of the Doppler shifted front and back wave in the resonator, so that it creates a moving mass object, creates the de Broglie wave, which is then very nice potential explanation for some quantum mechanical experiments like the double slit experiment and some others. Very important also, there are no independent objects like in the current reduction, a reductionistic approach. In DU holistic approach, any local object and energy state is linked to the rest of space, so that there's nothing independent object or particles. DU means major simplification of the theory structures. The basic postulates apply in all branches of physics. And to demonstrate that, okay, one comment, more comment here was that universal time and distance now, which we have in dynamic use, allow an understandable picture of reality, which certainly is very important. However, very important with the Aristotelian virtues, the main purpose of science is to make nature understandable, and that's what we are aiming to do. If we compare now the present theory structures and dynamic universe, we can see that there's a total house cleaning of the structures. It's quite understandable that we have historically had to make this path. there are some conclusions we have needed in dynamic universe, which certainly had not been available 100 years ago when the theory of relativity was developed. So that it's quite understandable that we have followed this path. But now when we combine everything we know today and the basic general principles such as conservation demands and other things, we can put the pieces together in a new way, which make the total picture far more simple and understandable. Now we have the predictions without extra parameters, and what's extremely important here is that we don't need any separate relativity theory. The relativity is a natural part of the physics here when we take into account the motion we have with the expanding space, and also how we are bound to the how local is bound to the rest of space. So thank you very much for your attention.
Let's see, we have really good questions here, and we have a little time, so perhaps we can use a couple of minutes for this. So first, here's let's take this one. So although the gravitational effects is instant in DU, does DU postulate that gravity needs a messenger particle, or is gravity a property of quantum fields in DU? So what is your point on, is the gravitational effect instant in DU? Is gravitational effect instant in DU?
Oh yes, it certainly is. So gravitational force means sensing the local gravitational potential or the gradient or local gravitational potential created by all the rest mass in space. And it's very clear that when we see the mass effect, we can't consider that the inertial force would be created in billions of years. It's immediate. So we sense the local potential, and local potential is created by masses, and the potential moves with the masses. It's not a question of moving energy. Potential is different thing than energy. Yes. So the answer is yes, it's instant.
Yes. Then about tests, what should I look into if I want to verify DU's predictions myself? And also about the LIGO and Event Horizon telescope, they have provided numerous extremely precise tests of general relativity. Can DU pass these tests?
What should I look into DU if I want to verify DU's predictions myself? Yeah, that's a tough question, because you have to look the literature which is available. So that I have done that verification for more than 20 years and still continue to do that. But we're happy to have help in that task. Event telescope have provided precise tests for general relativity. All the tests I have analyzed, they passes very well the DU. The big problem is that DU tests, the observations are interpreted in the DU framework. For example, there have been measurements with transporter technology, the distances between planets. And the result given is that according to this measurement, the planetary system do not expand with the expansion of space. However, when I found the publication analyzing the measurement, they have used if we look the readings of the atomic clocks, which measure the distances by measuring the light transmission time, then we get the answer that yes, the planetary system is expanding with the expansion of space. the way it was corrected was that the readings, time readings, were corrected, what they called the Einstein effect, which removed the effect of chasing clock readings within the time frame the measurements were made, so that it's extremely difficult to make fair comparisons, because we have to clean. For me, also, in order to see the corrections of the observations to emitter thrust frame, which were hidden in the core correction in the standard cosmology. Because I saw that the prediction is completely different. That where does come the difference between the bolometric and expressed observations? However, once they were found, I found that DU prediction works extremely well. It works directly to bolometric observations, which are the real observations that are made.
Yes, let's take still this question. So what is your explanation of the energy mass of photons or zero rest mass particles in motion within your cosmological model?
Yeah. Now we have to understand the nature of mass as the substance for the expression energy. So the substance is equally available in photons. And in fact, that's not a new idea, because already Poincaré, for example, saw that there's mass equivalence of electromagnetic radiation. So the simple expression for that is H0 divided by lambda. So that has the dimension of mass. That's what we call the mass of a photon. And in annihilation, the mass is the conserving quantity. So very, very simple. Okay,
all right, but we have so many questions. I have myself, I have also studied CO, so I can answer, for example, that the gravitational waves, they have been directly detected. How is this explainable DU? And DU thinks them in terms of energy waves. So energy is propagating, and that has gravitational effects. It's like a mass wave thing. All right, but thank you very much. Now you have 15 minutes for coffee breaks. Pretty good. All right, welcome back. Next up, we have Michael Grisek from Czech Academy of Sciences, Prague. And his topic is infrared measurements of the JVST suggest that our dynamic universe is spatially closed.
Okay, so thank you, Mr. Chairman, ladies and gentlemen. First of all, I would like to thank the organizers for inviting me to this beautiful city and to this very well-organized conference. And I am from the Institute of Mathematics of the Czech Academy of Sciences. And today I will tell a few words about how James Webb Space Telescope suggests that our universe is closed. There are never-ending discussions whether our universe is spherical, like that, yes, or if it is Euclidean space, flat, or if it has hyperbolic geometry, this means some pseudosphere. And recently it was found by James Webb Space Telescope that there are galaxies whose luminosities are around it is too weak, whose, say, redshift is approximately 13, and they shine too much according to the standard lambda CDM model. If the universe were flat, and we introduce the space-times lens principle, which I developed 25 years ago, that could explain why these distant galaxies shine so much. So we show that the observed flux luminosities are only some artificial optical effects of the positive curvature. And for Euclidean or hyperbolic geometry, such a large flux of luminosity seems implausible. And this suggests that the right model of our homogeneous and isotropic physical universe for each fixed time is a three-sphere. I am not able to sketch the three-sphere, but this is cross-section of such a three-sphere. And I will give you 10 examples to show that the curvature index is really 1. So, after introduction, I will introduce first the space length principle for a non-expanding three-sphere, then the space-time length principle for an expanding three-sphere. You will see that backing look in time, we also get some magnification effects, artificial magnification effects. I will present some main theorem arguments against unbounded manifolds. This means against that our universe could be modeled by Euclidean space or hyperbolic, say, pseudosphere. I will tell a few words about local Hubble expansion in the solar system and expansion of galaxies. And I will finish by final remarks concerning special theory of relativity. The main problem in modern cosmology is that there are not used proper mathematical implications. From Einstein equations, if you apply them to homogeneous manifolds, isotropic manifolds, you get the so well-known normalized Friedmann equation. And there I will introduce later the definition of these three symbols. It is exactly equal to 1. So there is a mathematics implication, no approximations. And from measurements, we get that the sum of these two parameters is almost approximately 1. And from that, cosmologists deduce that the curvature, this is last parameter, curvature is 0, that the last parameter is, and that the universe is flat, yes? This is, this implication is completely fails because, for instance, this floor is flat, but the whole, say, our Earth is rounded, yes? So from local, that something is locally flat, you cannot predict that it is globally flat. Labbé and other, and Laporte and Wang, they discovered, say, stars at such a large distances which shine very much, and they should not exist according to the standard model. So we will now, I will now show you 3 examples of 3 different magnification effects when you work on sphere. So already Karl Schwarzschild in at the beginning of 20th century conjectured that our universe can be roughly described by a huge 3-dimensional sphere in Euclidean space. So if you take away the last 2 terms, you get a circle. If you take only this W squared, you get something like that. And 3-sphere is defined in this way. This is Euclidean space, and A is radius in cosmology. Also, Albert Einstein, in his famous paper on cosmology, assumes that the universe could be modeled by the sphere S3, and it is on the last page of his famous paper. And in this way, he could avoid initial and boundary conditions for his field equations. And if A is equal to 1, we shall just suppress this lower index A. So for spherical model, Schwarzschild derived that the radius of this sphere is 1.5 multiplied by 10 to the 19th meter by using some, say, measurements of globular clusters. And I will now improve this estimate. I will find a better lower bound. And at present, we know that the mean mass density in the neighborhood of our galaxy or our cluster of galaxies is approximately 10 to minus 26 kilogram per meters, which means that in 1 cubic meter there are approximately 6 protons. It doesn't matter if there is 1 proton or 10 protons. It will have no big influence on our estimate. And moreover, by observations of James Webb, there are billion of galaxies that are currently observed in each, and each having about 10 to the 11 stars. Maybe that there is even number 2, twice to the 10 times to the 10 to the 12. And thus the total mass of the entire universe can be, if it is spherical, yes, can be estimated from below by 10 to the 12. This is here, 10 to the 11th, and here allow me to write mass of the sun. Mass of the sun is 2 times 10 to the 30. So if you multiply these numbers, you get such an estimate. And the volume of three-dimensional, of three sphere is given by this relation. And moreover, volume is mass over density. So if you put these together, mass, we substitute from here. There is 2, they are cancelled. So you will end up with such an inequality. Pi square is approximately 10. So if you divide this number by 10, you get 10 to the 78. And if you take square root, you get that the lower estimate is 10 to the 26. So you see that there is a very big difference between the number which was derived by Schwarzschild and which can be derived from the current observations. We will use this, say, inequality several times during my lecture, so please remember that this is lower estimate. So we shall now assume that the radius of this sphere is fixed. It is a fixed constant. In this definition, there was this W, but I will assume that it is equal to 0, yes, because I take some hyperplane and just cross the sphere, and I will end up with such a, say, two-dimensional or two-sphere. And we shall assume that the surface of this sphere is perfectly transparent, yes, just to introduce the main idea. So, and now assume that there are 2 galaxies of the same size and which have the same bolometric luminosity, and they are facing, they are oriented facing an observer. So we will have on surface 2 galaxies on different places, but the same size. And assume that the observer stands at the North Pole, and he will observe the 2 galaxies under the same viewing angle. In this sphere, the observed flux does not decay like with the square of the distance, like in Euclidean space, but completely differently. So please remember this picture. Yes? So I have one galaxy here. Assume, for instance, that this co-moving angle is 30 degrees, and the second galaxy here, and it is 150 degrees. Yes. But since the observer observes these two galaxies under the same angle, completely the same angle, and we assume that the universe is transparent, and photons travel along geodetics. Geodetics are main circles, yes? So the observer will see those two galaxies exactly the same, yes? And this explains why Wang and the other observed these galaxies so that they shine so much. For instance, you see that this angle is 5 times larger than that angle. But in Euclidean space, if you would have two galaxies, and one galaxy would be 5 times more away than the first galaxy, then the total luminosity would be 25 times different, yes? But here it is the same. So this is the first phenomenon which I want to emphasize. And later I will show you that the galaxy with Z equal to 13 is approximately at such an angle, yes? This means that the magnification effect is extremely large. Now another example, which tells you which is the difference between Euclidean space and sphere. So now let's again take our observer here, and let us consider some, say, tangential plane, Euclidean plane. And we have again two galaxies of the same size and same distance from the observer. This alpha, this is the viewing angle if you are in Euclidean space. And then it can be shown that this size, angular size, is dimension or diameter of this galaxy divided by the length, the distance. And in spherical case, this distance is just defined that it is A multiplied by this co-moving angle, which is indicated here. So now I will show you that in Euclidean space you get smaller viewing angle than on the sphere if the galaxies have the same size. So this is the definition of the viewing angle in Euclidean space. Now this is equal, D is equal to A times co-moving distance. Since sinus is always less or equal than, only less than this angle, then for reciprocal values you get such an inequality. And this is the definition of the viewing angle on this sphere. Here it is important to notice that if you take here two tangent, say straight lines, then this angle is equal to the angle between these two lines. So you see that in Euclidean space, you see a smaller angle than on the sphere. So this is the second effect which should be taken into the account. And here, if you look carefully, then you see that there is D over A, and here is also D over A. So there are two constants which I will cancel, and I have to only compare 1 over theta and here 1 over sinus theta. And you get such a graph. So this red line indicates the angular size, how the angular size depends on the distance. This black line, it is in Euclidean space, and here is still the blue line, which indicates how it looks like in a hyperbolic pseudosphere as H3. So these two effects, in the previous example and second example, leads to the so-called space length principle for fixed, radius. Here I would like to add some continuation to the example 1. So you can have the big galaxy, twice bigger galaxy at the angle 30, and some very small galaxy, twice smaller, near the South Pole, yes? For instance, at this angle 170. So their absolute luminosities, the ratio will be 4, yes? Because this is 2 times larger in diameter and that one is smaller. But the smaller galaxy will shine more than the upper galaxy if it is close to the South Pole. And this is just due to nonlinearity of this, function, sinus, because you have here 16, this is equal 1 over sinus phi 1. Phi 1 is 30 degrees. This is 1 over 4. So it is 16, and it is less than 1 over that. You can calculate that this smaller galaxy, if it is near the South Pole, it shines more than twice more than the upper galaxy. Yes, so this is the effect which was probably observed by James Webb Space Telescope. Even though this lower galaxy is 5 times more distant from the upper one. There is also a very big difference in, ratio between flux intensities. I show you the dependence of the angular size, but angular size square gives you the ratio between flux intensities, and it looks like that. So at the beginning, if it is very in the neighborhood of our galaxy, it is almost 1, this ratio. But if you are approximately on the equator of our universe looks like that. This is in the equator of 3 sphere, yes. So then it is approximately 2.5, the magnification, and if it is close to, for instance, pi, then it is extremely large. So now I will explain you that also, if you look back in time, that you get another magnification effect. So we will assume that our universe is homogeneous, isotropic for a fixed time. This means that I am not able to sketch you, as I told you, 3 spheres. I will sketch only these main, great circles. So here, this is observer. There is our universe at this time, and then there are the notion of our universe is not uniquely defined or not uniquely used, because there are 3 different manifolds for which we use the same term universe. Yes, so this blue manifold is just 3 sphere for fixed time. And this part is not causally connected with us, yes, because it is this instant state. And the Friedmann equation describes this blue manifold, but the observed data are from this yellow manifold. This is the so-called light cone. So you have data from completely different manifold than which you use then in Friedmann equation. And moreover, this red line, this is solution of the Friedmann equation usually, but it is not exact. It needn't be, but it is the so-called expansion function. Yes, this is the rate which depends on time, and if you solve Friedmann equation, it looks approximately like that. And this manifold is 5-dimensional, and it arises by rotation of this red curve along this time axis. And this last yellow manifold is just observable universe. And according to a famous book by Peebles, the current radius divided by at that time radius on some, for instance, on this sphere is equal to redshift plus 1. So, according to the standard cosmological model, this is the age of our universe. And concerning luminosities, in, for instance, the famous book by Weinberg, you can find that there are, this is the so-called luminosity distance for, say, 3 sphere. There is the sinus, and this is the measured flux. There is sinus square, and you see that there is some ambiguity, because if you if you are on the, say, upper part of this hemisphere, the galaxy is here, but if you are in lower part, the sinus is the same, yes, the same. So in fact, you do not know if you are above the, say, equator or below. So one should find if we are above or below, if this co-moving angle or co-moving distance is in the upper part or lower part. So I will present in a few minutes theorem which from redshift you will get the proper co-moving distance. So now concerning the magnification in time. So now this is some projection. If I take this picture and I project it from here along time axis, then I end up with such a picture. So there is Big Bang, and there is some 3 sphere, previous time, and here is our Earth. And the photon travels from some quasar on this line or curve, which I will show you that it is logarithmic spiral, very roughly. And so we must very much distinguish between at the time and actual dimensions. By angular measurements, we paradoxically see very distant objects as being larger. And now I will show you some examples. So there were many observations which detected superluminar speeds, yes? There were some quasars, and these jets were so quick that the speed of these jets exceeded up to 10 times the speed of light, yes? And this is also due to such an effect. If the quasar is too large, too long, too far away, then you get such an effect. But there are also other effects which can be taken into account. So now I will demonstrate this magnification on the cosmic microwave background. So the redshift of the cosmic microwave background is, according to this paper, Eisenstein-Bennett, more than 1,000. Here is this famous ratio from Peebles' book that Z plus 1 is 1,090. T2 is the, say, time when cosmic microwave background appeared. And from that, we see that this radius of the sphere when microwave background appeared was due to from this relation. That, and now I ask you to remember this inequality. And it is, if you do this calculation, it is only 3 megaparsecs. So, for instance, Andromeda galaxy is, I think, 0.7 megaparsecs. So it is the universe when cosmic microwave background appeared was relatively small, yes, comparable to the distance our Earth and Andromeda galaxy. And an enormous magnification was the Big Bang itself, which appeared roughly so many years ago. And although it happened probably in a minimal volume, I don't want to say in some singularity, yes, some minimal volume, because I believe that there is some, say, limit on mass density. The present position of Big Bang we see on the very large, say, two-sphere, the possibly greatest two-sphere, the so-called horizon, which extremely large radius. Yes? So this shows that looking back in time, we get artificial magnification effects. The farther we look, the corresponding sphere seems to be bigger and bigger, even though the universe was smaller and smaller. So this I will call the time-length principle. So now concerning the main theorem, which establishes the, say, relation between redshift and the comoving distance. So if you solve Friedman equation, you get such a red curve. It cannot be solved analytically, only numerically. So for these cosmological parameters, you get such a curve, and you see that from here, approximately, it is almost linear. And the blue graph is the first or absolute and linear term. This is from the Taylor expansion. And this green graph, if you add still, say, a term which contains acceleration, it is quadratic term. So you have lower and upper bound of this red graph, but it is almost a linear function. So we will assume again that the say, space curvature or is k equal to 1, and the expansion function is linear over some long interval, and the theorem is the following. So assume that S3 expands at a constant velocity v over this interval, and assume that the time derivative of the radius of this sphere is equal to v. This is the same. This is this assumption written in mathematical form. Then the trajectory of a photon towards the observer at the North Pole can be described by the logarithmic spiral in space variables with slope angle. This is the slope angle, and the co-moving distance is that one. So this is the main relation. So here is tangent. So here is phi. If the phi is 45 degrees, as it is in the case that v is equal to the speed of light, like in the previous lecture, then and that is the corresponding redshift. So this is the so here the space was small, and now we have trajectory of a photon, and this angle is very probably close to 45 degrees. And it can be symmetric, so you get such a trajectory. So this is in the book by Suntola 5 years ago, which was published. So now another example. So again, let us consider this galaxy with redshift z equals 13, which was observed by Wang. And from this relation, we find that the slope angle is 45. under this assumption, yes? And using the famous formula for the change of the, radii. So radius at that time was 14 times smaller than current radius. And according to this theorem, we get that this comoving angle or comoving distance is logarithm of 14, and this is bigger than pi over 2. This means that the galaxy with z equal to 13 is below the equator. It is below the equator in this equatorial hyperplane. And the corresponding angle, if you substitute here, it is 151. Yes, so it is exactly, or almost exactly the example which I showed you at the beginning of my lecture, introduction. And moreover, because there are other effects, as I told you, if you replace spherical surface by Euclidean space, then you get another magnification effect. So altogether, we see that the ratio between fluxes is that one, and if you substitute that it is 30. So in fact, the galaxy, astronomers in this paper were very much surprised why they see such a large luminosity of Z equal to 13, but it is only a mere optical effect. It is, they observe galaxy which shine 30 times less. Yes. Okay, so let's go further. Now I will show you why this assumption is realistic, yes. So it corresponds to the comoving angle pi over 2, and due to the corresponding redshift, Z is 3.81. So this means that if you are on the equator, then if this is true, then Z is almost 4. And we can get a lower estimate of this expansion rate V. So this is approximately this ratio. And if you substitute again, we know this, or you remember this inequality, and you substitute for, say, age of the universe, 1 year is approximately pi times 10 to the 7th second. So you get that lower expansion rate is 0.75 C. And I told you that this estimate was relatively rough, so we are almost at this. But of course, if this is not true, then the above relations can be appropriately modified. Now, example 6. So there are, it concerns collision of black holes. So these are neutron stars. There are single black holes, and there are binary black holes. And you see that there is some black hole whose mass is 150. And there is a logarithmic scale, yes, and I'm claiming that it is overestimated. In this paper, you find that the luminosity distance was 5.3 gigaparsecs, and they assume that Z is equal to 0.82. and k is equal to 0. But if k would be 1, then by the previous theorem, the corresponding comoving distance is such a number here in radians, and the ratio, flux ratio, is 1.13. So instead of 150, if the universe is spherically symmetric, you could get lower mass. But in this paper with my colleague Sommer, we present several other arguments that these masses are largely overestimated, because you see that there are observed data, but here are calculated data. So, and there is a big gap. Also, there is gap between single black holes and binary black holes. Yes, so this means that in calculation there is some hidden mistake. I think that they didn't take into account the gravitational redshift and so on. We give 5 arguments in this paper why this mass is largely overestimated. So now a few arguments against unbounded manifolds. So the sphere, hypersphere, or pseudosphere, hyperbolic pseudosphere, cannot be embedded into 4-dimensional Euclidean space like S3 sphere, yes? The Nobel Prize winner for economics, John Nash, he got also a Abel Prize for mathematics. So he derived that this space can be isometrically embedded into 7-dimensional Euclidean space. Yes, this is very deep theorem, and you see that this isometrically, this means that the distances are preserved, and it is not known whether this exponent can be reduced. So you see that the hyperbolic manifold is a very strange object, yes? The second argument is that the infinite universe for a fixed time instant would have, if the fact that if it would have at each point almost the same curvature, almost the same density, pressure, temperature, and so on arbitrarily large scales is very unlikely, because this would require an infinite speed of gravity of information. And now finally this normalized Friedmann equation. So it is of this form. There are definitions of these 3 parameters. So this is gravitational constant, mean density, Hubble constant. Hubble constant is defined by this well-known relation. This is time derivative. This is cosmological constant. This is constant. This is divided again by a square. And the density curvature parameter is defined via this relation. And from this, as I already told you, it is incorrectly deduced that the curvature is 0. Yes, and now I will show you that this parameter can be really very, very small, smaller than 1%. So let me again go back to cosmic microwave background. So from this relation that T AT2 divided by AT0 is this reverse version of Z plus 1. Here is T0, T0, and here is T2, T2, so this is nothing changed. And now you only substitute here correct numbers, and you get that at the time when cosmic microwave background appeared, then the expansion speed was 33 times larger than at now, yes? Moreover, if again I substitute from, I will take some lower bound for this value and that value. So at that time, the expansion rate was approximately 20 times speed of light, 25 times speed of light. So by the mean value theorem from differential calculus, there exists some point T3 such that the derivative is greater than 25c. And if you substitute here, you see that there is c and it is squared. So you have 625 times c squared. The c squared is cancelled here, and you end up with such a number. So this parameter for sphere S3 is positive, but non-zero. Very, very small, but non-zero. Next slide is devoted to Andreon, that the mass of some galaxy such as that was very, very, suppose that it is very big, but again, this reduction factor is approximately 1.5, so it is smaller. Pavel Kroupa investigated with his team very rapid emergence of supermassive black holes with high redshifts. The Z was 9 plus 1. In this case, this reduction factor of fluxes is 10, so perhaps the accretion disks produce 10 times less, say, flux than they assume. And finally, several arguments again, for cosmic microwave background. So there are, say, fluctuations, and the size of these fluctuations, or the most frequent size of these fluctuations, is 1, say, degree, which is so many radians. And the distance can be again estimated by this formula. And we can estimate easily these two, the product of these two terms. So this is the in radians, and if you take into account this upper bound or lower bound of this, say, radius, you end up with that. So altogether, D is estimated, the size of this fluctuation is estimated by these numbers for particular index curvatures, and the time at when microwave radiation background arise was that, but you see that the distance in hyperbolic case, this is very large. This is more than 1 million light years. Yeah? So it is not causally connected, because universe had no time or the light had no time to travel for so many years, such a long distance, also in this case. So this is another example why this, why I think that the curvature is 1 and not less than 0. So again, there is this false implication which is used, and the fact that we do not observe too many galaxies and quasars with big Z is also due to the fact that there is just near the South Pole, there is not so much space, yes? Like in Euclidean space, there will be a lot of space for these galaxies, but it is not for the sphere. A positive curvature index allows us to explain why in the early universe we observe some supermassive stars, supermassive black holes, and two large stellar black holes, supermassive velocities of jets produced by quasars, two large early galaxies, two large galaxy clusters, the size of the most frequent fluctuation in cosmic microwave background, super energetic quasars, giant gamma ray bursts, supernovae, and all these phenomena are just mere or apparent optical effects. Yes. Now a few words about local Hubble expansion. So the luminosity of the sun increases. There is orbit of our Earth, but say 4 gigayears ago, it was probably smaller. And it is interesting that if you take into account that the luminosity of sun increases approximately linearly, then to guarantee the almost constant temperature on Earth, you get that the expansion should be almost the same as the Hubble constant, yes? And we have other arguments concerning Earth that it could be so, based on paleontological data. Also, rivers on Mars, as were mentioned by Tuomo, high concentration of C2 contributed to higher surface temperature on Mars, but cannot fully explain the liquid water because of the huge decrease of luminosity. This is luminosity on Mars, and it is this is standard solar constant on Earth, but in say 400 gigayears ago, it was much smaller. It was only 75%. And since the luminosity decreases with the square, so this is the distance of Earth, this is astronomical unit, this is the distance of Mars from the Sun, it is squared, so you get that it is Mars luminosity is L, this is solar constant divided by 3. So you can assume that there we would have, for instance, not total eclipse, but 2/3 of total eclipse, yes, all the time. So this shows that Mars must have been closer to the Sun, and now the faint Young paradox, it can be explained, see again the Suntola's book, the large recession speed of the moon from the Earth can be explained by local Hubble expansion. We organized conference on local Hubble expansion this September. There are data on that. Then the paradox of large orbital angular momenta of our moon, Triton and Charon, can be explained. Slow rotation on Mercury, paradox of large recession speed of Titan from Saturn, the formation of Uranus and Neptune, long existence of rapidly moving satellites on the below stationary orbits of Uranus and Neptunes. And we have more than 10 arguments concerning our solar system, and the big argument is the long existence of life on Earth, which is described also in this book, which appeared last year in Springer, Mathematical Aspects of Paradoxes in Cosmology. And there are also, we have some arguments that galaxies expand. It was in fact measured by Christine Martinez Lombia. The observed expansion rate of the Milky Way is approximately 1 kilometer per second. And if you recalculate it to the, say, radius of our galaxy, you get that it is almost equal to the Hubble constant. Also, if the galaxies would have the same size, and if you look back, and they would have all the time the same size. This is for z equal to 2, and this is for z equal to 2, but for 4, z equal to 4, but you don't observe such a, say, picture of the universe. Yes, the galaxies, if they wouldn't increase, if they would have the same size, you don't observe such a picture of the universe. And in this paper, it is proved that there were super dense galaxies for big redshift. And finally, I have a few remarks because I'm unsatisfied with standard special theory of relativity. So it is based on 2 laws of physics, that laws of physics are the same in all inertial systems, and the speed of light is the same in all inertial systems. And there is famous Lorentz transformation. This is Lorentz factor. And just why I am not satisfied, I will show you now one counterexample. We said that this system S prime has such a velocity with respect to the fixed system, to this system. Then if you substitute to this Lorentz factor, you get that this Lorentz factor is 5/3. And now if you concern the standard clock paradox, then you fly, for instance, 4 light years away, and Adam will be 10 years old. Bob will be 3 years old here, and to avoid just infinite acceleration and decelerations, he can transmit say data about his age to Charles, and Charles found that that this trajectory took only 6 years and Adam 10 years. Yes, so this is the main say idea of this time dilation. But you can consider dual situation where here is Bob, and Bob has 5 years, but Adam flies 3 years to this point. And the situation is sketched here. Why I am not satisfied? Because in the previous, in this slide, Adam had 10 years. 10 years was on his clock. And this point is below the light cone. There is light cone, which is defined by this equation, and this line is defined by this equation. But the trajectory of Charles is somewhere here. It cannot go below light cone, yes? So this point is below light cone, so it is causally not connected with this light cone. So there is contradiction. You cannot do such a contradiction if the speed would be only 60% of the speed of light. It does not work, but 80% works. So there is a contradiction regardless of any physical experiment. Yes, you can easily recalculate that that I'm right. So thank you for your attention. Because you were shocked, perhaps. There are many theories in mathematics: theory of probability, theory of graphs, theory of matrices, theory of groups, and so on. But I didn't see any paper which would criticize such a theories. But concerning special theory of relativity, you have hundreds of papers which criticize, is special theory of relativity wrong? Here, Dingle, is special relativity wrong? In Nature, Dingle wrote a book, Science at the Crossroad. Yes, it is only about time dilation, nothing else. He wrote one book. I prepared one slide, yes, or this picture. So there are other papers, yes, you can find it on internet. So there must be something wrong, yes, without any physical experiments. This is just mathematical contradiction. Yes, this point, the end point of Adam, is not in the light cone. That's all.
Totally. Are these papers available later on?
You mean these papers?
Yes.
No, they will be published in the proceedings. This, yeah.
All right. Of course, there are different theories, and theories have different domains of applicability, and there are always problems in dealing with them.
Okay, thank you. Thank you.
All right, so let's start the afternoon session today, and it's my great pleasure to introduce Silvia De Bianchi from Università degli Studi di Milano. As I mentioned yesterday, we met in San Sebastian in October in this very nice meeting, and so I kind of recruited both David Wallace and Silvia De Bianchi from there, and we had an excellent time eating some pink chos and having a lot of discussion. So please.
Thank you very much, Paavo. Thank you very much to the organizers for the invitation. I'm very glad to be here today. Today I will touch an important issue, of course, that is in our mind. In a sense, what we're trying to do currently in both physics and philosophy is to discuss on the very foundations of our best scientific theories and overcome the present situation. And the present situation is a situation in which there is a quest for a unified theory, and it's a long-sought objective that, of course, changed throughout time. So we cannot, of course, say that today we pursue the very same program that, for example, Einstein and other people in the 20s were pursuing a program of unified field theory as they understood it. But of course, the quest for unified theory in physics is not that at all. Now, let me state very briefly what we are looking for. As you all know better than I do, the current problem that we are facing is that of incorporating gravity with the standard model, basically. So this is the major issue that radical physicists and also philosophers who work on the foundations of physics try to address. Now, the real, or better, it's not the only problem, but a real big problem concerns Kurt space-time. Because, of course, Kurt space-time, that plays a fundamental role, it's at the center of the theory of GR, leads to difficulties when it comes to giving a quantum account of the physical world. Now, the quest of a unified theory, as I said before, changed throughout the years, throughout the decades. So it's more than 100 years that we deal with this issue. And today we have some attempts that we can, broadly speaking, identify with the following list. So we have quantum gravity. That is a research program that does not contain, of course, only canonical quantization approaches, but many other families, I would say, of possible solutions. Then we have string theorists. And when we talk about string theory, we're not just addressing, or we're just not referring to one theory, but we are referring to many models that together constitute this research stream. The same holds for loop quantum gravity in the sense that it's more recent, of course, as an attempt, but we can find that there are different streams of research even within loop quantum gravity. For not to speak of the fact that loop quantum gravity has a very structured program that also addressed cosmological issues that is called loop quantum cosmology. Then we had, in the last 100 years, also proposals for the so-called theories of everything, okay? And supersymmetry. 10 years ago, everybody was doing supersymmetry. So as a young postdoc, I started my career moving, around Europe for postdocs, and everyone was so much into supersymmetry. There was great excitement also with respect to the LHC results and so on and so forth. And nowadays, we all know how supersymmetry, let's say, evolved. And there is just a small window that is left in order to think of supersymmetry as a possible unified theory. Now, the unified field theory that Einstein had in mind is very abstract, in a sense. It's a very abstract theory, and it's highly theoretical. And until today, we didn't have any evidence for it. There are also conceptual issues that emerge from it, and really the simple fact that we don't have any experimental evidence, not only for unified field theory, but in general for any for none of those programs should, at least as philosophers, let's think that we should take a step back. A step back and reflect and ask ourselves, why is that? Now, let me briefly describe the first attempts. So, as I said, Albert Einstein himself started thinking about the unified field theory and was among the most ferocious opponents. He was self-opposing his own theory in a sense. So he was very well aware of the limits of GR, and he wanted to pursue this idea of a unified field theory together with other important theoretical physicists and mathematicians, including Hermann Weyl, Eddington, and Kaluza. Since I don't think that we're having to do with giants here in these pictures, we're not having to do, with some naive people that just started thinking about this idea out of the blue. We have, however, to remember that one of these people, in particular Hermann Weyl, thought in between 1918 and 1922 that he has found a way to unify the electric potential with the gravitational potential and therefore solve the problem for the quest of a unified field theory. But it wasn't the case. He himself understood that this program was not, it was impossible to pursue this strategy, and he abandoned the program. However, not many years later, but a few years later, thanks to the great quantum revolution, or the second quantum revolution, of course, here we have to talk to historians of science in order to define in the correct way what happened and the process that happened. It's clear that Hermann Weyl in 1929 restored to this old idea that it set forth in his beautiful work, Space-Time Matter, Raumzeitmaterie, but he applied it in a completely different field. So what was going to born in 1929 were several attempts that then led Paul Dirac to solve and to start, the program on quantum field. The idea basically is the following. So Weyl had the intuition that those ideas that were not applicable to the gravitational potential of GR were rather applicable in a totally different field, in a totally different area of physics, and he used new mathematical objects in order to define his approach. He used spinors. And it was very interesting to see then that some ideas that were developed within the field of this research program were then used afterwards, after 10 years, in a completely different area, and were very successful. Now, what I want to present here to you today, it's something very intriguing. This is a letter on the right-hand side that Einstein wrote in 1950 to Pantaleo. Pantaleo was, in 1950, the head of the Italian Physical Society. And they invited Einstein to be present at the conference in 1955 for the 50 years of relativity from the 1905 paper, right? And there were many celebrations going on throughout the world in 1955 for that, and in 1950 already people were contacting Einstein in order to have him present in these events. And Einstein replied, yes, okay, I'll be there, and I will also write the preface to the volume of this conference, the forthcoming volume of this conference. And this preface is written in German and is translated in Italian only, so probably it's not in English. I mean, I don't know if you read it, but I don't think so. And it's written a few days before dying. So so he wrote this a few days before dying. So we cannot inquire more for what he had in mind when he wrote this preface, but it's of extreme interest, of course. So even if he recognizes, even in the preface, the failure of the unified field theory he had in mind, yet he talks about the problem of quantum gravity. And let's see what he says. He says that if the field is considered irreducible fundamental object of the theory of relativity, and is considered to be the fundamental concept of physical description of reality, then it's impossible to avoid the clash with particle. And why is that? Because in reality, these two things stand for two completely different ideas or theories of matter. And to quantize the field is wrong, he says. He says this very clearly here. Okay? So, quantisierte en Feldtheorie. No? So this is not the right path for him. He didn't, of course, explain extensively in this preface why it was not the case, but what he concludes that is even more intriguing is that perhaps an algebraic theory is to be sought, that new algebraic objects should be sought at some point. So if we really want to go beyond this clash, we have to go for a new theory. And this new theory is not only algebraic in nature, but does not contain an idea of spatio-temporal continuum, okay? And he concludes also with this consideration that is the step back that I was suggesting before to do, at least to us, I mean, as philosophers, because of course the physicist has to produce, has to publish, on Physical Review D, on Physical Review Letters. Sociologically, we all know how the pressure goes on the shoulders of physicists. But we philosophers have the privilege, we also have to publish, not to perish, but in a very different way, I would say. We have the freedom to take a step back when it comes to these issues and when it comes to the definition of reality and when it comes to metaphysical questions, of course, as well as to logical questions. So, in Einstein's view, GR is incomplete, but in the deepest sense. He says we are far from possessing a solid conceptual basis deriving from physics. So we cannot be sure about the limits of the theory. We do not master all the equations of the theory and the solutions of the theory, therefore the predictions of the theory. And if we don't know the limits of GR, how can we make sure that we overcome GR? And also, if we do not master the theory, it's also very arbitrary, the conceptual content that we extract from the theory, the basis that we extract from the theory. Now, let me show you why Einstein was not that wrong with this reflection. So here you see one of the atoms that during the early 50s, well, end of the 40s, beginning of the 50s, Gödel did with regard to the solution of Einstein-Fields equation. Now, it must be said that Einstein and Gödel were very close friends. They spent most of the time together at the Institute in Princeton, precisely in those years. And they spent a lot of time talking about time. One of the favorite topic of Gödel, of course. And Gödel, who was smart enough to find the solution to Einstein-Fields equations, of course, found these solutions, of course, not because he wanted to pursue a specific career in astrophysics and cosmology, of course, but because he wanted to show to Hermann Weyl, to Robertson, and other physicists of the Institute that the theory was still unknown to us, that the theory was incomplete in the deeper sense, because our knowledge of the theory is incomplete. Because we can always find solutions that can show the arbitrariness of certain other concepts, such as the concept of absolute cosmological time. This was the task that Gödel had in his mind at that time. And he succeeded. At that time. With the publication of these two papers, an example of a new type of cosmological solutions to Einstein's field equations of gravitation and rotating universe in general relativity theory. So, by the way, the first one is the one in which there appear those solutions that everyone is, in the philosophy of time, there is this conception according to which, Gödel is the one who offered the solution for time travel, but these are not physical solutions. So Gödel didn't want to show that time travel was possible. Indeed, he published the second paper in which it's clear that this is not possible. Anyway, the interesting thing, however, with respect with these toy models, one without matter, let's say, and the other one with non-homogeneous distribution of matter, is the following. These are the proofs that the theory contained solutions that were very different from those that were used in cosmology at that time, by Robertson, for example, in his first textbook on relativistic cosmology. And Gödel wanted to show that he was able to find this possibility, these hidden possibilities included within the theory, thanks to a dialogue with philosophy. In particular with Kant. He believed that for this specific purpose, Kant was very useful, even if he's not, Gödel is not at all a Kantian. And so he wrote this beautiful manuscript notes that he wanted to present for the 50 years of relativity, entitled Some Observations about the Relationship Between Theory of Relativity and Kantian Philosophy. Because contrary to the mainstream for Gödel, Einstein's relativity and Kant's philosophy were very close. And why is that? Because Gödel, differently from many others, at that time read Kant's Metaphysical Foundations of Natural Science, not just the first critique, and read especially the fourth chapter, which is the phenomenology. That is the philosophical understanding that Kant gave of Euler's equation for rigid bodies, not just of Newton's equation of motions, as usually we hear. So he said, basically, we have to look at Kant's way of talking about phenomenology. And why is that? Because Kant there denies absolute motion, absolute rest, absolute time. The only thing that he saves is absolute space, but not as a physical object, rather as an idea. Indeed, Kant wrote in this work that absolute space is therefore necessary, not as a concept of an actual object, but rather as an idea, which is to serve as a rule for considering all motion therein as relative. And all motion and rest must be reduced to absolute space if the appearance thereof is to be transformed into a determinate concept of experience. Now, why is this important? Well, because Gödel was very well aware of the fact that Euler, Lagrange, but even Kant, from the côté of the philosophy, let's say, wanted to expand Newtonian physics. So they went well beyond. I mean, Euler went beyond Newton, okay? So the physics that Kant witnessed, that Kant had in mind, was an extension or a modification of Newtonian mechanics. He could see a theory called fluid mechanics, okay? That is not certainly included in the Principia overall. Now, and Kant even had a different theory of gravity. Kant thought that gravitation, is an instantiation of the concept of central force. And that there is a more universal law from which we can derive Newton's third law of motion, for example. And this law is the law of antagonism in all community of matter through motion. So basically, there is this natural law that is universal. From this natural law, one can derive Newton's laws of motion. But since his physics is based and includes the results of Euler's equation of rigid bodies, it includes, let's say, the idea that we actually don't need to use the concept of absolute time in order to measure the relative motion of different reference frames. And since we don't have a concept of absolute motion nor a concept of absolute rest, what we really need is just an idea of absolute space. We can call it either, we can call it in many other ways, but still, this is what we need. Now, going back to Gödel. So Gödel read this work by Kant and got impressed. And said, look, in reality, we could find some solutions of Einstein's field equation that could prove that the concept of absolute cosmological time is an artifact, and that this slicing of nows is in contradiction with other accounts. So in other words, we can create just as derivation of the same theory, different toy models of the universe. And this is what he says in the first article. It says all cosmological solutions with known vanishing density of matter and at present have the common property that in a certain sense they contain an absolute time coordinate, owing to the fact that there exists a one-parametric system of three spaces everywhere orthogonal on the world lines of matter. But it says it's easily seen that the known existence of such a system of three spaces is equivalent with the rotation of matter relative to the compass of inertia. And here is where Euler's come into play, Euler's equation come into play, and also his idea that his solution is proposing with zero value cosmological terms, the solution to exhibit such a rotation. And Gödel's paper also is of fundamental importance, at least philosophically speaking, because it draws an asymmetry between space and time. So just like in Kant's metaphysical foundations, there was an asymmetry between the treatment of space and time. Gödel believes that we can also draw such an asymmetry in a relativistic framework. And he says, basically, that conceptually, what we can really define is a schema, is a universal schema. The schema of what? Of all possible motions of rigid bodies. So he's able to provide a toy model of a universe in which all possible motions of rigid bodies can be described consistently. However, the idea of absolute time should be dropped. He wrote, indeed, these movements, so the movements, the motions of rigid bodies, can be described by the world lines of all points of these bodies, and these world lines, in their turn, are described by their coincidences with or relative position to the material points of the actually existing bodies. So there is a correspondence, of course. And this schema is what may be called the objective physical geometry of the world, of which the various geometries existing for various observers are only different aspects. Now, since this is a conference about physics and reality, and since the literature generally stresses the fact that Gödel is not so trustworthy as a physicist because he insisted on the fact that time is an illusion. He went against the idea of cosmological time. Of course, within these specific solutions, there is no absolute cosmological time for sure, but there is what he calls the world time. So locally, of course, we can define time in a cosmological setting. The problem is that the literature forgets to stress that for Gödel, there is an actual, real geometrical structure that can be identified not just in relativity, but in any physical theory. In any physical theory, and that marks the signature of the progress of physics for human beings. That's very interesting, actually. And why he wanted to find this objective geometrical structure, let's say, that we can identify in any physical theory? Well, because he was one of those that were for a quest of a unified theory, of course. It stated, in the present imperfect state of physics, it can be maintained with any reasonable degree of certainty that the space-time scheme of relativity theory really describes the objective structure of the material world, perhaps is to be considered as only one step beyond the appearances and towards the things. Quantum physics, in particular, seems to indicate that physical reality is something still more different from the appearances that even the four-dimensional Einstein-Minkowski world shows, and Kaluza's fifth dimension points in the same direction. So here he discloses his sympathy for Kaluza's and Klein's proposal, but to conclude this part on Gödel, basically what I wanted to show you is that the quest for a unified theory led many physicists, so either led, as an example, Weil to find solutions that were then applied in other contexts and were very successful, or could enrich our knowledge of a theory such as relativity, and also could help us in identifying possible objective structures that could mark, that could be seen as signatures for the progress of physics. Another example that certainly inspired many of us is Sharma's paper. this Sharma's paper dated 1953 on the origin of inertia. Again, Sharma had desire for a unified theory and a unified view of the universe as a whole. And he thought that to describe the universe, we should have gone beyond relativity, of course. And he stated that the gravitational field of the moving universe, which in our theory gives rise to inertial forces, must also be derived from a tensor potential. Indeed, in this paper on the origin of inertia, Sharma shows how we cannot do that by relying on a scalar or on a vector potential, but we should pursue the search for this tensor potential. And says, I will reserve the discussion about this in the next paper. Of course, this next paper never came out, so it's incomplete. Then we have discussed here, I didn't know about the dynamic universe proposal before knowing Paavo, of course, and I think that it's an attempt again to offer a unifying view, a unifying theory, no? Now, you can agree or disagree with what the theory entails, but the point is that it's another way in which it is proposed to go beyond, not only beyond relativity, starting from relativity, like, for example, Gödel did, but it's actually it's actually a competing theory, I would say. Okay. But it's a competing theory with time and distance as universal coordinate quantities. It's a theory where the so-called objective geometrical structure can be identified. So what is this attempt telling us? Well, it's telling us that we could do something very similar to what, for example, Kant did. Okay, let's find a universal theory, a universal law. Kant called it universal law of community of all matter into motion and so on. Mach called it in a different way, and the dynamic universe found the primary law of nature in the conservation of an overall zero energy balance. You can call this fundamental law of nature as you want. It's simply a way in which you portray the relationship between whole and parts, or global and local, as you prefer, that responds to a principle that, however, is or can be different depending on other constraints of the theory. Yeah, so let me go towards the conclusion. Do we have time yet? Yeah, we have 10 minutes at least. So what happens to our communities right now is the following, I think. We are forced, so both physicists and philosophers, to think of the status of scientific theories. So we are really at the right moment, in the right place, I would say. And it's clear that many of the physics community, of course, think that the solution should come, and also some philosophers think that the solution will come from new physics or from new theories, and that the quest for a unified theory is something that will attain objectively, and so on. However, I always remember and recall that GR is incomplete in the deepest sense. So if we really want to go beyond GR, we have to master the theory. We have to know the exact limits of the theory, because otherwise we cannot be sure that we overcome it. Otherwise, it can happen that someday another Gödel come up with some solutions to Einstein-Fields equations that show that what we firmly believe with regard to the relativistic universe might be wrong, or it's still arbitrary. Okay, so the incomplete knowledge, of course, is not. So the fact that the theory is incomplete is due to the fact that our knowledge of the theory is incomplete. And then the next question is, but are there complete theories? Because this is a big issue, I think. Of course, to a certain extent, yes. There are theories that we can define as being complete, of course, not in Gödel's sense, but of course, a complete scientific theory of the whole reality would be something very strange, If we look back at the history of human beings, and if we really want just to limit ourselves to the history of modern science, please do indicate to me a complete theory of the whole reality. And the real question, in my view, for a philosopher is to ask why question. So why is that? And my suspect is that there is a structural incompleteness of scientific theories. I'm not the first one in saying that, of course, but I would like to say more more about the reasons why is that. First reason, there can be more than two reasons. It's at least two reasons. The first is that the language of our physical theories is mathematics. Mathematics is evolving. We created and constructed new objects throughout the history. Think about fluxions, think about tensors, think about spinors, think about spin networks, if you like loop quantum gravity and things like that. Think about this. So we create mathematical structures that can be used to create a new arrangement or a rearrangement of physical principles, and can shape also new intuitions that physicists can have, and then can be used to systematize and to increase the capacity of the theories to be applied. And the second reason why we don't find a complete theory of the reality, of the whole reality, is that, or holistic theories so easily, is that the physical content of our theory is applied. So we cannot think of science without engineering, without technology, without the fact that there is, science is done by human beings, and with groups of by groups of human beings organized in society. And it's clear that the theories are, if you like, even modified by the fact that we apply physics. So the progress in our knowledge of reality, it's clear that depends also on the knowledge that we derive from physical theory and their description of the world. But it's also true that we also modify these theories, and for example, by testing them, we can also have some hints to new phenomena, and inevitably we have to include this aspect if we want to talk about progress in physics. The scientific theories are externally driven, in a sense, because I always ask myself, what is Prussia didn't want to invest so much in building up engineering, so in building up new infrastructures and so on by involving the Berlin Academy of Sciences. Probably Euler could have not written the fluid mechanics. So science is externally driven. There's no doubt about it. It was so even in the past. Even for the big geniuses that we think were, just sitting on the desk writing alone equations. Well, they were writing alone equations, of course, but they were working to realize ideas that were in mind of kings. So, to conclude, there is a structural incompleteness, in my view, that surrounds scientific theories, both because there is an internal factor, let's say, because it relies on mathematics, and mathematics is able to produce new objects, and since we enter into contact with, so we are in touch, actually, with a dynamic reality that can show us new phenomena that apparently we cannot explain due to the fact that our theories are incomplete, then these new mathematical objects can be accompanying this new intuition, and together with other factors that include even technological development, lead to a new theory that can show us, if you like, a new geometric structure of reality, to say it a la Gödel. However, I tried to show you also the fact that the quest for a unified theory is important, is an important goal that we have to pursue anyway, not only because we produce toy models of the universe through this, which is something that human beings did for millennia. Well, not, of course, with the current mathematical objects, with more primitive ones, but still. And the second point is this reveals that the quest for a unified theory looks like a sort of regulative ideal. So it is as if we can use it in order to mark a progress in our understanding of reality that cannot be complete, okay, but still we can approximate this completeness. So let me conclude with a slogan. Incompleteness, of course, is not wrong, it's an opportunity. And I really hope that we have time for the discussion right now. Thank you.
Thank you. Why isn't there a sort of more mundane answer to why have we never come up with the theory of everything, which is just something like, it's really hard, and at least until extremely recently, we very clearly didn't have the pieces. I mean, if we tried to come up with a theory of everything prior to the 1970s, we clearly would not have got a successful one, because there was a ton of particle physics we didn't know. And if we tried to come up with a theory of everything in the 90s, we'd have left out various things we now know about cosmology. So even assuming there isn't another empirical discovery yet to come, which strikes me as implausible, we've only had like 20 years or so. Give us a chance.
Yeah, no, I mean, indeed, I said that there are at least two reasons. I mean, we can, of course, either substitute one of the two with your observation or add this to the list. I mean, I didn't want to exclude other possibility for the reason why there is no complete theory of everything, basically. It's true that you can tell me, okay, but there is no theory because it's hard. I'm not sure that it's just this. Also because we didn't have, as I said, we didn't have I mean, we had a large part of a scientific community, including people like Einstein, Gödel, Weil, that worked on this. We also had very good mathematicians and physicists in the second half of the 20th century working on it. I think that if we really want to pursue, so let's assume that there can be a new theory, okay, that overcomes the present impasse. How could this be? So let's put it in this way. What is, to put it in Gödelian terms, what is the geometric structure, okay, that is objective and objectively can be used to describe everything there is? Because this is the point.
Well, if I knew that, I would not be in this conference. So
yeah, but no. But the interesting thing, exactly, the interesting thing is there a mathematical object that can do? I mean, Bauman and colleagues, the Universe Plus project that you mentioned, this is what they want to do. So they want to create new geometrical objects that do not rely on spatio-temporal continuum, which is actually what Einstein suggested before dying. And they wanted to apply to all interactions and also at the cosmological scale. So they want to create a theory of everything based basically on this new this positive geometry. I don't know if whether they succeed, but this could be perhaps the only way, in a sense.
Yeah, and I guess just to follow up briefly, I guess my concern is something like this. I mean, in the 1950s, we had a massive zoo of particles and no real idea. Oh, yeah. In the 1950s, we had a massive zoo of particles and no real idea how to unify them. And you can imagine asking the question like, why can't we come up with a unified theory of all forms of matter, all forms of terrestrial matter? And you can imagine thinking about whether there were blocks of principle to that. But of course, it turns out there weren't any blocks of principle. It was just a difficult problem, and it was more or less solved by Weinberg and Salam in the 70s. And then conversely, if you want to ask, like, why didn't Newton come up with a theory of everything? It's kind of obvious. I mean, no matter what a genius Newton was, the empirical situation he was in didn't give him anything like the resource, the data to allow him to do that. And it's also, it's also the case that Einstein in the 50s didn't have anything like the amount of data necessary to do that. And maybe now into 2024 we don't have anything like the amount of data to do it. Who knows? But you don't need a transcendental reason to see why Einstein didn't come up with a theory of everything. There's just sort of ordinary scientific data reasons. He wasn't going to do that any more than he could come up with a theory of neutron stars. He was lacking core scientific discovery.
I'm not sure that it's just the lack of data that determined the fate of unified field theory and other attempts. But we can discuss it more later. Sure. Thank you so much, David, for the question.
Yeah, thank you very much for your very clear and interesting presentation. But I believe that there's much more to say about the cooperation between physics and philosophy. And it's true that theory construction in physics relies a lot on mathematics, but that's because of the very strong influence of the empirist philosophy of science. And there still seems to be some sort of old-fashioned philosophical assumptions in contemporary practices in physics, which have been rejected in philosophy 50 years ago or something like that. But that's
precisely? Which statements that I did seem to
No, well, it was not what you said. It was not what you said. But I'm just thinking about the strong influence that seems to be relevant, or sort of operationalist sort of view of concept formation. And that I think that's something that should be discussed in conferences like this quite a lot. But then empiricist is not the only philosophy of science, and one relevant alternative is the Aristotelian or the neo-Aristotelian philosophy of science, which aims to combine, I think, exactly what you were sort of tending towards, sort of metaphysical reflection and empirical knowledge, and not only sort of scientific observations. So actually the ancient Aristotelian epistemological starting point is a very wide notion of what kind of knowledge to use in sort of theory formation. And this, I was trying to sort of say something about this, how the Aristotelian approach is the underlying approach in the DU approach. And I think that has been a very, very strong impetus in creating that theory. So what would you like to say about these comments? Thank you.
Thank you. Well, about the first point, so about the role of mathematics in physics, I tend to consider very much what Weil suggested in philosophy of mathematics, natural science. I'm not talking about philosophy of mathematics too course, so I'm not talking about number theory, I'm not talking about debates that regards even idealizations, for example. I'm talking really about the use of mathematics within physics and the way in which we construct our scientific theories thanks to mathematics. And in this sense, I fully agree with Weil. I'm really in line with this idea that there is symbolic construction, that we as human beings, we use mathematics to build up scientific theories by performing a symbolic construction. Construction, of course, can mean many different things. Still, it's not in contradiction eventually with those who might want to give just an operational definition of mathematical entities in the physical theories, but at least it's a position that also wants to investigate the origin of the mathematics that we use within our theories. And I'm not sure that an Aristotelian position can make it, but maybe that I'm completely wrong with that, in the sense that it's clear that the scientific theory can talk about relations among quantities, for example, and physical systems, can talk about amplitudes, can talk about invariance, and so on and so forth. But there is a sense in which there is a correspondence at some point, like it is with geodesics in GR, you know. At some point, there must be physical content that is expressed mathematically in the theory, and the theory has the great capacity of anticipating the empirical content of future observations, precisely because there is such a correspondence. But this correspondence is constructed, is the result of a construction, in my view. Yeah, well, is it Aristotle? I don't think so.
We have 3 more minutes, so short question and short answer.
Thanks. So I wanted to question to what extent it's essential that we focus on incompleteness of a theory in order to make progress. So specifically, we're suggesting that in order to get a quantum theory of gravity, we may have to sort of really focus on the ways in which GR is incomplete. And by incomplete, you mean that we don't fully understand the space of solutions to the equations. So so let me just give an example of why I don't quite fully believe that. So
no, not only that. There is also information that is wrapped in tensors and that should be made explicit, of course.
Yeah, okay. But crucially, the point is you want to more fully understand the mathematical structure of the theory in a certain way. So the example that I have in mind is something like, if you look at if you're interested in understanding fluid flow, and you look at Navier-Stokes equations, now obviously it's a open problem, a Millennium Prize problem to fully show that it doesn't have finite time blow up. Nevertheless, if you are actually interested in modeling water, then the relevant thing to focus on is molecular structure and maybe build some molecular dynamical simulations and so on and so on. And the sort of mathematically interesting structure of the Navier-Stokes is not that relevant to some extent. Like, obviously it's relevant to some extent, but it's not what I would focus on. So I'm just curious, and it seems to me it's the same is true for quantum gravity. Instead of focusing on the mathematical structure of GR as much, we should try to see where the theory breaks down, right?
But you, as I said, you don't have a unique approach to quantum gravity. So you are asking to me about quantum gravity as a program in general, I guess, not about just canonical quantization and so on, right? I mean, you have different. I mean, you can overcome the difficulty. You can use mean field theory as JFT does. You can. I mean, you can overcome the incompleteness of our knowledge of GR. But the results can lead you to something very similar to what, for example, is obtained by emergent gravity scenarios. And, you know, I mean, I don't know if I'm answering your question first before going on, but I think that this is a very important point to underline. So even if our knowledge of GR is incomplete yet, we can mimic, so to speak, we can mimic its, so the behavior well, the behavior of the theory, I would say, or components of the theory, and try to show that, I don't know, for example, GR is a sort of hydrodynamic limit of more fundamental theory of quantum gravity, okay? We generally do that by employing techniques, by employing techniques that can give us certain results that are not extremely precise for the time being, of course, and that do not tell us much about the theory. So it leaves, you know, a lot of implications of the theory of GR. I mean, of the theory that are, you know, underexplored or implicit. Yeah, I mean, is it useful? What do we have to do with that? Plus, it can rely on, you know, some converging results, perhaps with analog gravity. The problem there is that in order to obtain a correspondence with, I don't know, for example, sonic black holes and astrophysical black holes, what you do is insert by hand the metric in the matrix, or the Lorentzian metric in the matrix, so it's just a dog. What's that? Is it physics?
Okay, so we move on, but thank you very much for this. And our next speaker will be Avril Sturman from the University of Helsinki. And Avril is a very key person behind this conference and also in this project we have at the University of Helsinki, Theories and Reality in Physics and Beyond. So, and he will be talking about evaluation of theories and methodologies, relativistic physics versus the dynamic universe.
All right, thanks, and thanks for everybody, previous speakers. I will continue from what Tuomo already told and others. There's a lot of common elements also with the presentation of Mr. Lopez. So we are evaluating not just theories, but also methodologies. The abbreviations here, so RP is relativistic physics, comprises the special and general theories of relativity, SR and GR-based standard cosmology, abbreviated as SC, and DU, the dynamic universe. All right. So we'll first ask which criteria should be used in the comparative evaluation of relativistic physics and DU, and then I'll go through case examples where the selected criteria are the basis of the evaluation. All right. I start from the classical ideal that was respected in the era of classical physics. Their scientific theory ought to provide causal or dynamic, they're interchangeable. I'll use the dynamic term. So it ought to provide dynamic explanations that elucidate force or energy transactions, make the explained phenomena understandable, and yield novel predictions. Then relativistic physics became a paradigm in the first quarter of the 20th century, and physicists who conceptualize reality through its lens often regarded as the only alternative, either true or not true, but still correct. And consequently, whenever relativistic physics has not provided a classically virtuous explanation, it has not been falsified, but instead the criteria have been modified to conform to relativistic physics. This means that what are its problems from the classical aspect, or based on the classical criteria, have been, so to speak, concealed by legitimizing them. That is, by changing the criteria so that the problems have ceased to be problems. And practically, this instrumentalist criteria make relativistic physics unfalsifiable. First, predictions are prioritized over explanations that make nature understandable. And the classical notion of understanding a phenomenon by understanding its explanation is demoted into understanding how a theory is applied in producing a prediction of the phenomenon. But this is not just in relativistic physics, but it's typical in modern theoretical physics or mathematical physics. And then anomalous data may even be disregarded, or if it's taken seriously, then it may be accommodated with the help of additional hypotheses. And we'll see examples, so many examples that we can call it an orderly methodology. And simultaneously, rival theories are eliminated in the peer review because they are inconsistent with relativistic physics. Like this is, you can read this from many sources. So here's an analogy. I took this Marvel's, the gauntlet, infinity gauntlet. So imagine that you have like unlimited power. You can basically do whatever you want. Like you can disregard anomalous data, or if you take it seriously, then you can accommodate the data with applying additional hypotheses, and then what you do, you can just produce a mathematical prediction. You don't have to produce an understandable explanation. And then when somebody suggests that, okay, I have this beautiful theory that gives a dynamic explanation, then it's no. It's no, because it's incompatible with the relativistic physics. And all this has been notified in Philosophy of Science. Here's Thomas Kuhn on the left and Feyerabend on the center. Feyerabend says, theories shape and order facts and can be rechanged, come what may, and that the invention of alternatives to the view at the center of discussion constitutes an essential part of the empirical method. Conversely, the fact that the consistency condition eliminates alternatives shows it to be in disagreement not only with scientific practice, but with empiricism as well. And Kuhn points out that the decision to reject one paradigm is always the decision to accept another, and the judgment leading to that decision involves the comparison of both paradigms with nature and with each other. This is what we are doing here. But Feyerabend could not say that which criteria we should apply in the evaluation, because he was against any stable criteria. And here we may turn again towards Kuhn. His 1977 article is a good starting point into the investigation of theoretical virtues. And evaluation criteria and virtues, they're interchangeable. And after Kuhn, we've seen finer distinctions of virtues, their interrelations and organizations. So it's an active active field of research. What's the best representation of theoretical virtues? And if you look at the philosopher's criteria, they are much closer to classical than relativistic criteria. And I represent here the classical criteria as a taxonomy of ethical, explanatory, and pragmatic virtues of a theory T. There's not an exhaustive classification. I just show some ethical, explanatory, and pragmatic virtues that are respected by DU and violated by relativistic physics. Okay, first, ethical virtues. And I'll just list the examples here, and after I've listed them, then you can select the examples we'll look in detail. So first, data ought not to be modified. That's quite acceptable, I think. But if you look at the standard cosmologist conversion to emitter's rest frame in the K correction, that looks like modification of anomalous data. And I'm sure it was like done with no harms, no bad feelings, and innocently. But if we look at it from the DU aspect, which does not require the conversion, then it looks like modification. And anomalous data ought to be acknowledged. It's quite not generally acknowledged that general relativity textbook approximations yield Mercury's escape. Nobody really, the general public doesn't know that versus DU predicts a stable orbit for Mercury. And general relativity does not provide a plausible explanation for the evolution of the number of days in a year versus DU does. Also looks like unacknowledged anomalous data. And finally, applied formulas ought to be derived from the basic structure of the theory or considered as its primitive commitments. But in the Scout D experiment, we can see accommodation in terms of a non-derived formula. We can look at that later. Okay, then the most important, always considered most important virtues, the explanatory virtues. They can be formulated in terms of evidential scope. It's a range of phenomena for which the theory's predictions are sufficiently accurate and its explanations are sufficiently deep. That the scope is determined by the theory's accuracy, depth, and consistency. So if it's consistent, no problems, but if it's inconsistent, then the scope is decreased. So those three defining properties or virtues of scope: predictive accuracy, how well its predictions match the empirical data; and explanatory depth, how well it describes the causal factors of the phenomenon to be explained; and consistency, its internal and external consistency. And here, we don't consider that one or two rival theories, they don't have to be consistent mutually, of course, because they're rivals. We just want to select the best theory based on other virtues. And another central explanatory virtue, or I consider it explanatory, is the theory's ontological weight. That's determined by the number and quantity of hypotheses in the theory's basic structure and its auxiliaries. So that's total ontological weight. So we can consider explanatory virtues in terms of two central virtues: evidential scope and ontological weight. And next step is to define unifying power or relative simplicity as a ratio of scope and weight. So a theory's unifying power is great when it explains several heterogeneous phenomena with a simple and internally and externally consistent basic structure and a small number and quantity of auxiliary hypotheses. And now we can look at the examples. We evaluate them in terms of the ratio of scope and weight. So whenever there's problem, we can see it either as a decrease of scope or the increase of weight. Now, in the context of the given examples, du scope is at least as great as that of relativistic physics. When their basic structures are considered to have an equal weight, then du has a smaller total ontological weight because relativistic physics deploys various additional hypotheses in accommodating phenomena, for which du gives novel predictions. And these are either used novel, that means that they were not applied in the construction of du, or temporally novel, means that the phenomena were not known when du was constructed at the end of the 90s. Yep. Therefore, in the light of these examples, du has a greater unifying power, greater ratio of scope and weight. So let's look at the examples. So first, baryogenesis for explaining the matter-antimatter asymmetry. That's an additional hypothesis in standard cosmology, not required in du. Then the inflation hypothesis and theories for explaining the resulting graceful exit problem, also not required by du. And dark energy for explaining supernova perceptions, also not required by du. And it's a great thing in this evaluation that we don't have to decide if they are, we call them ad hoc hypotheses or just hypotheses. They are still hypotheses. And if another theory does not require them, then that's like a sign of them being ad hoc. Then we have the incorrect prediction for the angular size of galaxies that either decreases scope or, I believe on Monday, Mr. Lopez told that there's some explanation applying some hypothesis, additional hypothesis in the standard cosmology. And then there's this unrecognized data modification in the K correction. We could count that as an increase of the weight of standard cosmology. And then we have lots of different hypotheses for defending the hypothesis that local systems do not expand. We have lots of data about the evolution of the Earth-Sun distance, evolution of the Earth-Moon distance, and the faint young-sun paradox. And for all these phenomena, we have additional hypotheses for explaining them away in the context of general relativity. So there's really no there's no lack of hypotheses. Then rotational velocity of a black hole is applied as an additional hypothesis in Kerr metric. This is a good one, the Schwarzschild metric does not work, so we just make space rotate. So then it works. And then another interesting feature is that there is no consensual dynamic explanation for atomic clocks in general relativity. There's just the basic metric explanation and two competing causal explanations. So 3 rival explanations. And in du, there is one single dynamic explanation. Okay? And by definition, general relativity is incoherent, does not cohere with quantum mechanics because there's contradiction between them in the vicinity of black holes, and because there's no explanatory relations, so that you cannot derive any postulate of one theory from the other. That's why there's these additional frameworks for unifying them. They also increase the total weight if you count like general relativity plus quantum mechanics. So these additional frameworks increase their weight. And in du, there's no contradiction, no known contradiction, and at least some explanatory relations, so there's no need for additional frameworks for unifying them. And then there's the unrecognized problem of the Mercurius escape, decreases the scope of general relativity, and that's explained in DU. And the evolution of the number of days also should decrease the scope of general relativity. And again, if it's 1 day explained by some hypothesis, then it increases its weight. So here we have I think here's enough additional hypothesis so we can say that it is just integral part of the methodology, relativistic methodology. If you cannot explain something, you just invent a hypothesis, and that's it. And then some pragmatic virtues. So, theory is pragmatically virtuous if it's labor-saving, convenient for human action, like easy to use, test, and to understand. For instance, syntactic simplicity is considered a pragmatic virtue here. Understandability. Okay, the basic metric explanation that changes time and distance locally of special general relativity makes nature non-understandable. We can't understand like a totality whose parts exist at different times. Whereas DU yields a picture of reality that is in principle understandable. At least it's not especially non-understandable. And as a single theory is easier to learn and to understand than 3 theories. And in DU there's definite geometry of space, whereas standard cosmology starts from space-time geometry and then 3 alternatives on top of that. So we ask, what does the geometry of universe now at one point of time look like? There's no answer. And DU provides unique solutions and predictions derived from the basic dynamic explanation, whereas in relativistic physics there has been difficulties in choosing between special and general relativity. That's shown by the twin paradox, SCOUT-D, or gravity probe, a experiment, and the Haffel-Keating experiment. There's been toggling that uncertainty that which theory should be applied or what is the rest frame. And we can also point out like the relativity principle that states that there is no privileged reference frame. It's upheld in SR, but in the Schwarzschild solution, there is always a single mass center. So it looks like there is a privileged reference frame. Looks like a contradiction to me, but I'm sure that nobody would admit this. And then there are different metrics for different situations, like Schwarzschild and Kerr metric. Schwarzschild metric does not work, then we can take Kerr metric. In DU, there's only one metric, or one dynamic solution. That's the nested energy frame solution. So, summary before we go into the detailed examples. So if you want to accept the classical criteria, then DU is a better explanation of the given examples. Of course, there's a limited number of examples. Then I must ask that how long can a group of physicists just keep on rejecting rival theories just because they contradict the pet theory and keep on teaching the ideology students that it has no alternatives? That's not true. For me, this looks like social injustice. So there's a lot of space for philosophers, even social philosophers, to talk about this. And as long-term remedies, I suggest that we should teach philosophy of science in all education programs, starting from kindergarten and continuing through physics education, and even make it a rule in science policy that journals should explicate sustainable evaluation criteria and also follow them. So we could talk a lot about this, but for now, I'll just thank you, and then you can select any detailed example you wish to look at. Thanks.
Thank you very much. And we have plenty of time for discussion and selection. We have David here. Yes.
Thank you. I mean, there's a lot I could criticize in what you say about GR, but maybe it would be more productive for communication just to engage with this question about how the peer review process works in physics journals for alternative theories. I don't think the account you're giving is accurate of that. I mean, one of the consequences of being a philosopher of physics who's physics trained is that I fairly frequently get asked to referee for physics journals. And I'm very often sent alternative theories that propose radical transformations of extant physics. And I don't think my refereeing of them is particularly unusual in form. And I reject dozens of these theories. But I've never rejected one of those theories on the grounds that it's incompatible with our existing theories. I mean, it might be productive just to read out briefly an example report of this kind. This is pretty short and sweet. This paper attempts to build a discrete theory which unifies quantum electrodynamics, QED, and classical general relativity, GR. The author eschews the normal strategy of looking for a mathematical formalism which reduces to these theories in appropriate limits or regimes, pointing out correctly as far as it goes that all that is scientifically required is for the empirical predictions of those theories to be reproduced. However, there are literally thousands of empirical tests of QED or its various limits, and a great many tests of GR. The author's project requires either the monumental task of going through the experimental data and showing case by case that their theory conforms to experiment, or more plausibly proving that their theory is empirically adequate to QED and GR in the very wide range of conditions in which the latter theories have been tested. The current paper does not even begin to carry out this task. However, if one proposes a replacement for a very well-confirmed physical theory, it is obligatory to prove its consistency with the experimental data. Since that is not done, the paper is not publishable. And that is the standard way it goes, I think. The reason these theories are run with is because they make thousands of predictions, many to extremely high accuracy, and those predictions are confirmed. The uniform experience I have, and the uniform experience every physicist I talk to has, is that the supposed alternatives submitted do not understand the empirical situation, gesture in the direction of the occasional half-understood experiment from decades ago, and have very little understanding even of the fact that there is a mass of quantitative data to reproduce, let alone attempt to reduce it. I'm not at all familiar with the particular theory you're discussing, and for all I know, it lacks all of these vices, but that is the general form by which alternative physics gets rejected. And I think that is fine. That is good science.
Of course, yes. You have to take into account the other side too, as you notified. Like, okay, suppose that you get an alternative theory that's 100 to 200 pages. Like, how many weeks or days does it take to properly evaluate it? That's a big problem. But then also, if we take Tuomo, it's like developed pretty well and has, like, as these examples show and many more, that is pretty good in many ways. But it's still not even evaluated. And I read this from Emilio Pannarella's editorial article that, okay, and also from Martin Lopez's books, and a lot of other sources also tell that practically you see deviation from the standard theory in the title or in the abstract, so it's just rejected. Well, maybe you are an exception. Well, there are lots of people who have like other experiences. Maybe you've been lucky.
This is just a comment on this discussion that I think that the situation that Avril discusses is actually much more common than one could think. And so since I also work in alternatives, but in Mond, so we've been doing experiments, submitting like a paper or an abstract, where instead of saying like Mond does this, like, so you do that, and then you get rejected. And then you replace that Mond with Lambda CDM, and then you get accepted. And this is really, Stacey McGaugh has been talking, like people have been talking about for a long time. So I think that there is a problem that there is a lot of crap. Like there is a lot of bad like alternatives developed by amateur like people who just think that they can like just do everything they want. And because there is so much of it, you lose really good things in this mess. Because you immediately like have this stance that, well, someone comes to me like, I don't know, undergraduate, and says like, oh, Einstein is wrong. I have now a theory of quantum gravity, like much better than all of you. And because of this, you have the attitude towards everything else. I think that this affects very much. And I have no doubt that there are a lot of like people who have very honest like peer review process for physics alternatives like you do. But I also know from the examples with dark matter that this is not the case for cosmology in many, many situations. And even now, I am like indirectly involved in the process with Nature Astronomy, who do not want to even consider the objection because it is not consistent with the standard, like, you know, with the standard view. So I think that it's there and should be kind of talked. But
yeah, so I don't think Mond is analogous to the kind of nonsense papers that get rejected all the time. And I don't think Mond's reception has been analogous. I mean, Mond was being taken pretty seriously by very serious astrophysicists in the 1990s. Mond papers were being published in perfectly serious journals. We can have a conversation, you know, that Mond is currently regarded rather badly by the scientific community in something like the way the steady-state cosmologies were regarded as badly. Again, that was serious science, recognized as serious science at the time. It's moved away. There's a conversation to have about whether science is too conformist, about whether the attitude, there should be more pluralism at the level of theories like Mond or fractal cosmologies or things. These are really different. Mond understands the scope of people working on Mond understand the scope and sweep of the data and they engage with it. I mean, we can disagree about how well they deal with it, but they're informed and responding to the need to do the empirical and observational reproduction work in a way that is not true for the kind of nonsense that I end up rejecting all the time, and that every other physicist I know has to.
Yeah, and by the way, obviously the peer review system is not perfect, so there's a lot of space to develop, like, a good question, what is a perfect peer review system?
Yeah, no, I wouldn't ever wish to claim peer review is perfect.
Okay, my name is Esa-Matti Parkko. I would like to first thank for the presenter for the nice presentation, and I would like to have, if you could take this Merkur's escape, and if you could check that, what is the situation with Einstein's theory? Thank you.
All right. So, it's very well known that the explanation for the missing arc seconds was among Einstein's central goals in the construction of general relativity, and it's an important early victory. But according to Suuntola, these three textbook approximations that are listed there entail Mercury's escape from its orbit. They explain its perihelion shift, but they contain a cumulative term that then in hundreds of thousands of years they entail its escape. Now, we discussed this with one GR professional who said that this must be surely only as approximations. Of course, you can always say that, but why is there different approximation in each book, and where is the correct approximation? Where is it derived from? And Mr. Krycek, in his new book, they indicate that due to its mathematical complexity, no exact GR solution is available, but only approximations can be given.
Only so long I can be bothered to iterate this. It is a provable result for central body motion in the Schwarzschild solution that you won't have escape. There are conserved quantities.
Maybe Tuomo has some comment on that.
Well, when I presented the problem with Mercury orbit, it's generally denied. In fact, it's exactly the same effect which I showed in my presentation, which cosmologists accept, which shows that in Schwarzschild solution, stable orbits are possible only for orbital radius higher than 3 times the critical radius.
Sure, but that's falling into the black hole. That's not escaping to infinity.
Yeah, and yes, but the same tendency starts from the very also in low gravity situation. In close to a black hole, it takes one cycle only, or a few cycles if you go a little bit further away. But we need millions of cycles to make the same effect. But they are exactly the same equations. Yeah, nobody admits it, but that's simple mathematics.
Yeah, but here is like okay, Tuomo admits that there is an escape, and Mr. Wallace does not believe it. So, how can we decide who's correct?
Do you want me to prove it on the black hole?
Orbital velocity approaches the escape velocity gradually, and it exceeds at 3 times the critical rate. Very simple.
Indeed, a very interesting debate here. I like to hear the different opinions. I try to agree more the position there, but I'm not going to make a major comment. Just a minor question about the K correction you mentioned several times. K correction is not an option in the correction of data. It's not something like you introduce in order to explain better the data. It's something that you need to introduce. It's just due to the effect of the redshift of the galaxies. When you observe a galaxy invisible at high redshift, you are observing it at ultraviolet at rest. So you need to make this correction. It's just a technical correction, nothing to do with cosmological theories or something like that. So it's with any cosmological theory should introduce the K correction. This is independent of the cosmology, is what I mean.
Oh. So, according to Tuomo, the K correction consists of filter mismatch correction and the conversion to emitter's rest frame. So, at least in DU, it's not needed. The conversion to emitter's rest frame is not needed.
But it's just the fact you are observing not the galaxy in the same wavelength. It is shifted to the left, so it's compulsory to introduce it with any cosmological theory.
Well, it's not needed in DU. Well, it's like okay, you have standard cosmology, there you need it. Then you have another theory DU, you don't need it. So, if you look at it from the DU aspect, it looks different. And so who's right? I don't know. I'm just comparing theories like you. I'm just saying that from the aspect of another theory, things look very different.
I'm trying to follow the discussion with some difficulty, so this comment may be irrelevant, I don't know. But if I was trying to work out, for example, whether Mercury might eventually, his orbit might become unstable and leave the solar system, I wouldn't do the calculation as a two-body calculation. I'd have to do it as a n-body calculation. And likely the you know, if Mercury does become unstable, it's because it'll interact in some way with Venus's orbit or something like that. Now, I'm not aware that any calculation like that's been ever done in the context of a GR calculation. It's just too complicated. So I don't quite see how one can make any comment at all about the relevance of GR for such a calculation. So maybe I'm missing something here, but I'm struggling to understand what the point is. So, am I making myself clear or not?
So you just said that you don't see the problem. Where does the problem come from?
I'm saying the problem with stability, if I wanted to calculate the stability of an orbit, I'd have to do it in an n-body environment where I take into account the fact that, you know, there's Venus, the Earth, maybe Jupiter, I don't know. And all of these things will affect whether or not Mercury becomes unstable.
And the claim being made is that the two-body orbit is already unstable.
Okay.
Exactly.
Well, I don't have any special comment for that. Do you want to comment, Tuomo, that about the further comments that?
I wrote 2 papers on this subject, and the problem is that the gravity center of the solar system moves every day more than 1,000 kilometers, yes? But this perihelion shift is only 96 kilometers per year, yes? So it is absolutely ill-conditioned problem, yes? If you compare these 2 quantities, and we have many other things. Moreover, Einstein in the derivation did a, say, numerical mistake, yes? It is in my book, there is a theorem, and it shows that there is a numerical mistake when he calculated some elliptic integral.
Okay, may I make one more comment on this orbit problem? I tested the Schwarzschild solution in the way that I removed the increase also of relativistic mass, which shouldn't be there according to the DU perspective. When I did that, the orbit became stable down to the critical radius. So that, as I explained in my presentation, my analysis of the problem comes from the conservation of energy. When we make acceleration at constant gravitational potential, we need to bring extra energy into the system. When we do that in free fall, it's a conversion between gravitational energy and the energy of motion when we don't have the extra mass increase there. So that was my analysis. But it's good to remember that nature is what it is, and it's not at all dependent how we describe it. If we are happier with using changing time and distances and on kinematic basis, we are free to do that if we are happier with that. If we are happier with the dynamic solution, which explains the reasons for the changes, then we are happier with that. Free choice. It's more philosophy than physics. Thanks.
Wasn't it so that you suggested in Helsinki Physics Department as a student work to calculate it? And the answer was, well, there's no problem because obviously Mercury stays on its orbit.
It's interesting that it was easy to demonstrate the stability for the orbits when I made this correction.
But I'd like to see the approximation that is derived from Schwarzschild metric without any additional hypothesis and sustained stable order. I'd like to see, when I see it, I believe it.
It's in every textbook.
Well, obviously not in these textbooks.
It is in the textbook.
There's at least 3 textbooks.
Phrase, it's in any textbook, essentially. It's in the standard source, it's in Wald, it's in Mosler-Thorne and Wheeler, it's in... It's a standard framework. You've got a central force problem, you've got a conserved angular momentum, you've got a conserved energy. Integrate out the conserved angular momentum and you have a radial problem with a potential function. It has a shape. The energy is conserved. The particle has to move in radial coordinates on that shape. There is a 200 scale. It can go in because there's a pit in the potential, so that it can get, if it's on the near side of the angular momentum potential, it can fall into a singularity. But provided it's between the angular momentum potential and infinity, provided its overall energy is below zero, which is actually true for these orbits, it will have to stay there forever. It's just a central force.
Well, let's continue the discussion. I'm sure either you or Tuomo, only one of you is correct.
Anyway, this is the sort of, in a way, I think this is also the sort of discussion we need for our project. We need some, things where you focus on which things to clarify and maybe some change. But let's thank Gabriel very much for
Okay, so welcome to this final longer plenary talk of the afternoon. We have Karen Croucher from University of Oslo, and she will talk about quantum gravity.
Okay, thanks. Great. So yes, I'm interested in asking the question of why do we want a theory of quantum gravity? So we have this problem of quantum gravity where physicists are searching for this new theory. We call it quantum gravity, and it's supposed to be a new theory of fundamental physics. And as we just heard from Sylvia, they've been looking for it for a long time. And normally, when physicists are looking for a new theory, it's because of some observed anomaly, something that we've seen in the universe that doesn't accord with the theories, or the theories are predicting something that we don't observe in nature. So some examples, of course, were the experiments that motivated the development of quantum mechanics, black body radiation, the photoelectric effect, and also the development of special relativity, famously motivated by asymmetries in Maxwell's laws that are not observed in nature. But in the case of quantum gravity, we don't have this. So we have general relativity, we have quantum field theory, and they work very well. They're not leading to any observed anomalies that we think motivate the need for a new fundamental theory. So instead, it seems like we're being motivated by some sort of conceptual dissatisfaction, philosophical concerns, and theoretical problems. And it's these that I want to start examining more closely. So we don't have observed anomalies, we don't have a theory, and it seems like we don't really know what the theory should be like and what it's supposed to do. Instead, what we have is this plurality of different approaches towards finding quantum gravity, but they're all doing really different things. You know, they have different starting points, different aims, different motivations, different theoretical frameworks. So kind of what is it that they have in common here? They're adopting different criteria of success in a way. So what is quantum gravity? What's kind of this minimal definition that kind of, we can classify these approaches as quantum gravity. And I would say it's whatever theory satisfies some set of principles and constraints that we take to actually define the theory. So my idea is to try and step back a bit and to kind of look at these. So what are the motivations for seeking this theory in the first place? And can these be framed as constraints in order to define the theory? And then maybe we can frame these as principles and then philosophically assess these. So this is kind of the general project that I'm starting. And the idea is that, you know, later we can use these sets of principles to classify and evaluate the different approaches to quantum gravity. So for this talk, I'm mainly focusing on the motivations for the theory. So why we're looking for the theory in the first place. So I'll start by saying a bit about what I mean by motivations, what are constraints,
and other things we have called desiderata. And then I'll describe this primary motivation for quantum gravity, which I take to be kind of the minimal characterization of the theory. And there's two different ways we can approach this or look at it. I'll call the standard perspective versus this new framework perspective. And then at the end, I'll talk a bit about other motivations for quantum gravity and how they relate to this primary motivation. So, motivations. So, as I said, it's really why we're looking for this theory in the first place. And that's what I mean by motivation, kind of the starting point. And it's sort of a descriptive project at this stage where I'm looking at all the cited motivations, so everything that people are citing as a reason for seeking this new theory. But also kind of looking for other potential ones that haven't been cited. And then the more kind of prescriptive, evaluative stage of this project, I'll say, is actually looking into these. Are they actually well motivated? What are they coming from? What are the philosophical underpinnings of these different motivations? Are they necessary? Should they be used as constraints? And if we're taking them as constraints, what are their consequences? Especially when we're combining them with other principles involved. So here we can distinguish between internal motivations and external motivations. I'll say internal motivations, these are reasons for treating our current theories as not fundamental. So reasons for thinking that these theories are in need of replacement at some kind of more fundamental level of description. So these are, I guess, problems within our current theories taken as they stand separately. So, for instance, I think two of the big ones are in general relativity, this problem of space-time singularities. Many people point this out as saying, you know, GR has within it the seeds of its own destruction because it's featuring these singularities and motivating the need for a new theory. Another one is in quantum mechanics, the measurement problem. Many people take this, well, maybe not so many, as a motivation for seeking a more fundamental theory that would explain quantum mechanics. So not just an interpretation of quantum mechanics, but a new theory that would be more fundamental and that would kind of explain or solve this measurement problem, or at least be without it. Okay, so those are the internal motivations. The external motivations, they can come about kind of just from anywhere else than within the current theories taken as they currently stand. So I think a big one is this desire for a single coherent description of the world, goals of unification, as we heard, and it also includes any kind of puzzles, problems, or striking theoretical results that come about already from attempts to combine GR and quantum field theory. So in a sense, these ones are kind of already kind of secondary motivations because they're already coming about from trying to combine these theories and doing so in different ways and coming up with different results. But still, I think they do signal the need for a new theory, and they also offer invaluable hints as to what this theory could be like. Okay, so I'll say in accordance with this primary motivation, which I'll introduce. So those are the motivations. We also have constraints. So some of these motivations can be taken as constraints on the theory. So I call these criteria of theory acceptance. So this means that we just would not accept a theory of quantum gravity if it doesn't satisfy these principles. So yeah, they definitely need to satisfy these ones. They're kind of the defining features of the new theory. But there are also additional constraints that the theory must satisfy in order that it be accepted as a theory of quantum gravity that aren't directly related to the motivations for seeking it in the first place. So constraints that are not motivations. Some of these include, for instance, constraints coming from our current theories within the domains where we know they're successful. So the idea is that the new theory should not violate these in the domains where we know they hold. And for instance, symmetry principles, thinking about like Lorentz invariance, which was discussed a bit yesterday, it shouldn't, the new theory shouldn't violate Lorentz invariance in the domains where we know Lorentz invariance holds, right? It might violate it at the more fundamental scale, but at the level where we know it holds, it shouldn't violate it there. Another big constraint on quantum gravity is, or on any new theory of physics, is that it needs to actually explain the success of our current theories in the regimes where we know they're successful. So our theories work very well, and the new one should kind of explain how it is they work so well, given that they're not fundamental. And this is related to the idea of the generalized correspondence principle, or the idea of limiting reduction in physics, so that the new theory should reduce to the older ones in some appropriate limit is the usual idea, or it should approximate the old theories in the regimes where we know they're successful. And yeah, these are big constraints on the theory of quantum gravity, of course. And finally, we have empirical constraints. And here I think we have three different categories. The first are empirical results that are not explained in our current theories. So big ones I have in mind are dark energy and dark matter. These haven't been taken as motivating quantum gravity, but it could. Perhaps quantum gravity could solve these problems. Another class are, of course, the empirical results that are explained by our current theories. And again, this could be done through that idea of generalized correspondence, as mentioned, if we show that the older theories were kind of limiting cases of the newer one, then it's like a shortcut to recovering all of these empirical results. And finally, we have future discoveries, so maybe new empirical constraints. And here I have in mind results from quantum gravity phenomenology, astrophysical results, cosmological results, but also perhaps some novel experiments. There are these proposed tabletop experiments of quantum gravity using Planck-sized masses. So these are potential future tests. So these are all constraints we can use on quantum gravity, but not directly motivating the need for the new theory. Nevertheless, they are constraints in that, ideally, the new theory we're expecting wouldn't be accepted if it doesn't meet these criteria. So also note that constraints can also form part of the definition of the new theory. And I think especially those coming from the motivations for it. So those are the motivations, those are constraints. We also have this other desiderata, or nice things that the theory could do for us. So these are features of the theory that are not necessary as constraints, so we could still accept the theory even if it doesn't have these nice features. And they're not taken to define the theory. But yeah, they would be cool things to have. Things like unification, things like UV completeness, or explanation of particular theoretical problems. So maybe they serve as motivations for the theory, meaning that we're kind of putting them in, we're actively looking for these features. Or it might just be that we've developed the theory for other reasons,
and then it turns out to have these extra nice features as sort of unexpected bonuses. So they could then be used as means of non-empirical confirmation. Have in mind the work of Richard David here. So serving to increase credence in the theory, reasons for thinking it's on the right track. And alternatively, they could be used as indicators of pursuit worthiness. So reasons to pursue this research program could lead to interesting results in the future, or at least give us interesting problems to work on. So those are kind of the other features that we could have. All right, I'll now turn to what I call the primary motivation for quantum gravity. So I was thinking, like, what is the minimal characterization of quantum gravity? Something that maybe all the approaches could agree on. And I would say something like this, that we're searching for this new theory of fundamental physics. First, that describes the domains where both GR and quantum field theory are thought to be necessary, and which somehow combines or takes into account the lessons of both of these theories. So I would say that this primary motivation is really based on this desire for external consistency. External meaning between these two theories, not within a single theory. So we want this single coherent picture of the world. And currently these two frameworks do have, they're saying conflicting things about the world, and they're both supposed to be universal frameworks applying everywhere. So we kind of know already that they can't both be correct everywhere. So I'll say a bit more about these aspects of the primary motivation that I mentioned, because it's quite vague, as I've stated it, and I'm kind of probably not going to clarify it too much. Maybe you can help me with this. But I think these highlighted aspects are what needs more precise definition here. So what do we mean to say that this theory describes the world? What are the domains where it's expected to apply? And what does it mean that it somehow combines or takes into account the lessons of both of these theories? So I'll say a little bit more of each of these. So starting with the domains. As I said, GR, quantum theory, they're both supposed to be universal frameworks. And also, we have a theory that does combine both of them. We can call it low-energy quantum gravity, following David. So basically, it's semi-classical gravity or quantum field theory, treating the fluctuations using the background field method and evaluating GR via path integral formulation of quantum field theory. All well and good, except it breaks down at high energy, or thought to break down at high energy, around the Planck scale. And this breakdown we might think of as being a symptom of the inconsistencies between these two frameworks, meaning that maybe this low energy quantum gravity as a theory itself is internally inconsistent at high energy scales, or non-predictive there. But again, as David will emphasize, this doesn't mean that the theory isn't useful. And it might not actually indicate that the theory isn't self-consistent. But regardless of all this, at least we can see that the domains of full quantum gravity, or quantum gravity proper, will have to kind of apply at the Planck scale where this theory isn't being predictive. So this new theory, quantum gravity, should apply at the Planck scale. It doesn't necessarily have to be UV complete, but it needs to be a bit better than what we've got. It needs to kind of describe more. And of course, the other domains where we're wanting this theory is black holes, cosmological singularities, and early universe cosmology. So these are the domains of quantum gravity. what does it mean that quantum gravity should describe these domains? Well, ideally, we want the theory to give predictions that are tested and not falsified. We have a hard task at the moment, so perhaps more minimally, we could require that the theory give predictions that are physically reasonable when applied in these domains, or at least that it's formally predictive here. Yeah, and I think here the empirical constraints, including those correspondence relations I mentioned, can help give us kind of hints of this. But again, I think, as I said, there's a bit, needs a bit more definition of what exactly we mean by physical reasonable predictions here. So it's a bit vague still. How can we actually assess these predictions and know that it's actually describing these domains? Finally, the third part is thinking about this combines or takes into account the lessons of both theories. I think there are different ways of satisfying this condition, but two that I think are particularly necessary. And here I'm following Ashtekar. This quote here I think is quite revealing. He says, "Everything in our past experience tells us that the two descriptions of nature we currently use must be approximations, special cases which arise as suitable limits of a single universal theory. That theory must be based on a synthesis of the basic principles of general relativity and quantum mechanics. This would be the quantum theory of gravity that we are seeking." So here I think we can isolate the two conditions. First, the new theory should recover both of our old theories in their respective domains of applicability. And secondly, the new theory needs to somehow combine the principles of both theories. So combine, and he talks about synthesis of principles here. I think we don't need an actual synthesis of principles, meaning that we've somehow taken old principles and turned them into some new, more unified principle. I think it's also enough that the new theory features one or more principles from our current theories. So call this idea of principle correspondence, when the new theory and the older theories share some principles in common. And I think the two main contenders here are, well, the principal correspondence with general relativity is background independence, which is taken very strongly in quantum gravity. And for quantum mechanics, this principle of quantization seems to be the dominant one that's being used. Okay, so now I think there are kind of two different views on this aspect of taking into account. So we can take this new framework perspective, which is kind of motivated by this idea here. The two descriptions of nature must be approximations or special cases which arise as suitable limits. So here the idea is that we need to recover both general relativity and quantum theory. And this is, again, motivated by another Ashtekar paper, where they say general relativity and quantum theory should be understood as distinct bodies of universal rules. And this means that the quantization of gravity is essentially different from quantizing the electromagnetic field, related to this idea of background independence, of course, and the problems that Sylvia was mentioning. So on this new framework perspective, we can say, I should clarify, Ashtekar doesn't use this terminology, and he's actually quite ambiguous between the two. So I don't mean to attribute this to him. I've come up with the framework idea myself, but just kind of inspired by his writings, I would say. From this viewpoint, then, the problem is to obtain a new body of rules which suitably encompasses the essential features of those of quantum mechanics and general relativity. So we need a new theory, a new framework, basically. And the motivations for seeking this kind of new framework Again, might be the measurement problem in quantum mechanics. So it's not that we kind of want, like a quantization of gravity in the same way as the electromagnetic field. We want a new theory that's kind of beyond quantum is the idea. And one recent proposal along these lines is from Oppenheim, Jonathan Oppenheim, who's put forward this post-quantum classical gravity, which modifies both general relativity and quantum theory. He's also being motivated by problems with semi-classical gravity and what he perceives as inadequacies with the current responses to black hole information loss. Let's see. I have one little slide on this, but I don't have much to say about it beyond this, I should say. So this post-quantum classical gravity, it's a theory where it shows we can consistently couple a classical space-time with quantum fields. And as I've said, it requires modifying both the theories. So that's the new framework perspective. It's in contrast with the standard perspective, which is the one that most approaches to quantum gravity take. So, the mainstream view, which is to treat quantum theory as fundamental. And on this view, you don't need to kind of recover quantum theory because you're not actually really radically modifying it. So on this view, you're taking this motivation, you're treating quantum theory as universal, and that is like a fundamental principle of physics, being inspired by Lowell and collaborators, saying the physical world at the fundamental level is governed by quantum laws, and the classical picture is only an approximation valid at sufficiently low energies and on sufficiently large scales. Another sentiment that you hear a lot, especially from Rovelli, quantum mechanics says that all dynamical fields should be quantized. GR says that space-time is dynamical field, so we need to quantize. So this is quite the standard perspective in contrast to this new framework perspective, which is supposed to go kind of beyond the quantum. So that's a summary of the two views there. And can show that there's more specific ways of satisfying this criteria of taking into account both our theories. Butterfield and Isham, in their very programmatic paper, they show that there's 4 different ways to approach quantum gravity. The first, to quantize GR. Second is to treat GR as a low energy limit of a quantization of a different classical theory, or GR as a low energy limit of a quantization of a theory that's not a classical theory. Or we start ab initio with a radically new theory. So here, using my classification, we can see that the first 2 represent the standard perspective, where we're using a quantization. And this last one represents the new framework perspective, where we're not taking quantization. And the third option here, I think I've written this wrong, low energy limit of a theory that is not a quantization of classical theory. I think just ignore that. It's like double quantization here. This third one could be either could represent either perspective, depending whether or not it's being formulated in the framework of quantum mechanics as we're currently understanding it. Okay, and as I said, the dominant approach by far is this first one, where quantum gravity is supposed to be a quantum theory. It's supposed to be one in which gravity is quantized. There's also a third perspective on this, which we might call the 3 pillars approach, and it's becoming increasingly significant now. suggests that quantum gravity is not just about combining these 2 pillars of fundamental physics, but 3 pillars of fundamental physics, so including thermodynamics or statistical mechanics. And of course, this is being quite motivated and implications being revealed through study of black hole thermodynamics, theoretical results there. And some examples of approaches which are along these lines are kind of the Jacobson, showing the Einstein field equations can be derived from the proportionality of entropy in black hole horizon area, together with the first law of thermodynamics, and also emergent gravity approaches. So these treat space-time as an effective thermodynamic entity. Importantly, this means that if we quantize space-time, we're not getting at the fundamental micro degrees of freedom. What you're getting is something analogous to phonons. So some approaches along these lines from Padmanabhan and Verlinde, of course, presenting arguments for treating gravity as emergent in these ways. Okay, and to finish, I'll just talk about some of the other motivations for quantum gravity. Yeah, so I was making this map last night. I'm not sure if the arrows are, which way they're pointing. So we have the primary motivation, and I think it's being motivated by these inconsistencies between general relativity and quantum field theory. So that's going into the primary motivation. And then we can see that unification is one way of satisfying the primary motivation, and then we could look at, and unification might be itself a motivation for quantum gravity, but then the idea is that for all of these, we need to look at them separately and start to evaluate them as motivations. Are they necessary as constraints? Why are we using these as motivations? What are they going to do for us? Are they philosophically sound? And start to evaluate them more closely. So unification, you can think of quantization, again, as a means of fulfilling the primary motivation. Also might be a way of getting at a unification because you're bringing in gravity to the quantum framework. We've got the singularities that I mentioned, so not just the space-time singularities of GR, but also divergences in quantum field theory. Not many take this as motivation for quantum gravity, but some do. But regardless, at least for the space-time singularities, the idea is that these could be resolved through quantization. So that's the link there. And yeah, I probably won't go through all these, but you can start to see how we might map them out. These ones on the side, I think, are also kind of motivating this primary motivation, saying that the solution to these problems will come from having a theory that satisfies this primary motivation, as I suggested. Okay, so to conclude, I'll just go over again the summary. The idea, as I said, is to examine the motivations for quantum gravity to better understand the theory being sought. And I hope this talk is kind of more of a motivation, especially for younger researchers to come in and start looking at these problems. The idea, I think, is to start to evaluate whether these are well motivated if we treat them as principles, and to start to understand the consequences for the theory. I've suggested that the primary motivation is kind of the minimal definition of quantum gravity, and that we need to look at this a bit more. And yeah, I think I haven't really argued for one perspective over the other, but I think it's a good question to think about this new framework perspective. Maybe it's a way forward as well. And finally, this is being based on a manuscript. I just got back from the reviewers, so I'll fix it up again. And this will come out through Cambridge Elements. So thank you.
Right, thank you very much. And we have time for discussion here, so I can take time and bring back.
Thanks, Karen, that was great. So this is like a minor modification to your starting observation. I mean, I agree with you that clearly most of the motivation is coming from conceptual theoretical issues, and we don't have anything like the evidential situation we had for quantum mechanics. We don't have no empirical evidential situation. I mean, we don't have zero evidential problem. I mean, we don't have a good theory for early universe cosmology. You know, we have we don't really have any ability to predict the theory earlier than that, and there are plenty of moving parts in the very early bit of lambda CDM, particularly the inflation stuff, and there's plenty of space to think that a quantum theory of gravity would let us understand the early bits of that well. And, you know, there are things that are a little anomalous. The cosmological constant problem's a bit weird, the hierarchy problem's a bit weird. You never know about dark matter. And we're not in a situation, we're in a very comfortable fundamental physics situation compared to the 1900s, but it's not like there aren't the odd anomaly that might turn out to be trouble as well. And we're not without some empirical domain where having the theory would actually be helpful.
Yeah, that's a good point. Wait, is this? It's not very loud. Yeah. So you saw in the. What? Can I go back to the map? No, it doesn't show up again. But yeah, those ones were listed on the side about the hierarchy problem and the.
Yeah, no, you've got it in that slide.
But you're right. I should highlight that they're actually empirical problems. Thanks. Yeah.
Thank you. So in terms of criteria of acceptance of a quantum theory of gravity, I just wanted to, I mean, obviously, you know this and this is important, but I just wanted to sort of emphasize that new empirical predictions that can at least in principle be tested are probably a pretty significant criteria of acceptance, and that's often the grounds on which string theory is criticized for not providing novel quantitative predictions of quantities that we can actually, at least in principle, measure. And so even if you find something that unifies and quantizes and resolves the singularity, but somehow doesn't provide any novel quantitative predictions, that would be a huge problem for that theory, I would imagine.
Yeah, okay, yeah, that's a really good point. Like, I haven't talked about how we would weight these different constraints, right? I've just said they're all constraints. I didn't actually even think about that, how we would put the emphasis on some rather than the other. Even though they're all kind of necessary, maybe some are more strongly held or something like this. The empirical ones, do you think, would be trumping everything else in a way?
Thanks for the talk. I was just wondering the unexpected connections between, let's say, the holographic principle and condensed matter physics. It's almost revolutionized some aspects of condensed matter physics. Would that be, what kind of motivation would that be?
Yeah,
it's unexpected benefit.
Yeah, it's an unexpected benefit. I would say this one. So I think that's along the lines of the pursuit worthiness I mentioned. I'm not sure if that is a means of confirmation. Some people might, but I think it's definitely a theoretical problem, which means that we should be pursuing it. We should be looking into it more. It's giving us hints and interesting stuff to work on, for sure.
So just a thought about your setup. Are we having some unified set of lessons from both quantum mechanics and gravity, or that might modify both, or are we quantizing a dynamical field inside the quantum framework? I mean, one thought there is that if there's some reason why gravity is fundamentally different and it just won't yield to normal quantization processes, most of the arguments for thinking that wouldn't show up just at the Planck length. They'd be general cases. So a lot of those are things I think that will yield to empirical evidence within the next 10 to 20 years. I mean, as you know, I already think we've got quite a bit of evidence for the low energy quantum gravity framework, but the thing we conspicuously don't have evidence for is superpositions of gravitational fields in the coherent regime where you don't have to appeal to Everett. And conversely, if those experimental results come in and they go the way I think most people, certainly me, expect them to go, at that point I think the motivation for supposing that kind of the linear framework of quantum mechanics breaks down at the Planck length, obviously you couldn't rule it out logically, but it will become much less motivated, I think.
Yeah, I can see that. And I'm not really sure what to say about it. I think you're certainly right, like many of these arguments, I mean, at the levels where we can test, we think that it's not going to be shown through kind of philosophical argument, it's through these experimental tests. But you're saying, yeah, they might go one way, but it's not going to tell us about kind of more fundamental stuff.
I suppose
but from those we can kind of
I mean, it might have
lose the motivation for
exactly. I mean, I think if somebody wanted to say, look, maybe quantum gravity will force us to give up core principles of quantum mechanics as well as what some people see as core principles of gravity, it would, again, and you never say never, but it's not obvious what the motivation to think that would be if it only occurs at Planckian scales. I mean that won't solve the measurement problem, for instance. It won't solve Penrose's worry about superposing geometries. Conversely, if the experimental results come in really differently, of course, we're in a totally different game, and then there will be a ton of money put into trying to understand this stuff at very sub-Planckian scales, and it'll be really exciting. I mean, I'm pretty confident the results will be what we expect, but I certainly, in a certain sense, I hope they're not, because it'd be much more interesting.
More fun. Yeah, I mean, it depends on how attached you are to your favorite interpretation of quantum mechanics. So, yeah, some people would think that maybe this measurement problem isn't something that the interpretation, we need something more fundamental. So, yeah.
Well, I love my favorite interpretation of quantum mechanics. It will be in ruins if the experimental data comes in and rules out gravitational superpositions. I still hope that'll happen. It'll be much more exciting.
Maybe once we have the conference coming and the questions. Can you do those in 2 minutes? Take the
I'd say the emergent approaches, I quite like them. I think more people should look into them.
Okay. And what about the first one? What is the current stage of the project? Is there any progress?
Well,
in the SAT?
Yeah. I mean, talking about quantum gravity projects as a whole is quite difficult because in each kind of approach, let's say they have progress, but from the outside it's hard to judge.
Excellent.
Thank you.
Siddharth Muthukrishnan, please.
So I'm going to talk about black hole complementarity. And black hole complementarity is a family of ideas that have become quite popular in the physics literature in response to the black hole information paradox. So first, let's briefly talk about the black hole information paradox. The quick setup here is an evaporating black hole. So here's a stylized Penrose diagram of an evaporating black hole. If you're not familiar with Penrose diagrams, the basic idea is simply that vertical axis is time, and you won't go too wrong by thinking the horizontal axis is space, but spatial infinity is a point here. And you have a space-like slice with some matter and radiation. It collapses, forms a black hole. The black hole evaporates, and then you have some post-evaporation structure. An evaporating black hole leads to a paradox. I'm going to focus on a version of the paradox which gets called the page time paradox. This name was given by David Wallace, but the paradox has been around in the literature for a while. in order to see the paradox, let's look at the entropy of the black hole. On the vertical axis, we have black hole entropy, and on the horizontal axis, we have time. There's one argument that tells you that the entropy of the black hole should increase monotonically throughout evaporation. The argument is due to Hawking, and if you combine Hawking's argument with an assumption about unitarity, then essentially, because the Hawking radiation is always thermal, this means that the entropy of the black hole should also always be thermal, and so the von Neumann entropy of the black hole increases monotonically. You have another argument, which tells you that the entropy of the black hole should start decreasing at some point, estimated to be roughly halfway around. I won't reconstruct the argument here, but to get an intuition for this, the idea is roughly that the information that fell into the black hole has to start coming out at some point, and the radiation can't always be entirely featureless because it must eventually contain enough structure to reconstruct what fell into the black hole. And if you estimate when it needs to start turning the corner, so to speak, should be roughly halfway in between. Obviously, the entropy can't do both at the same time. So we have a contradiction, which is a paradox. A natural thought here is to ask, can we get an empirically observable contradiction from the quantum physics of this black hole? So entropy is not an observable in quantum theory. So can we do some experiment that'll display this paradox? This is where black hole complementarity begins to make its appearance. So one version of black hole complementarity, what I'm calling operational complementarity, says that the answer to that question is no. So we can't do an experiment which will allow a single observer to detect a violation of the rules of quantum mechanics in or near a black hole. So let's get a feel for why that might be the case or how that might work. Consider a thought experiment in which you have two experimenters, Alice and Bob. Alice bravely decides to fall into the black hole. Bob is hovering outside, not quite so courageous. And Alice will experience a smooth crossing if the black hole is large enough compared to her size. Now, you can give a quantum argument that says that from Bob's perspective, he will see Alice as essentially hitting a surface one Planck length above the true horizon and thermalizing on that surface. That surface is called the stretched horizon, and it's the boundary of the exterior field theory that you have to have in order to maintain unitarity and consistency with black hole thermodynamics, black hole statistical mechanics. Obviously, it seems as if you can't both have Alice cross the horizon smoothly and get burned up at the stretched horizon. But how can we do an experiment which will display this contradiction? A natural thought might be that Alice will send a signal to Bob after she crosses the stretched horizon saying that I'm safe, and this will tell Bob that something's wrong with his picture. However, because the distance is only one Planck length, she will have to encode her signal in modes of Planck frequency, and we are assuming that experimenters don't have control over Planck scale degrees of freedom. As to why that is, I'm happy to discuss more in Q&A. Now, this is an operational way of formulating the complementarity principle. That is, it is making reference to what observers can or cannot do. You might be uncomfortable with such principles because it reeks of instrumentalism. You don't want to formulate physical principles that make appeal to observers. A natural thought, then, is that can we formulate the principle in a fully descriptive way? So when we teach special relativity, they talk about observers and moving trains and all of that. But in those contexts, the talk of observers is dispensable. They're just placeholders for reference frames. So we can think maybe we can make a similar move here. If we try to do that, then we get what I call a descriptive principle of complementarity, in which you have essentially two descriptions, one associated with the exterior observer, Bob, and one associated with infalling observers like Alice. And the claim is that these two descriptions are consistent as representations of the way the world is. They're not just consistent by some operational constraints, consistent with each other and with quantum mechanics. So if that works, that would be good. But does that, and how might that work? So go back to the previous thought experiment. Here, essentially, the thought would be that there's some way in which you map mathematically the description of Alice smoothly crossing into the horizon onto Bob's description of Alice being thermalized on the stretched horizon. So there are several proposals here, but insofar as we can mathematically make them consistent, then at the very least, it leaves open the possibility that there's physical consistency as well. So this, if, holography is the sort of thing that you should be thinking about here, where there's a holographic description of Alice on the stretched horizon. But unfortunately, descriptive complementarity faces problems, and I don't think it can work. So in order to see this, consider another paradox in this neighborhood, which is the cloning paradox. So let's say Alice carries with her a quantum state. She falls into the black hole. Now, eventually, that quantum state is going to emerge in the radiation. If you remember, the information has to start coming out at some point. And that information, if it comes out, you can actually argue that there are, even within one description, you will have a cloning process, because the quantum state is present both in the interior and in the radiation. And given that this quantum state is arbitrary, what we have done is generate a quantum cloner, and quantum mechanics tells us that quantum cloning is disallowed. So if we take these states as descriptively seriously, as really representing the way the world is, then we are representing the world in a way that is in conflict with quantum mechanics, and that is bad. However, now you can ask, well, can I operationally see a violation of quantum mechanics here? So how might you do that? The natural thought is that Alice carries with her a quantum state. The quantum state emerges in the radiation. Bob extracts the quantum state from the radiation, and then he jumps into the black hole. And in the meantime, Alice sends Bob a signal after she crosses in with her quantum state. And now Bob, having recovered the state from the radiation, will collect the state from Alice and compare it with the state that he recovered in the radiation and check that, hey, a cloning process has occurred. But can we actually do this? Well, the key barrier here is that Bob doesn't have enough time, because Bob has a very short life expectancy. He's going to hit the singularity very soon. So, and if you can actually calculate and show that there is just not enough time. It's the fastest you can try and acquire the information is, after it fell in, is the longest time Alice can wait before she has to send it before he hits the singularity. So if you work it out, it's a just miss. But, so operationally, you can't recover this. There are several other thought experiments of this nature where, essentially, descriptively, it seems as if there's a violation of quantum mechanics, but operationally, if you try to carry it out, you have barriers that show up. The most famous example is the entanglement monogamy violation, or the firewall paradox, or the AMPS paradox. Dialectically, this is similar to what happens with perpetual motion machines, is that someone proposes a perpetual motion machine, and then turns out there is some subtle barrier that actually prevents that machine from being a truly perpetual motion machine. Okay, so what should we take from all of this? So let's say you're a realist. So what you want is a theory that describes the way the world is that can be realistically interpreted. Then at the very least, you should take into account the success of operational complementarity. That is, these barriers are signaling something that you should take into account. So similarly, just like statistical mechanics, we knew that perpetual motion machines were impossible well before statistical mechanics came on the scene. Statistical mechanics should tell us why perpetual motion machines are impossible. Similarly, whatever realist theory we come up with should tell us why operational complementarity is succeeding. If you're an operationalist, that is, you don't mind referring to observers in your theories, perhaps you're an instrumentalist in your philosophy of science, in that case, the black hole information paradox isn't really that worrying to you. Because there aren't any, if operational complementarity continues to be successful, as the physics literature has indicated, then you really don't have a paradox that is operationally troublesome, and so you can be more quiet about the information paradox. Thank you.
Thank you for the talk. I was just wondering, Bob has to receive all the information that's radiated, all the Alice information that's radiated from the black hole before he jumps in. And I'm just curious, what part of the black hole has to evaporate? I mean, how can you be sure that all the information about Alice, maybe the whole black hole has to evaporate before you can be sure that all the information about Alice is accessible to you? Well, and then there's nothing to jump into.
So the arguments that I'm referring to model the black hole as this object that scrambles information and returns it. And you can calculate that, you know, let's say after the page time, which is roughly halfway through, if you toss in a quantum system, the information contained in it is going to come back at you very fast, order m log m, which for a solar mass black hole is like 10 to the minus 4 seconds. So you can calculate that you'll recover enough to recover the state that you just threw in. So yeah, so you don't have to actually wait till the end of the evaporation process to recover what, at least parts of what fell in. Obviously, you need to wait until the end to recover everything, but that's not what we're trying to do.
Okay, thank you very much.
Okay.
And the next speaker is going to be Alvaro Mosota Frauca. Please.
Thank you for being here. Today I will be speaking about quantum cosmology and the age of the universe. So the idea of this talk is to revisit the problem of time, but in the context of quantum cosmology. The simplicity of quantum cosmology makes the concept of analysis much more simpler than in the context of full general relativity. And I want to make two claims. One particular claim is that the first one is that there's a problem of time in quantum cosmology. There are some predictions that go missing, in particular those regarding time, such as the age of the universe. And then I will take this to support the more general claim that there's a problem of time with quantization of general relativity, canonical quantizations of general relativity. So I will start by discussing the problem of time, and then if I have time, I will speak a little bit about cosmology. So what is the problem of time? The problem of time is a series of conceptual problems that arise when we try to canonically quantize any reparametrization of differential invariants, any invariant model, like general relativity or some other models I will speak about. And what happens is that when one tries to formulate a Schrödinger equation for it, I'm skipping out of technical details in here. What one finds is that the action of the Hamiltonian on quantum states has to be 0, so the Schrödinger equation becomes trivial. So there is no temporal evolution as one would be expecting. And now my analysis of this problem is that how serious it is depends a lot on the ways the original classical theory represents time. I will argue that there are two types of models, of reparametrization invariant models, and the diagnosis for the problem of time for both kind of models would be widely different. So the way we'll illustrate this is by showing how quantization works for 3 different models for one same system. This system is a model of 2 harmonic oscillators, described by two variables, x and y, evolving with respect to Newtonian time t. But I will give three models for this simple system. One is the standard Newtonian model. The second one is a model in which we have introduced an arbitrary temporal parameter tau, but we still keep our original Newtonian time t. And in the third model, the original time coordinate t just disappears, and we have evolution with respect to this variable t, tau. So this is analogous to the case of general relativity, in which we can choose freely our time coordinate tau, but if one wants to measure proper time, there is still one proper time proper in this model, which is the Newtonian time. And very quickly, what happens when one quantizes the model in the three cases it's quite different. So as I said, the three models differ in whether they are representation invariant or not. The first one doesn't have this symmetry. We are describing things just with respect to Newtonian time. The second and third one are representation invariant. We can choose freely our time coordinate. But in the second one, we say it's deparameterizable because our original time coordinate is still there, while in the third one, it's not there. So we can say that time is represented in different ways in the three models. So in the three of them, we have an ordering aspect of time. We have a parameter describing what happens after, before, or what happens in between two events. But in the first one, it's Newtonian time, and the second and third one, it's our parameter tau. Then we have a metric aspect of time, which is this Newtonian time, which is explicit in the first two models, while in the third one, it's not explicit. We can recover it by means of this expression, that for you, those of you who are familiar with general relativity, this is similar with the way we define proper time in general relativity starting from a particular solution of general relativity. That's the way of connecting an arbitrary coordinate with what clocks measure. Then when we quantize the theory, for model number one, it's just the standard theory, there's no problem of time, everything goes fine. For models number 2 and 3, as they are representation invariant, what happens is that the action of the Hamiltonian has to vanish on these states, and we get states that do not evolve with respect to the temporal evolution parameter of these models. This means that we get states that are independent of tau. However, here there is an important difference between both models, because in model number 2, in the classical model, we had this redundancy, we had t and tau explicit in the model, so even if tau goes missing in the quantum model, we still have t, so we can still do quantum mechanics as we usually do. So in this sense, what we obtain by the quantization of model number 2 is formally analogous to the quantization of model number 1, and everything works the same. However, when we quantize model number 3, we don't get any dependence on t or tau, any dependence on temporal structures goes just missing, and the model is much more problematic. So in this sense, I would say that for this kind of model, the quantization is problematic. And what I will argue is that in the case of quantum cosmology, the same happens. We have a model which had a clear temporal dependence in the classical theory that just goes missing in the quantum model. So to insist, well, in classical cosmology, what we do is use a particular class of space-time models, which are symmetric, are homogeneous, and in these models, we are able to describe a preferred time variable, which is this cosmic time t, which allows to define prediction, to define the edge universe of the universe and make predictions such as has been commented this morning. So it's a model with a clear temporal structure. So we have, as in the same in the Newtonian model, we have an ordered structure, something that defines after, before, and in betweenness. And we have also metric predictions about how long certain processes last. So yeah, in this classical model, we have the same type of temporal structure that we had in this double harmonic oscillator model. So now when we quantize the model, what happens is that this kind of model, as it's representation invariant and it's non-deparameterizable, t is not explicit in the action of general relativity, or not explicit in the action of cosmology. What we get is wave functions that depend on scale factor, on the matter we have, but not on cosmic time. And as I said, this seems to be problematic, but nevertheless, the quantum community takes this kind of states to be constituting a physically meaningful and sound theory. And they do so in two ways. So there are a part of the community which says that the way of interpreting the states is by choosing one of our variables and taking them as a clock. When they say clock, sometimes they oscillate between a clock or a time variable, but at the end of the day, what they really mean is something like a time variable. It's something finding a temporal sequence, it is defining an order, something like that. And then there is another kind of interpretation, which is to read this kind of state as encoding some probabilities of finding some size of the universe, some state for the degrees of freedom, so on and so on. And what I will argue very, very briefly is that these two readings are problematic. In both cases, facts about time and duration seem to go missing. So first, in the case of the eternal time strategy or approach or resolution of the problem of time, I think there is a conceptual mistake or mismatch in what these people are sometimes proposing, because, as I said before, A or phi, or in our first model, X or Y, are dynamical degrees of freedom. They represent something like the size of the universe, something like the state of matter, something like the position of two oscillators, and they are not time variables. So in this sense, taking one of them to play the role of a time variable seems to be mistaken. And one can even ask if we took one of these variables to be a clock variable or a time variable, how would we still recover facts about metric time, facts about the age of the universe? So there was those facts encoded in T, that even if we say that time was A or time was phi, there seems to be a missing link in between this Alet's time parameter and the time parameter we usually do and take to be meaningful in classical cosmological model. And then we have the probability approaches to quantum cosmology, which read wave functions, the wave function that one obtains by applying these quantization methods, to be encoding probabilities in some way. However, this interpretation seems to be quite problematic. It seems to be implying that there is some sort of observer measuring the universe, but it's still a kind of worrisome. One still would expect that there is some time dependence, that when one performs a sequential measurement, the universe could be expanding and so on. But all of this seems to be quite unclear in this kind of model. And in particular, well, here I quote Carlo Rovelli and Francesca Vidotto, that when they discuss cosmological models in the classical setting, they say, oh, but what we really care in relativity is about, they usually speak about correlations between observables. So in this case, they say, we just care about the value of the size of the universe when the field takes some given value, or we just care about the value of the field when the universe is this big, something like that. But to me, this seems wrong, as I have said, the temporal structure of classical cosmological models is much richer, and in particular, we also care about things like the age of the universe. We take it to be like an empirically meaningful prediction, and it seems that to me that they are leaving this part of the story out of the picture. So to wrap up, I will insist in what I have just said. Classical cosmological models have time and temporal facts about order and duration as part of the empirical content of these models. And in particular, I speak about the age of the universe. When we apply canonical quantization methods to these kind of models, this part of the empirical content of the classical theory seems to go missing. The two main families of interpretations in quantum cosmological community, I find in both of them serious conceptual problems, and that I think that they fail to recover this original empirical content. So one may worry about these particular models in general, and about the application of canonical quantization methods to models like classical cosmology or general relativity in general. And that's everything. Thank you very much.
Thanks. I'm sympathetic, but just a thought on the age of the universe point. I mean, obviously, it's not as if we have direct empirical access to time anyway. It's always, in practice, a more indirect process. So if I apply this kind of method and I get out something like the sequence of spatial geometries indexed by, I don't know, overall scale factor or something, and then I can show that that sequence of spatial geometries is such that it basically satisfies the constraint integrated out versions of the Einstein field equations, so it can be embedded into a geometry, and the geometry says the singular point at the beginning is 13.8 billion years before the bit that seems to match the present epoch. I mean, wouldn't that be a satisfactory recovery of the age of the universe on this kind of program?
Right, but the model isn't giving you the proper time or anything like that. So it's something you would be adding somehow by hand, I guess. Or
well, if you think about GR generally dynamically, I can write a GR dynamics, at least formally, as a dynamics on superspace, right. With no intrinsic parameterization, and then I can recover the parameterization by solving for the constraints.
Well, but you still have your lapse function and
I can solve, but I can solve for
is encoding the temporal part of the metric.
Yeah, if I've got the trajectory in superspace, I can at least formally, there are technical problems, but formally I can solve for the lapse function.
Oh, you mean by applying like solving the constraints or something like that, or
basically
applying like that thin sandwich conjecture?
Let's talk more later.
Okay, thank you.
Thank you very much.
Okay.
And next, Anastasia Lazutkina.
So good afternoon, everyone. Thank you for staying and attending my talk. I'm a philosopher of science. And as a philosopher of science who works on cosmology, one of the main questions that I'm trying to understand is how justified are you working in alternative cosmology, so not part of the standard Lambda CDM. And the claim that I will try to defend today is that you're justified to do that, and actually there is no epistemic justification for eliminating alternatives like MOND from the theory space as possible solutions to the problems that we have. So statements like Lambda CDM has overwhelming amount of evidence for dark matter and there is nothing better are simply false. So I'm going to present you the framework in which I work, so this meta-empirical theory assessment, then I'm going to go through the theories I'm talking about, give some constraints, and then we'll go to the conclusion. So meta-empirical theory assessment was proposed by Richard David in the context of string theory. The idea kind of lies within the Bayesian epistemology, so confirmation is understood as raising the probability, but it's not like yes or no. So it's very gradual. Something can raise the probability of your theory being empirically adequate. And apart from empirical arguments, there can be non-empirical or meta-empirical arguments that could also raise the probability of your theory to be empirically adequate. And he presents 3 of those, so this is no alternative argument. Basically, if you have a certain theory that accounts for all the empirical data, explains it, or at least is consistent with it, and then it also makes predictions for the future experiments and satisfies your theoretical constraints, you can look if there is no other theory that can do that, then you can have a meta-empirical argument in a sense that it's apart from the domain of the theory's applicability, and it can raise the probability of your theory being viable. And then you can supplement it with unexpected explanatory coherence. So this is when you can explain things that your theory was not designed to explain. And then you can have a meta-induction argument. So if this worked well in the past of the research tradition, then it would work well also now, like for example with the particle physics. And so I use the problem-oriented reformulation. We start with the problems and then we see what kind of constraints one can draw from it. So we have basically, the biggest problem is GR. GR is inconsistent with observations from cosmology and astrophysics if you take only the standard model of particle physics into account, so only the baryonic matter. And you have to explain from cosmology, it would be you have to explain the power spectrum, so you have CMB, you have the structure formation, you have the nucleosynthesis, and then from the galactic scales, you have individual galaxies, their rotational curves, clusters of galaxies, and even the star clusters, wide binaries, and so on. And two kind of main solutions are postulating a particle outside of the standard model. Usually these are cold dark matter particles, so WIMPs or axions, or suggesting to modify theory of gravity. So Mordechai Milgram suggested that in 1983 by observing, so empirically driven kind of observation, that when you go below a certain acceleration, so just to remind, in our solar system, the accelerations are very high because the distances are not so large. But if you go to further than that, then you can have very low accelerations. And if you have them, then your dynamics changes. And this is what he noticed. So basically, they formulated with Bekenstein in 1984 a non-relativistic Lagrangian. And then you could see here I have the modified version of the Poisson equation. So if you do have low accelerations, then it would lead to the modified dynamics when the matter density would kind of boost the Milgromian regime. And if you have a high acceleration, then the whole thing will reduce to the just standard Poisson equation. And now there've been another kind of development within the TVS. So this is a relativistic extension also developed by Bekenstein, and it had contradictions with gravitational waves. And that's why now we have the best model is the Ether-scalar tensor by Skordis and Zlotnik. So this is from 2021. It is an extension of GR. So it's not really extension of Mond, but it gives you Mond in a classical limit. But it also has extra fields. So it has unit time-like vector, you have a scalar field, and then the usual metric tensor of GR. And then we have a cosmological model, so new HDM. So you have Mond and sterile neutrinos. And then a Bohemian model that is currently being worked on in Bonn and in Nanjing in China, which is also kind of the better version of everything we have now. And since I have so little time, I cannot, of course, go through comparison of all the kind of tests that you have. But the point is kind of simple. For every single kind of scale of astrophysics and cosmology, both approaches have answers. So sometimes these are wrong answers, so there are falsifications, but there are falsifications of both. So Lambda CDM has a lot of problems as well. And sometimes you have no predictions, but only accommodation, depending on the scale where you go to. But the idea is that for a long time it has been claimed that only dark matter can account for this evidence. But what we have is a kind of underdetermination because you have both approaches accounting for the evidence. And probably the most well-known thing is that Mond cannot account for CMB, but now from 2021, we can actually do that. So when you take the relativistic version by Skordis and you add those extra fields, you get indistinguishable line you see here. So you have the lambda CDM as a black line, and then you have, you can adjust, so basically Mond to the lambda CDM cosmology without dark matter. And this is the first theory that is extension of GR that can account for CMB without dark matter. Now, it does so in a fine-tuned way, so it doesn't actually predict CMB, but just also to remind, lambda CDM only predicted one peak of it, so the rest was accommodation. But the nice thing is that we can actually solve the Hubble tension. So this sounds like very kind of, very bold claim, but so this is the work by Moritz Hasbaro and et al. So you can kind of give a solution within the CMB and the KBC void that we have now. Then just briefly about the clusters, galactic clusters. They also used to be known as the best evidence for dark matter, and the situation has changed dramatically because now the galactic clusters, like the Body cluster or El Gorda, if you look, I have the probability of such things existing within the lambda CDM.
and these are observed clusters. So if we look at their velocities, it should be, according to the last simulations, it was about like 2.5. So if you look at this probability of it, it's way beyond like so possible. Like it's arbitrary unlikely. It's beyond 5 sigma, so over that. And on the other hand, MOND is not really great in that as well. If you add sterile neutrinos, then you can account for galactic clusters. But there are problems with simulations and with the structure formation also. So you have kind of difficulties everywhere. And then one of the things that for people who work in MOND, it serves as a kind of very good background for why there is no cold dark matter, but we can still add sterile neutrinos, is because cold dark matter would form dark matter halos. And this would affect galactic dynamics in an unavoidable way, because if you have a dark matter halo, and then you have a galaxy, so you have a galaxy that is inside the halo, and then there is another huge halo, and then you have a galaxy that has its own halo, and it comes inside the host galaxy. So what would happen if you have so much like mass density, so many halos? Your dynamics would change in a way that the galaxies, like the rotating bars of the galaxies will start to slow down. But what we see is that actually the real galaxies have very fast bars. And also they should merge much more frequently, and this doesn't happen. So this is again like a real problem for the model. So when you go to the MOND regime, so yes, again, it has this fine-tuning for the CMB, but for the galactic part, it was designed to explain the galactic dynamics. So in this sense, it has much more predictions, and it doesn't have problems because it doesn't have halos. And hot dark matter wouldn't cause those halos because sterile neutrinos, they would just fly away. It wouldn't just appear. So that's why it's not only a methodological question, but an empirical question of empirical adequacy. So if I take it to the kind of virtues that one can talk about within the meta-empirical theory assessment, usually you're not justified to do that because you have no epistemic justification to think that the theory that will solve all your problems is a simple one, or that it has to unify. Those kind of things usually come from the research tradition that you have. But if you have to think about it, well, so you have parametric simplicity for MOND because it doesn't have free parameters, but when you go to the relativistic extensions, you have those free fields. So simplicity really goes away. And for lambda CDM, well, you do unify like all the scales, but if you're empirically inadequate on those scales, then the question is this really unification? And then predictive power, yeah, a lot of discussion about that. And I think underdetermination questions also kind of arise because you have these problems on different scales and virtues on different scales. But if you take both scales together, if you apply very strict scientificality conditions like no fine-tuning, no ad hoc, only predictions, you would not have a single approach. But if you take down, you're like, okay, whatever. Like, as long as there is like empirical consistency on some scales, as long as there are some predictions, then you have both. And so the only theoretical constraints that I could think of so far within the relativistic extension is that MOND is a nonlinear theory. But this is not an epistemic constraint. We don't have, it's just a practice. Like, it's about pragmatic considerations. We don't have epistemic reason to think that the future theory will be a linear one. And then a violation of strong equivalence principle. Well, here it's also it's not really such a big problem to reject the theory because you have the weak principle and the Einstein principle satisfied. So they're not violated. And then there are actually some empirical studies from 2020 that there is actually external field effect, and this violates the strong equivalence principle anyway. So just to conclude briefly, we have the same domain of applicability. So if you look at it as a kind of effective framework, so MOND and lambda CDM, because in both you don't have a final kind of solution. Lambda CDM has so many versions of dark matter you can kind of look into, and MOND has so many things that you can use as an underlying theory to produce Mondian phenomenology. But you still account for the same data. And to make a neutral claim, you at least on a par. So at least on a par accounting for them. Although, of course, people who work on MOND would disagree, people who work on lambda CDM would disagree, but if you try to have this kind of
neutral perspective, I think we just look at the scales. Okay, can you be consistent with that? Yes, then it works. And the theoretical constraints that I gave, they don't seem to be epistemically viable enough to eliminate it from the theory space. And so my conclusion is that MOND remains a viable alternative to Lambda CDM. And the only reason why would someone not even consider this as an alternative is a practical question or a sociological one, because epistemically speaking, there is no reason to do that. Okay, thank you.
I mean, there's lots we could talk about the physics, maybe offline or something. But just as a question about the overall methodology, I mean, here's something deflationary somebody could say back here. The papers you're quoting about the Mondian approach to the CMB are things that come out in the last 2 or 3 years.
Yeah.
Now, if you wanted to say, look, for 20 years we've had a solution to the CMB problem, and in Mond, and that's been ignored by mainstream astrophysics, that sounds like a philosophy of science question about the sociology of science or something. But science doesn't turn on a dime. I mean, let's stipulate that those results are entirely right. It's still not all that surprising that that people haven't updated their priors much inside Lambda CDM, because it's pretty recent. And it sort of feels like the argument you're making there is not an argument to make to a philosophy of science conference. It's sort of an argument to make to an astrophysics conference.
Discussed within the philosophy of science papers as well. And people so my particular argument was here, if you see, it was also directed towards Richard David himself and Siska de Bademaker, who make a claim like this, referring to the same paper I talk about. So they refer to the Skordis and Zlosnik paper, and they still don't say that there is a CMB solution. So this is more, it's another question. And of course, this is it's on the border. It's on the border between pure just methodology for cosmologists and the philosophical questions. The thing is that, are you epistemically justified to do that? That's not a physics question.
Sure, but to be fair, you can't blame Baker and Dawid for a paper whose publication date is 2022 for not being up to speed with papers that came out in 2021.
But they refer to that.
Okay, that's good. That's a good response. Point taken.
So they refer to that paper and still say the same thing. And it's not just them. I mean, it's part of the larger debate in philosophy of science that you kind of you seem to say unless cosmologists, unless the cosmological community accepts this, at the large scale, then this is not really good enough for us to look at. But if you expect your philosophy of science to be based on what the majority already have, accepted, there is a problem. Because you can never look for alternatives that are viable, because you will have a circular argumentation. So you have to look at it.
Thank you very much.
Yeah, anyway, thank you.
And now Alexander Niederklapfer.
Thank you. All right. I'm going to ask the question of what is fundamental in fundamental physics. And in particular, I'm interested in whether particle physics can tell us what is fundamental in fundamental physics. It seems that a lot of people actually think that particle physics is the place that tells us what is fundamental in fundamental physics. So if we just look up fundamentality in the SEP, then we get Thomas, who might be here or not, saying that it is not uncommon to think that particle physics has some special role in our inquiry into the structure of reality. After all, every material entity is made up of fundamental particles. I think a lot of people agree with that, especially in the metaphysics community. You hear things, so here's just another example of that. So not only is it perceived or is it assumed that particle physics tells us what is fundamental, but also that the concept of composition or decomposition seems to be very central to that. So, my claim is I don't think that particle physics tells us by itself what is fundamental. We can't just, as metaphysicians or philosophers of science, point to particle physics and say, yeah, they figured out what is fundamental. Why do I think that? Because there is, as I will hopefully show, not a unique decomposition of systems into their parts in particle physics. And since fundamentality seems to be so connected to a notion of decomposition, that results in the fact that there's no unique account of fundamentality. So what is fundamentality? Many metaphysicians would agree that it is a sort of priority relation, which I here interpret in terms of the decomposition or composition of objects. So given such a decomposition or priority relation, there's basically two ways how people say that something is fundamental. Either you say that it is not divisible into more fundamental pieces, or you say that it is a sort of basic building block for everything else. So applied to particle physics, that would be saying that elementary particles are truly elementary because they can't be divided up any further, or everything in material reality is made up of elementary particles. I'll just, you can use your favorite of the two. It doesn't really matter for my argument. I think there's interesting things to say about the two, but not in these 10 minutes. What objects are we dealing with when we say that particle physics figures it out? Quantum systems. And for the sake of this argument, I just take a quantum system to be given by a Hilbert space and an algebra of observables. You could add a dynamics, but I don't think that adding a dynamics will make it easier for you, so we ignore that for now. As a little example, here's an electron. Well, obviously not. But you would usually model an electron with a C2 Hilbert space and the usual algebra of observables given by the Pauli spin matrices. Now it turns out that in particle physics, this Hilbert space and algebra of observables is very often given as a representation of a group, a unitary representation of a group, of the global symmetry group of that system. And that's what I will focus on here. So the two decompositions, I won't say much about them just because of time, but I take that both of them can be metaphysically, can be argued metaphysically for both of them that they are relevant decompositions. So for one, there's the tensor product. That's the standard one. Everyone uses that when they learn quantum mechanics. It's usually it's used for describing compound systems. Sort of the interpretation that is usually given is that the parts that you describe together with the tensor product will be statistically independent in a compound system. And now I'm arguing that particle physics, or especially group representation theory, gives us another one, namely the direct sum, which is usually interpreted as representing a mixture of a system. You have an ensemble of systems, and you can describe a mixed state on that. So, why is that? When we look at the standard model of particle physics, we see the pictures that are as nice as this one, where all of the particles are neatly organized into groups and are arranged according to certain properties, the quantum numbers. So we say that, I don't know, some quark has a special mass, a special charge, spin, color charge. And it is in this way that we would say that the ontology of the standard model is captured by the symmetry groups of the system. So SU3 describing color charge, SU2 and U1 the electroweak, and P is the Poincare group. So why are we interested in group representations? This basically started with Wigner and the classic paper there, who set out to find all of the unitary irreducible representations, short IRREPs, of the Poincare group. And that sort of became the definition of an elementary particle. An elementary particle is an irreducible representation of the Poincare group. Why? We can borrow something from Roberts here, Brian Roberts, who coins the term representation view, and basically argues that a quantum system has a spatiotemporal degree of freedom if and only if it carries a group representation of the spacetime symmetry group. I think we can extend that, I'm happy to talk more about that if someone is interested, to also the internal symmetries, namely the SU3, SU2, and U1. So in general, we get that you decide on the degrees of freedom that your system shall have. That determines the groups that it should be a representation of, and the mathematics gives you the rest. It gives you the Hilbert space and algebra of observables. Right, then the irreducible representations, that's the most interesting thing. Now here's the mathematical definition. I'm not going to read it out. But the interesting thing is that Wigner and Peter and Weil showed that for all of the relevant groups for the standard model, it holds that any given representation can be decomposed into a direct sum of irreducible representations. And irreducible representations, as their name suggests, cannot be broken down any further. So given any representation of the relevant groups, you will have the fact that it can be broken down into irreps, into a direct sum of irreps. So in that sense, irreps are fundamental with respect to the direct sum operation amongst the group representation. So we have that the tensor product and the direct sum are available for group representations as decompositions. We know that the direct sum is available for any representation. Thus, we can ask the question, given two systems, we tensor them together as we would do. Say here in a hydrogen atom, you have an electron and a proton, two spin 1/2 systems. So we tensor the two together, and then we can ask the question, how can we decompose this reducible representation of SU2 into irreducible ones? And it turns out that it is the direct sum of a spin 0 and a spin 1 system. So now we have that there's two decompositions available for the same class of objects, namely representations of the symmetry group. And the question is which one to choose? Or what should we metaphysically learn from that? Do we maybe have to just adjust our metaphysics? So particle physics is supposed to describe the fundamental objects of our universe. Fundamentality seems to be connected to decomposition. It seems like there's not, at least not easily, one clear decomposition available. I think at least the minimum that we should take away from that is that we, if we're metaphysicians, should not just point to particle physics and say they figured out what fundamentality is. Thank you.
Thank you. I'm just trying to understand why the direct sum is even prima facie a candidate for decomposition in the fundamentality sense. I mean, if I just think about a single spinless particle, then its Hilbert space is the direct sum of the Hilbert space of states that are to the left of you in this room and of the Hilbert space of states to the right of you. But I don't think I feel even the prima facie urge to say that somehow in any way salient to fundamentality that it decomposes into those two. It's just that, because it's quantum mechanics, it can be over here, and it can be over here, and it can also be in a superposition over here and over here. But what's the connection between that idea and fundamentality's notion of decomposition?
Yeah, absolutely. I think the main difference, what you're sort of alluding to, is that sort of I start out by saying, okay, I give you a system, and the degree of freedom is an SU2 degree of freedom. And I now give you, if I give you now a two-dimensional Hilbert space, that is, as you say, the sort of sum of being here and being there, or like pointing here and pointing there, then that's not representations anymore. That's not group representations anymore. But if I give you a four-dimensional Hilbert space and say that it carries a reducible representation of SU2, then as group representations, it splits up into 0 plus 1 representation.
Sure, but I'm still not seeing what it has to do with composition, with anything that feels like composition. I mean, I agree that's how the math works, but it's still, after all, that decomposition is still a superposition type principle. It's still the kind of thing it would say, well, it could be in this subspace, or it could be in this subspace, or it could be a superposition of these things.
Yes, that's still true, but you could, from a sort of metaphysical point of view that as decomposition into fundamental possibilities, for example.
Yeah, that feels like a rather different notion of fundamentality, but fair enough.
Maybe that's the answer to, sort of the metaphysical answer to the situation.
Yeah, I mean, it's a version of David's question. It's even in the language of quantum physics, with the direct sum, we call those different subspaces, and whereas with the tensor product, we'll call them subsystems. And the reason why the tensor product is the natural choice for subsystem decomposition is that when you have algebras of observables, then what you get out are tensor product structures. But maybe this we can talk about this later. A quick question, like to your broader project. I mean, don't we already know that particles are not fundamental, or that they're emergent from fields and so on? So, I mean, maybe some metaphysicians.
You could do the exact same thing for field operators, because you would say that your quarks field globally is a representation of the SU3. So might become a sort of different situation, but sort of in principle you can run all the things through. Just don't call them particles then.
Okay, thank you. And then Petri Turunen, Ilkka Pättiniemi, and Johan Hietanen.
And we are here to talk a bit about interpretations in quantum mechanics. So first of all, as you may know, there's a plethora of interpretations. So this is just a short list of a few. There's the many worlds interpretation, de Broglie-Born interpretation, Bohmian mechanics, transactional interpretation, Copenhagen interpretation, relational quantum mechanics, quantum Bayesianisms, consistent histories, superdeterminism, GRV spontaneous collapse theories, and so on. And of course, some of these can be thought of as mere reformulations of standard quantum mechanics, but it's still quite a long list. And one thing that gets overlooked is that there's also a different sense of interpretation in quantum mechanics, and that's related to the fact that quantum mechanics is an empirical theory. So you also have to interpret quantum mechanics to empirical cases. So you have to somehow pair bits of quantum mechanics to some empirical settings, ultimately. And I guess the reason that this doesn't garner a lot of attention is that we already know pretty well how to do this. This is something that's very common in scientific practice, and this is what people at CERN are doing when they are creating the measurement apparatus. So the interesting question for us is then, what's the difference between this kind of interpretations? Do we mean something different with these interpretations than we did with the interpretations of quantum mechanics? So to look into this, we propose this distinction between interpretations to and interpretation as. So interpretation to. So it seems that the important bit is that these are interpretations that are empirically evaluable. So you can actually find out if your interpretation gets the right results. You can evaluate the theories this way. And they also seem to be ontologically unproblematic. there are no ontology courses for quantum physicists, or there aren't these big ontological debates that dominate the quantum physics seminars or conferences. And in fact, it seems that very minimal ontological commitments are already enough to have this kind of interpretations. You don't need a lot of stuff there. There's some sort of basic non-arbitrariness constraints are already more than enough. And these are also very commonplace. It's something that happens very often in scientific practice. Yeah.
Okay, then. So then there are these things like the interpretations of quantum mechanics, which are, we claim might be seen more like an interpretations as. So they are not straightforwardly, at least empirically decidable. And they add elements that seem to be non-empirical, at least part due to underdetermination, although I know some disagree. So should we accept things such as, say, the Bohmian particle trajectories, or the backwards causation of the transactional interpretation, or branching worlds, or none of the above, given that all these ways of doing doing quantum mechanics give the same sort of predictions? We do the same physics in the end, with or without any of these added elements. So it seems that these interpretations, as we call them, quantum mechanics being somehow, and that's where the name comes from. So it's the idea is that they sort of tell us more than the bare sort of instrumental story of how the world is given our theories. So what is the role of these interpretations as? Given that interpretations too, as we point out, are enough for empirical work. So first of these can give rise to problems, so there are reasons to avoid things like this. So for instance, in the de Broglie-Bohm interpretation, you have nice little particle trajectories, but then the particle only travels one of those trajectories. But in cases like, say, the Bohm-Aharonov effect, the other channels, the channels where the particle doesn't reside in, are needed in order to make sense of the predictions. So what do we then gain by insisting that the particle actually is there in some strong sense? So what these things do is often said that they grant as a way of understanding physical reality and explaining the results we get. But then we need to ask, what do we mean by explanation? What do we mean by understanding? And there's some recent work here in Helsinki on scientific explanation and understanding, and of course there's a long tradition of that work. And if we understand explanation as something like, well, we can derive predictions, retrodictions, and stuff like that from our theories, then it seems that this added structure does not aid us in explanation. And if we take understanding as sort of an ability to do something empirically useful with our theories, then they seem to fail on this account also. But then, are we correct in thinking that there is a distinction between these two kinds of interpretation? Is one actually the other and the other way around? So are we being too harsh? And I think that's the question we'll leave it today.
I'll not comment on the underdetermination issue because I said what I thought about that yesterday. I mean, I would suggest that you think about the extent to which we really can separate how we apply this theory empirically that supposedly we understand very easily from some of the more interpretive questions. And I think decoherence is a good vehicle to look at there. I mean, decoherence definitely picks favorites among interpretations. It's tied to some approaches, not to others. But the development and ideas of decoherence were precisely based on the fact that a significant number of experimental situations and observational situations didn't fall very neatly into a previous way of thinking about applying the theory. I mean, consistent histories in particular, you identify as an interpretation, and it's there in your category of things that's neutral here. But the main things, people who drove the development of consistent history theory in the 80s and 90s were physicists who were trying to calculate stuff. So I think there's, I mean, I think the point you make that, look, we know how to apply these theories is important, and you're right to make it. But I think we can't completely cleanly separate the question of how we apply these theories to what kind of tacit interpretation moves we're making.
Yeah, so for us, the interesting question is exactly this: where does the distinction actually lie? So there are some sort of pretty clear cases where it's very interpreted, and then very empirical cases, and then in between you have these cases. So, like, our point is more that there's something interesting to be looked at that juncture, where you have this like empirical bit, and then also this interpretive bit that sort of relates to the empirical bit. And then on the first slide, so some of them are reformulations of quantum mechanics. The consistent histories, for example, I wouldn't really consider it as an interpretation.
Thanks for your talk. I was just thinking about kind of useful interpretations are usually like extensions of our scientific theories that kind of model future phenomena that we can then predict or then account for within our scientific theories. So, examples like the kind of Newton's invocation of the atom, which then led to like kinetic theory and the periodic table, and then also like non-Euclidean geometries. But these all like seem like ontologically extra things. So I'm not sure how they'll qualify as interpretations too in your framework, and then more be as interpretations as, even though they are empirically valuable, but they're just adding more to the theory rather than just being ontologically minimal.
Yeah, so of course, in scientific practice, the road from sort of building a theory to actually experimentally testing is a really long one. And for example, these non-commutative geometries that we heard about yesterday, they were like designed or like developed mostly on theoretical grounds. And then there was this like, how can we actually connect with the standard model thing? And you have the twisted Poincare symmetries and model products and all this like, construction that goes there. And of course, you have like there were conceptual issues on okay, what happens when the space-time gets quantized and so on. So it's like new interpretation of what the theory says, but then there's also this like goal of actually connecting it with the empirical cases. So it's a bit fuzzy when you're sort of still building it, but there's I guess the important bit is that the goal is to get something that you can actually evaluate.
Me. According to me, the difference between good and bad interpretation is, e.g., Einstein-Lorentz in special relativity. If you have a proper interpretation, you can evolve theory further. And in the case of quantum mechanics, all interpretation have hidden variables, which are not observable in principle. For instance, superposition can't be seen, can't be investigated because of Heisenberg relations. So, quantum mechanics is not complete. If you understand what is behind, we can evolve theory and practice very rapidly further, I think. What's your opinion?
I'm not sure that I agree that quantum mechanics is incomplete, but even given that, the superpositions might, in some sense, be empirically unobservable, but in another sense, of course, they are, because they have ramifications for predictions of experiments. So it looks it would look quite different if the superposition principle didn't apply. We would have a quite different kind of theory that would make quite different empirical predictions. So in that sense, it's part of the machinery that allows for empirical success in the case of quantum theory.
Thank you. And now Ilkka Pättiniemi.
I made a dramatic exit so I can make another dramatic entrance. Thanks all. So there were supposed to be 3 of us, and I was thinking I would not be part of the first presentation, but that's how it goes. So I'm talking about the old logical positivist Philipp Frank and his ideas on physics and reality, or something of that sort. So who was Philipp Frank? Well, he was a Viennese, an Austrian physicist and philosopher, a member of the Vienna Circle. He was hugely influenced by Mach and Boltzmann both, and I think he even studied under Boltzmann. And he held that that understanding the history and sociology of science is very important for the history of science, for the philosophy of science. Now, actually, I'm not delving too much into that. I'm just pointing it out to all those people who think that the Vienna Circle people were insensitive to such things. They indeed were not. So what I'm trying to show is something like Frank has a critical attitude that can help us avoid metaphysical pitfalls we might fall into when we are building, in his terms, a scientific world conception, in that is in trying to understand the world, in trying to understand the reality on the basis of our best science. And that this is doubly so in our quest for new theories. So the major reference here is Philipp Frank's book, Modern Science and Its Philosophy, which is a collection of most of his published essays on the philosophy of science. So, Frank tells us that throughout sort of natural philosophy, there has been this distinction between 2 kinds of ideas of truth. One is philosophic truth, and the other is scientific truth. And where philosophic truth is what we are beholden to, given our sort of a priori ideas about how the world should be. Whereas scientific truth has to do with, well, science. So here's Frank saying, the philosopher's attitude towards physical science had forever remained essentially unchanged. Physical theorems that are in contradiction with certain established general principles have to be rejected, even if these physical theorems are in agreement with all observed facts. And that there's, I think, seems to be some similarity here with certain aspects of interpreting quantum mechanics. So that's the sort of the philosophic truth there. Certain established general principles, we have to hold on to those and not to the science, no matter how well it has been observed. The scholastic philosopher, just as well as the advocate of empirism, upheld the distinction between scientific truth and philosophic truth. The truth of any physical theorem in the first sense has to be checked by experiments. The truth in the second, the philosophic sense, depends upon whether the theorem is compatible with certain established principles. So that's the sort of bad sort of metaphysical attitude. So Frank, of course, wants to do away with philosophic truth, or at least make it converge with scientific truth. The two criteria of truth which were of medieval thinkers like St. Thomas Aquinas, two distinct requirements, have fused more and more into one single requirement: to derive the best description of the observed phenomena from the simplest possible principle, where these principles are justified solely by the fact that they permit the derivation. So, Frank agrees that science and physics, with say, the metaphysician, that does require assumptions to build on. But he says that these are not, in any strong sense, philosophical or metaphysical assumptions, but they are rather pragmatically justified assumptions and held on only as long as they pay their way. So as long as they allow us to do more and better science, we hold on to them. And as soon as we find better ways of doing things, we are willing to revise these assumptions. So, on to a sort of, it seems now a distinct thing, but we are sort of converging towards something. So, in sort of an ancient analogy from Aristotle and others is to see physics as something like an organism, or physical world something like an organism. Physical entities they tend towards some goal, like objects fall downwards because they want to go to the middle of the earth and stuff like that. So there's this teleological organistic explanation going on. But then comes the early modern period with Galilei and others, and where physics is now seen as mechanistic. So it's stuff pushing other stuff around. It's like a clockwork. But here, Frank points out that at its outset, Newtonian physics was not seen as mechanistic. It had this weird action at a distance. So the good old mechanists of the day were aghast at Newton's weird ideas of this sort. That's not good mechanism. But when we came to the end of the 19th century, Newtonian physics was again taken to be paradigmatically mechanistic. It gives us this clockwork universe. So what's the problem here? One of the problems here is that we want to have these analogies, where we probably should not have any analogies upon which we build. So, should we think of modern physics, be it general relativity or quantum mechanics, as analogies to organisms or to mechanisms? Well, Frank says neither. We need a new conception, which he calls the logical empirical physics, which I fear is still sorely lacking. So, it was long taken for granted that the principles from which the facts had to be derived should contain a specific analogy, either to organism or to mechanism. Nothing was required except that the observed phenomena could be derived from the principles in a consistent way and as simply as possible. There's a no missing. It was no longer taken for granted, sorry. The words and the symbols that occurred in the principles and the way that were connected could be invented according to their fitness as base for the phenomena discovered by the experimental physicist. This new aspect of physics, which missed any traditional analogy and stressed only the criterion of empirical confirmation and logical coherence, may be called logico-empirical physics. So, under this name of logical empirical physics, I refer to the physics of the 20th century and dismiss by this terminology all misleading metaphysical interpretations of relativity and quantum theory, which we owe to philosophers, sociologists, theologians, and I'm sorry to say, also to some physicists. So he's saying we should let go of these old ways of looking at things and just accept that we have these weird mathematical formulae and we have ways of seeing how they fit in with the world, and we just go that way. We do not assume that the world is an organism or that it's a mechanism or whatever. We just take the best possible principles we can find and the best possible theories we can find, try to build up new, and we do our experiments and we see what happens and let go of sort of the idle philosophizing that has plagued philosophers and scientists of old. So thank you for your attention.
I just wanted, might not be the most important point, but just since this scholastic distinction between scientific and philosophic truths was mentioned, and specifically Thomas Aquinas, I think I have to point out that Aquinas doesn't draw the distinction that way. In the first part of the Summa Theologiae, in the first article, first question, he speaks of things which we can know by the light of natural reason, and then things which require the light of a supernatural light, meaning divine revelation. So he wouldn't have drawn it that way because he saw philosophy as part of science. So maybe not the most important point for your talk, but
fair enough. I'm not always sure whether Frank is very careful with his historical analysis on these things. But nevertheless, there had been attempts by philosophers and theologians to sort of do that kind of a distinction, not the one you attributed to Aquinas, but the one that Frank
yeah, I mean,
attributed
scholastic
to him.
can mean lots of things, but since Aquinas was mentioned by name, I felt obligated to defend my hero.
Yeah, that's a fair enough point.
Earlier on, you said that metaphysical assumptions can be Frank said that metaphysical assumptions can be pragmatic, and so they were useful in developing scientific theories. But then at the end, you seem to say there's no room for metaphysical interpretation. So it seems a bit of.
Well, yes, that sort of is the thing that it's. There are people who say that you need to assume something sort of extra empirical when you're doing science. And Frank says, well, yes, but you don't have to assume the same thing all the time, and you don't have to keep them assumptions. You can see whether or not they pay their way in making our theorizing better or what have you. So it's not saying that we will at no point ever have any sort of, let's call them extra empirical assumptions, but just that those assumptions are liable to change and have changed in the history of science.
Yeah, it kind of reminds me of, I don't know if it's logical empiricist, but Herbert Feigl and surplus content of theoretical terms. Is that the same kind of thing?
I'm unfortunately drawing blank at the moment. But not a bad question.
Have you thought about the connection between Frank's ideas and sort of modern forms of ontic structural realism in the sort of form that sort of French or Ladyman or me, I guess, have thought about it? So it feels like some commonalities. There's less of a tie to the sort of logical linguistic form, but there's some of the same sort of desire to avoid metaphysical commitments that go ahead of what the science needs or privileges intuitions about ontology.
Yeah, I actually haven't put too much thought into it, but I see there are commonalities. And just sort of a contingent autobiographical point, I was more or less led to stuff like this through reading Everything Must Go back in the day. So there's a sort of a connection to this way of seeing science and the role of philosophy of science and the role of metaphysics in all of this, which leads to certain kinds of ideas if you start from certain kinds of other ideas. So there's a lot of commonality. Now, Frank might not be all too happy with the added sort of realism bit, but I don't know. might have been, because some of the Vienna Circle people actually wanted to hold on to something like realism. Schlick famously wrote even a paper on his empirical realism, was it?
Yeah. Well, I mean, at least at the formal level, one substantial difference is just the idea that for Ladyman and Ross, that they want something like a semantic view of theories and not a kind of axiomatized picture. But I kind of feel that the Frank you're describing ought to accept that as a friendly amendment. And then I wonder if the gaps are all that large between them.
Probably more of sort of taste than of substance. And it's true that the sort of the old syntactic view of theories and models probably is unworkable. So.
Ilmari Hirvonen. Thanks. I'm referring to the previous question. So when you said that Frank is fine with these sort of pragmatic, non-empirical assumptions, whatever, this sounds something like the Reichenbachian distinction between the context of discovery and the context of justification. So would you be inclined to say that Frank says something like, in the context of discovery, it's fine to have this sort of non-empirical assumptions, but in the end they're not justified? Or is there something else going on here?
Yeah, well, most likely he would be willing to say that. But then there's the but the point wasn't that it's in the context of discovery, but it is in the context of justification that we need these, or might at the very least need these kinds of this extra structure, but that the extra structure always has to be for a purpose. It has to add something pragmatic to the situation. So you cannot just add extra structure that is idle. I think that's Frank's main point. And I think that's my time. Thanks all.
Thank you. And now the last speaker of the day is Tuomas Perno.
Great, thanks. Thanks for this opportunity to give a short, sharp TED talk on a topic that nobody finds interesting or controversial. Yeah, so is the causation in science, in physics. I don't have a nice table of content, hopefully able to give you a nice historical narrative that you can easily follow and discuss during the salad and drinks. So causation, obviously, fundamental, important notion in philosophy, history of philosophy, metaphysics, philosophy of science. In the sciences, a fundamental, important notion, and in common language, common sense too. And when you look at the kind of textbooks on causation, on textbooks on metaphysics, all these stories start from Aristotle and his 4 definitions of causation. Then during the medieval times, nothing happened, obviously. And then early modern era, PSR, the principle of sufficient reason. And when reading of this is a causal reading, that every event has a sufficient cause, of course. I don't know what PSR really is, but it's a much more richer notion. And during that time, the idea that the simple substances and their causal relations is the fundamental thing. And then along comes David Hume and says, no, there is no such thing. There are no necessary connections. There's no causal glue out there, just a series of events. Then Kant, who says, well, okay, then causation is a category of our understanding, and we don't know what's really out there. Currently, we are at this. Russell's paper on the notion of cause came out a bit over 100 years ago, but this is the paper that dominates the discussion now in philosophy of science, philosophy of physics, done by philosophers. He says here at the beginning, all philosophers of every school imagine that causation is one fundamental axiom, or axioms or postulates of science. Oddly enough, in advanced sciences such as gravitational astronomy, the word cause never occurs. So So the modern science, physics, the fundamental sciences don't use this notion. And the law of causality, I believe, like much that passes muster among philosophers, is a relic of bygone age, surviving like monarchy only because it is erroneously supposed to do no harm. So what exactly is the problem here? So here's from Matthias Frisch's nice Stanford Encyclopedia entry. I'm not going to go through all of these, but maybe the first and the last one are most important. The first one is just the conceptual point that it's not clear at all what causation conceptually is, and there's even contradictory intuitions there. And the most important thing maybe is that causation seems to be a time asymmetric or asymmetric relation par excellence. And then our fundamental physical laws are obviously formulated in mathematics and are symmetrical in a variety of ways, but are time symmetrical in particular. So now if this was a class, I would ask you to tell me, is there something missing in this list? And because I think there is. So this is obviously Newton's work, and Newton was obviously I mean, I'm not a Newton scholar. I'm happy to talk about this more during the salad and drinks. But he obviously formulated these astronomical and mechanical laws, and mathematical laws came up with these mathematical laws. But he himself, I mean, many others at that time, but he himself was bothered by this. And he didn't think that these are fundamental laws, that there are these simple substances or whatever that actually transmit these forces or explain this dynamics. So this problem doesn't seem to appear on this list, at least not directly. It might follow from these problems somehow, but I don't think Matthias Frisch addresses this issue. But so what has happened in the philosophy of science and in the philosophy of physics for the past 20 years or so is that a significant number of people have been taking for granted that there is no causation at the fundamental physical level, physical theories, and the only kind of interesting question is, so how does causation emerge? And it's some sort of a macro physical or macro or folk notion, whatever. But there's no causation at the fundamental level. Weirdly, at the same time, there's been a big shift from this deductive nomological, this law and a mathematical kind of a based explanation to causal explanation. Let me just point to kind of a sociological, historical observation that for the past 40 years or so, people have been in philosophy of science started to focus more on the special sciences, biology, psychology, neuroscience, social sciences, medicine, and so on. And in these fields, both in these fields and this philosophy that deals with these fields, the notion of causation is central. So most of the literature nowadays on scientific explanation is actually about causal explanation. And what has happened to this is that now people have started to ask, so how does mathematics then explain? Because now everybody's talking about causal explanation. So now it becomes a mystery, how does mathematics explain? And this is now kind of a recent philosophical consequence of this historical development. But at the same time, we have this discussion in physics and mathematics, and here is a very famous paper by Eugene Winger. So I had to think about this stuff for this talk a little bit, and I think there's actually kind of these are the real problems that we are facing, which might be one problem at the end. But the first one is what Eugene Winger is talking about, the problem of mathematical spooks. This is my term. So how can the results of pure mathematics or purely mathematical entities that we have postulated be useful in our physical theories? And then there's a fundamental, this Newton, or the problem that was prevalent in Newton's time, what are the ultimately real transmitting mechanisms of the dynamics that we observe. And this is maybe my own motivation, not in physics, but in general, this is what many people in the special sciences are concerned when we have some mathematical results, statistical results, and then we want to know what really causes the stuff out there. Now, I want to offer my own solution, which I call manipulative structuralism. So we have to approach this from the perspective of the notion of causation, so what is causation, and then from the perspective of mathematics, or what is mathematical explanation, and relying on a kind of model-rich notion of causation, which I here define very broadly as an account where causal connections are connections between the values of variables of a system of interest that remain constant. Stable is the word that people use often under specific variations of the system. So some sort of manipulationist, interventionist difference making account of causation. And then an account of mathematical entities and mathematical explanation, structuralism, where mathematical entities are structural or relational, and manipulative structuralism would now say that mathematical explanations are to be understood as hypothetical manipulations on a system. And my point is that we can actually come to this conclusion through physical or mechanical observations. So this is actually what Archimedes did with his proof of the law of the lever. He fluently wrote this treatise in English, geometrical solutions derived from mechanics. So actually mechanical or physical observations and manipulations base our mathematical proofs. And here's a nice passage where at the end he says, "For of course it is easier to establish a proof if one has in this way previously obtained," so in this way in mechanical manipulations, in this way previously obtained a conception of the question than for him to seek it without such a preliminary notion. So we have this mechanical understanding of the world that kind of gives us the solution that we are trying to get at, and then we formalize this with mathematics. And I would say that he is here grasping at the very notion of a system or idealized system. So the idea of a relevant physical system is kind of comes before we establish a mathematical proof with respect to it, and that's what he is actually doing with the proof of the law of the lever. There's actually a couple of papers with this title out there, The Unreasonable Effectiveness of Physics in Mathematics. So this is an ongoing discussion, and people have been formulating physical mathematics. So it's not just that we have mathematical physics, but we actually have physical mathematics. So what I suggest at the end is that we have two problems: the unreasonable effectiveness of mathematics in physics, this kind of a traditional, typical problem, but we actually have a lot of historical examples of this other issue, the unreasonable effectiveness of physics in mathematics. And I suggest that maybe these come together under manipulative structuralism. So, I mean, the question of is there causation in physics is an ill-posed question. There's a continuum of systems, simple, idealized mathematical systems based on mechanical observations, and then we have richer and richer systems where kind of this concrete idea of causation then emerges. Thanks.
Thanks. I guess I'll get a clearer view of manipulative structuralism if I can understand how it's different from more standard views of causation. So, two sub-questions. Could you say that it's like counterfactual theories of causation where the manipulation relations provide the ordering on possible worlds, like the accessibility relations on possible worlds? And B, how is it different from, say, some kind of interventionism like Cartwright's view?
Sorry, what exactly is Cartwright's view?
The idea that causation has to do with, or maybe it's not Cartwright, maybe it's hacking. The idea that causation has to do with interventions in experiments and where we can intervene and where we cannot, and that's what yields the causal relations. It's relative to our the kinds of manipulations we can make in experiments.
Yeah, I mean, I'm not that familiar with Cartwright's view, although I have her paper there because it's a historically important paper. I mean, what I can say is that my motivation, I come from the interventionist counterfactual difference-making background. And what I find problematic there is that you have to assume this system in order to, this kind of model space where it would work. And of course, they don't really give that account. I mean, Lewis has his ordering of possible words, which is quite terrible. But that's basically where it is. And that's where I'm kind of trying to get at this, that there are these actual model spaces out there that we can observe, that Archimedes does observe. And that gives us the system, which is these rules of manipulation and space of relevant variables.
Okay. Quick question. I just talked to a famous physicist about the same problem of the unreasonable effectiveness of math in physics and physics in math. And he thinks it might have something to do with the brain. That somehow this is the third part of the system that needs to be considered. I just wonder what you think. And thank you for your talk.
Well, of course, the easy answer is that everything is dependent on the brain. So, I mean, I don't really get what is supposed to be that special there. But we can talk about that.
Thank you very much. And now we have the hard problem of finding the universe reception, but we try to make it easy.